So very good morning to all. Hope that you might have enjoyed the previous sessions. Today we are going to start the first session. The speakers are Professor S. Muthusamy from Trichy, Professor K. Sathiyanarayanan from VIT Vellore, Dr. V. Sivakumar from IIT Hyderabad, and Dr. Annadhasan from, and then Kishore Natte from IIT Hyderabad, and Annadhasan from IIT Hyderabad. So we are going to start with the first lecture. So Professor Muthusamy, so I am actually honored to introduce Professor Muthusamy. So he is my senior. So where we did that PhD in the same Department of Organic Chemistry, University of Madras. So Professor Muthusamy has enormous publications, and he has worked in the organic synthesis, so development of macrocycles and supramolecular chemistry, this of new molecules of with the stereo selectivity and metathesis reaction and green chemistry. He has published numerous papers and patents. Also, he has been awarded many awards. So, the few of them I can read: a fellow, the Royal Society of Chemistry, UK, at the year 2021, and Tamil Nadu Scientist Award in Chemical Sciences in the year 2018, and Council Member CRSC, Bangalore 2017 to 23. The list is extending. So also he has delivered many lectures in various platforms, conferences. So with this short introduction, I may invite Dr. Muthusamy to deliver his lecture.
So, very good morning to everyone. So, it is a great pleasure for me. So, Friday, 23rd February. So, we are here in MKU. So, first I acknowledge the Dr. Sivakumar, who is taking the pain in arranging this event for 3 days event on the national conference on current trends in chemical sciences. So, it's a first of all, no, it's so difficult. It is not giving lecture is difficult, but it is arranging this kind of event in the state university. It's a challenging job nowadays. So as I know that sister university, Madurai Kamaraj, is always very tough to arrange this event, and then the accomplishments goes to Dr. Sivakumar in gathering this kind of crowd after COVID. We don't have any kind of direct contact. So it's a great thing to be here. So the morning lecture, so what I want to say is the synthesis of thioethers, and then the thiazolo 4,5-B indolamines, and then the diindole fused macrocycles from diazoimidamides. So that's why, because what we are working on the diazocarbonyl compounds, so the functionality always will be the like our carbonyl compounds. So we always work on the diazo functionality as the structure is shown here, the C double bond N2, and also the other side we have given the sulfonamido-indole. So that's a diazoimidamide is this system, and this is a 2-sulfonamido-indole, N-tosyl group is there. So we used mainly these two substrates for today's lecture. At least what we could be able to do, some of the substrates on thioethers and fused indole systems and macrocycles, these three systems. So I would like to show that. Yes, so So you can see that indole, I no need to give any introduction because the whatever the heterocycles units we study in the master's syllabus. So you can see that you have plenty of alkaloids when you substitute on indole system, or if you take any kind of a fused heterocyclic system, if you are incorporating on the indole system. So plenty of applications, we no need to discuss further on it. And you can see that the reserpine already it is there as a commercial molecules, and you can see vincristine, vinblastine. So whenever you study about indole alkaloids, the students will remember always all these natural products, indole based natural products, and we don't have any shortage on these systems. Okay, so you have plenty of alkaloids, you can name it, and the biological activity, so there is no other place. So just for the student purpose, it's just the indole heterocyclic system is given. So we all study the alpha and beta position, or 2 and 3 position of the indole heterocyclic system. Okay, so then let us come to the diazo functional group. So you can see that the diazo functional group, you can see the compounds containing C double bond N2. The diazo functionality, whenever it is there, the compounds are very labile. So that means, you know, what is a labile? Labile means it's a completely unstable. So that's a problem. So whenever you try to make some molecules based on the C double bond N2, otherwise, you know, if it is a carbonyl compound, you don't have any problem. You have a ketones, aldehydes, plenty of compounds we make, all kinds of reactions involving name reactions and so on, we do and so on. But in the case of C double bond N2, the functional group itself labile, and because it's thermally as well as photochemically reactive. So that's why, you know, whenever you make a molecule and keep it on the lab bench, and if you go for a lunch and then come back, then the molecule may not be there. Okay, so that's a problem. So that's why, you know, one has to be little skillful to handle the compound. So that's a mark I would like to have. So even some of the compounds are explosive in nature, but anyhow, we never come across during our work on the 2 to 3 decades, because what the C double bond N2 functionality, what the molecule goes out is a nitrogen gas. So any molecule, the solid state to the gaseous state when you make, so that's nothing but your crackers. Okay, so that's what happens when the molecule is there. So you can see the molecule of nitrogen always goes out and creates the gaseous state. So that's why the molecule handling is always sensitive. The student should take care just to handle these molecules. And you can see that the functional group, for the master students, you know that it is exists in the dipolar nature, and you can have the resonance structures and so on, and you can see single bond N, triple bond N, the molecule of nitrogen goes away, and one can generate a carbene as a reactive intermediate. So that's what our interest on our research program, and generate a carbene intermediate, and then you do further reactions for the application purposes. But otherwise, if you take a carbenes, you don't have a name reaction involving carbenes, because the carbenes provides you plenty of products, and thereby you will end up in the mixture of products always whenever reactive intermediates such as carbenes exist, because it's a highly reactive intermediates. So that's why what we do normally in our program, so we make kind of transition metal, we always incorporate in our reactions and create a metallocarbenides to control the reactivity of the carbene. Then you do some synthesis based on that, and we have made based on that 2-3 decades, we made many new molecules based on the carbene as the source, and we could make some chemistry, develop some new chemistry on it. Anyway, today's topic, so I am not going to touch upon the metallocarbenides, and which not forming in this part of this lecture. And you can see many reactions which we could develop on the metallocarbenides also. Then when you take the diazo compounds, then you can play with the substitutions on the left and right, whether it is electron donating group or electron withdrawing group. Based on that, reactivity is controlled, enhanced, or diminished, and so on. And one can play with it with your substituent on it. Okay, so that's how we do that. And the right hand side, whatever the molecule is given, so we thought that it's a very labile compound. It may not be existing in nature at all, because we can't get any kind of natural products and so on, because whatever expertise which you develop, and you have to go further, whatever the nature does, that's the ultimate aim, end of the day for us. So you can see that the kinamycin is a diazo functional group containing natural product. nature also makes these kind of molecules. That's surprising to us. How this labile compound exists as a natural product, and that's a interesting part of the diazo functionality, and that's how you can make some of the naturally existing molecules which also exist, and which gives us confidence. Yes, when the nature makes the molecules, so that means there may be the advantage to develop this synthesis and also to provide the kind of things. So this slide is just introductory part of our previous work. So anyway, it's just briefly we just given some few reactions which we have done in the research group, and you can see that the diazo containing indole system. So we worked much on this particular molecule, and that molecule itself we have made more than 20-30 research articles on it, and you can see that only this particular molecule having the diazo functionality at the third carbon of the indole system, and you can see that indole 3 carbon you can generate a carbene, and based on that you can perform some interesting reactions, and you can see that if you react with the furan, so what you get is the conjugated alkenyl system on the third position of the indole system. And you can see that then we have also done some of the reactions with 2 diazo functionality, that means bis diazo compounds, and we thought that we could not do at the beginning, but you can see that mono functionality itself is difficult. I told it's a labile in the nature, so that's why we try to make bis diazo compounds and try to make the tricyclic complex systems to go further, and where you can generate a carbene in this carbon also, carbene in the down and the bottom diazo compound also. So then you can synchronize both the diazo functionality in such a way to study further, and you can see these kind of systems we have done, and you can see some of the compounds on the heterocyclic system in the spiro system on the third position, and you can create many heterocyclic systems, whether it is a nitrogen, oxygen, or nitrogen. So we played many possibilities, whatever the possibility you can think of, and you can make many spiro heterocycles, and then some of the macrocyclic compounds also we have already demonstrated in the recent past. Okay, so now for the today lecture, so what I want to have is only the 3 systems I just concentrated, and you can see that the diazoimidamides and sulfonamidoindole, which I showed the structure in the first slide itself. Then to synthesize the 3-indolyl thioethers, the sulfur containing compound on the third position. Then the second system is a thiazolo 4,5B indole, so that's a fused thiazole system with the indole heterocycle, and then diindole fused macrocyclic system. Okay, so these 3 systems let us see quickly. So now let us see about the starting material diazoimidamide, which I said, and you can see that this system many of us know it, and you can see that what you want to have is the indole containing the triazole you have to prepare, and you can see that the indole containing triazole system. So you can see the triazoles we all know very well. It's a very stable triazole system, and you can see Professor Katersky from USA, he has worked in his field, all are benzyl triazoles. So he has more than hundreds of research articles he has published on the benzyl triazoles systems for variety of applications he has published, and many other research groups also, and they worked on the triazoles. But here you just see the structure of the triazole, indole and triazole fused ring system in the equilibrium, and you can see the left hand side, that is a required compound. So what we want to have is the diazoimidamide. Okay, so it is not the structure wise, it is a indole triazole, fused indole triazole, or you can say that it is a diazoimidamide, it is isomeric form. So it's what is the structure, and even whatever the ambiguity is there, even in the diazo structure itself, first slide I showed C double bond N, that is a textbook chemistry which we write. Even that structure is still questionable, whether it is a linear form or it is a cyclic form, kind of diaziridine. Okay, so it can be carbon, nitrogen, so it can be a 3-membered ring. The diazo functionality can exist also in the 3-membered ring also. Okay, so that's why the ambiguity is there in the structure of the diazo functionality itself, and now you can see the triazole, and then you can see the diazoimidamide, you can have this system. Okay, but so what you try to synthesize is the triazole system, and that will exist in the diazoimidamide, then you can do further reaction with the diazoimidamide itself. Okay, that's what. Then you can see this kind of research, and you can see Dr. Annadhasan from IIT, he has written a nice review article recently, and you can get much information on this review article. How this is a triazole system, which we all know very well. This triazole exists as a structurally diazoimidamides. Okay, so based on that, we just prepared this triazole on the indole heterocycle and the corresponding diazoimidamide on the indole heterocycles, because based on the indole nature. Okay, so that's a lot of studies known in this kind of system, so there is no ambiguity in the existence of that particular structure. So we just took that as a starting material, and you can see this is again the literature on it. So just let me skip that, and you can just see here. So if you take the indole triazole, and it will exist as a diazoimidamides on the right hand side, and you can see then sometimes you can try to oxidize it, and you can get diazoimidamide or 2-tosyl imino indole, okay, sulfamido indole. Okay, so these kind of two starting materials one can prepare. So here I just showed the reaction so clearly. So the indole with tosyl azide 3+2 cycloaddition provides the indole triazole. So they oxidize it, and you can get the indole containing the triazole. So then it ring opens automatically, provides the diazoimidamides, and then diazoimidamide you can write the resonance structures, and then that diazoimidamide decomposes, go to the sulfonamido indole, 2 sulfonamido indoles. Okay, so these starting materials we have taken for our research purpose, and you can see again the students can see that it's quite nice, because it's all heterocycles, you have 2-3 nitrogen atoms, so it's quite easy. Now you can see the diazoimidamide, whatever you say that it is in the solution, you can see when you crystallize it, and you can just filter it, and very nice orange crystals, one can do it. Even though diazo compounds are labile and all these things, and I said already, but you can see some of the compounds are crystalline in nature, so you can see that the stability is good to proceed further. Okay, then so let me skip this spectra. So for the starting material, so you can see that based on this diazoimidamides, and you can see with the metallocarbenides. Okay, so anyhow, here I am not putting any kind of metallocarbonide work here in this lecture. So this is from literature from other research groups, what they have done it. I just showed some of the rhodium carbonides, people have tried it, and you can see some of the molecules which they can make from the diazoimidamides and so on. Okay, variety of systems they could make on the diazoimidamide as the starting compound. Okay, so now you just see here again there is diazoimidamide work on the literature, so you can make the 2-3 fused system on the indole system, and you can see the 3 spiro system also one can make from the enaminothiones when you react with your diazo compounds and so on. Okay, so you have the starting material is quite stable, so and again it's established to have some kind of reactions. So as I said, the thioethers, how will you make here? Again, it is a indole containing the thio group, thioethers on the 3 position. So you have a variety of biological activity already established in the literature. And then when you want to have a thioethers, what you can do based on the diazo functionality which is in our hand, and you can react with your thiols. Okay, generally SH insertion, insertion reactions one can do with the carbene, and normally literature there are reports one can find out easily to have a SH insertion with the corresponding thiols. So what we have done is, so we took this diazoimidamide, and you can see that with the just treat with the Lewis acids, and you take some cyclic thioamides, and or you can have a substituted thioureas, okay, as a reactant, and still you can get your SH insertion here. So again the thioethers one can get in the 3rd position of the indole, and also the right hand side you can see when you react with the thioureas, and you will get the corresponding thioether on the 3rd position of the indole. Okay, so this part is called carbamido thioate, that is a functional group, with the carbon having 2 nitrogen atoms and 1 sulfur atom. Okay, so with this with this work, so we could be able to demonstrate with a variety of substrates to establish on the cyclic thioamides and then thioureas or thiosemicarbozones, okay, any kind of a thioamide systems, one can have it to have the reactions on it. Okay, so here just to establish the reaction conditions and a variety of Lewis acids and Bronsted acid also and some different solvents. So what we try to optimize is BF3 and dichloromethane, room temperature, and you can see the starting material equivalent of a diazo compound and then your thiourea or thioamides, or you can say that thiosemicarbozones and so on, and you can see you will be end up with your corresponding 3 thioethers, okay, indole 3 thioethers. Okay, so now you can see substituted thiourea also, corresponding substituted thiourea with the diazoimidamide, and you will get corresponding 3 substituted thioether, and that is called carbamidothioates. It's a nomenclature for this system, and you can see that carbon having 2 nitrogens and 1 sulfur is called carbamidothioate. The students can note down that kind of a functionality, and you can see that a variety of substrate scope, definitely you have to demonstrate your methodology. So whatever the electron releasing or withdrawing and so on, and you can see that you should have a variety of substrate scope. So you should have the substitutions on the indole ring system and also substitution on the thiourea. You can have a symmetrical or unsymmetrical and so on, and you can see this is the unsymmetrical system. One is allyl group, and you can see one is unsubstituted amine. Okay, so that's also surprising to us. So you can see that even NH2 group you can have it without substitution also, the reaction works in it. And then this is on the extending from thiourea to the thiosemiCarbazone, and you get a corresponding thioether from the thiosemicarbozones. Under the similar conditions, you can see that the corresponding thiosemicarbozones provides the carbamidothioate on the at the third position of the indole system. Okay, so you have a substrate scope. Again, you have a variety of substrate scope on it, and you can have different substitutions and to do it. Okay, so one can extend plenty of molecules on that, then including the crystal structures and so on. Some of the packing arrangements which we have shown with the CH pi interaction is available on the crystal packing and the solid state structure of the product. Okay, so now you can see that a thiourea or thioamide or thiosemiCarbazone, and even you can have a cyclic thioamides and so on, but that will exist as a SH group. So there should be a double bond, N double bond CS. So there should be a cyclic thioamides, and you can have a corresponding carbamidothioate in this some cyclic heterocyclic system you can introduce at the third position of the indole system. Okay, that's what it is shown here, and you can see first compound is with the imidazole thione. Okay, so you can have a benzene imidazoles and derivatives and so on. You can have a variety of heterocyclic system linked with thioether functionality. One can get from diazoimidamides. Okay, so this is mechanistically how it works. So the reason is already known in the literature with the thiols, SH or mercaptan. Sometimes people say it's called mercaptan, and you can see that this thiol functionality, how it comes from thiourea or thioamide, it is just a tautomerism, and like your thioamide to amido-imidal tautomerism, which we study in the masters, or ketoenol tautomerism, and you get imidal, thioimidal, thioamide and thioimidal tautomerism. So you get C double bond N and SH, and this SH functionality is reacting with your diazocarbene, carbene generated from the diazo functionality, and undergoes the SH insertion. That's what the mechanistically given to provide your corresponding thioethers, okay, in the product. Okay, and this second molecule. So second molecule what we given is a thiazolo indolamines, and you can see the indole having thiozoles, and you can have a variety of systems, and what we are given here is a 3,2A or 3,4A, 5,4A, 5,4E and 4,5E. So I hope the students knows the heterocyclic nomenclature based on the ring fusion of these two heterocyclic systems, and you can see in the literature all these systems are known. In the 5,4B, so what we have done is a 4,5B, so that kind of the isomeric structure of that which we could able to get it. Okay, so you can see that these kind of thiazole fused indole system already known in your biological activities and so on, and already indicated in the literature. And you can see that how the thiazole rings and the indole rings are again biologically active. Okay, so here what we have done is you can just go back and see that what we can done in the isomeric form. Yes, so isomeric form, you can see 5,4B is having nitrogen and sulfur on the same side. Okay, in the 4,5B, the indole nitrogen and the thiazole nitrogen will be on the same side. That's a isomeric form, the reverse of it. So how it is reported? So there is only one report. It is there in the literature, and I think one is a patent. And you have a bromothiazole they took, and then the orthonitroboronic acid, phenylboronic acid, and they could be able to condense these kind of systems. So you can see the nitrogen and thiazole nitrogen on the same side. That is a system what we claim is a 4,5B ring fusion on the heterocyclic system. Okay, so what we could be able to synthesize based on the thioether work which we have discussed just now, and you can see that from diazoimidamide, you take substituted thiourea, and what we get is, and you can see what we have done, what we modified, slight modification, catalytic amount of BF338, and the co-catalyst is the camphor sulfonic acid, DCM and methanol, mixture of solvents, and what we get is the system is the thiazolo indoles with the 4,5 indole, where the nitrogen, indole nitrogen and the thiazole nitrogen on the same side. Okay, so you can have a variety of isomers on that as it is indicated in the literature. Okay, so based on this, and one can generate some kind of substrate scope, and you can have a the optimization as I said, and you can create the substrate scope. So here you can see that another side product is also obtained and without any cyclization. So what we get is the first one is the carbamidothioate, and which we further cyclize to get the thiazole. That's what the objective. Okay, so it's that's why we could be able to get that compound. So thiazolo indoles, and you can have a variety of substitutions based on this method. BF338 followed by camphor sulfonic acid, you can get the cyclized to get the indolo thiazoles with 4,5B nomenclature. I hope the students should aware that how to give this the ring junction between the two heterocyclic system. Okay, so you should be familiar whether it is 4,5B or 5,4B. You should know familiar with your nomenclature on the heterocyclic system. Okay. Yes, so this is some of the control experiments which we tried for this thiazolo indolamines, and a variety of conditions we just tried because it forms. First step is the thioether, and then the followed by cyclization. So we have isolated the corresponding thioether and reacted with the camphor sulfonic acid to cyclize to the indolo thiazoles and so on. Okay, we just confirmed all those things and so on. Okay, this again followed by HPLC and so on, to have a thioether as well as the thiazoles, and both are forming in a reaction mixture. So which is also followed in the HPLC, and we could confirm that yes, it involves the initial step is the thioether, then further cyclizes in the presence of camphor sulfonic acid to give the indolo thiazoles. Okay, so this is just a mechanistic skip, so I will just skip it. Then let me come to the last part of my lecture. So this is a di-indole fused macrocycles. So what are di-indole fused macrocycles? So just to give the introduction, you have the macrocyclic ring, and the macrocyclic ring should have a 2 indole fused system. Okay, so how will you get 2 indole fused system on the macrocyclic system? So that's what the objective to do that. Okay, so here what we have taken is, and you can see that the 2 sulfonimido indole and react with your simple aromatic aldehydes and paratoluene sulfonic acid. So you get a bis indole systems. Okay, this reaction is known with the indoles, and which we repeated with the sulfonimido indole. You can get the bis system and also mono arylated system also. You will get a mixture of the compounds bis and mono. You will get a 3 and 4, and you get conditions with the paratoluene acid. So you will get a bis indole system. So what we taken the bis indole system as the starting material further, and you can just see variety of bis indoles one can have it. So if you have a thiophenoldehyde or paramethoxybenzaldehyde or dinitrobenzaldehyde or trimethoxybenzaldehyde, doesn't matter. So it forms the bis indoles. Easily you will get the corresponding bis indole system from these two sulfonimido indoles. Okay, so what we have taken, so these compounds are again important to us. So what we have done is we just try to functionalize this NH, 2NH functionality. That's where our target is. So what we did is a very simple reaction. So we took, let me go to the second step directly, and you can see the second step is here. So what we have taken, the bis indole system having two NH groups, and you just alkylate it very easily. Take a dihalo compound, and you can just do the simple cyclization, N-alkylation, with the 2N alkylation at a single step. It works with DBU, mild base is enough, and you can get your corresponding the macrocyclic compound. Okay, based on the dibromo compound, so whatever the space length which you use, and you can see that increase the ring size, maybe the 12 or 15 or 13. So that's the tailor-made molecules. You can make it very easily, and all these molecules, you have a macrocyclic compound. The left hand side one indole unit, right hand side another indole fused unit will be there. Okay, so one can get easily. So that's again solid compounds, and one can crystallize, and you can get the crystal structures to confirm without any ambiguity for the structural data. And even in the spacers, you don't need to put only the aliphatic spacer. So even you can incorporate some kind of aromatic spacer with a para or meta and so on. You have the variations which you get, different variations you can get it. Okay, let me skip the spectra, it's not required. And here again, mechanistically it is not challenging. So when you have the bis indole system from the aldehydes, and what you have is a 2NH functionality. So you are just alkylating, bis alkylation, bis N-alkylation, which we are trying to do that. Okay, so this I can skip this one. It's just a bis indole system. So here what we did, little small change we did it from diazoimidamide. So we took the 3 substituted, tosyl amino substituted on the 3 system, and we could get the CH insertion at the indole 2 position, and again that gives our again the 2NH functionality on that compound. Okay, so this is again the different system, that is a bis indole which I have shown in previous slide, and here it is a bi-indole. Okay, so you can see the indole units are directly connected with the CC bond, and you have a 2NH functionality. Again you can try to alkylate and connect these two NH groups, and which we have done here, and you have a dihalo compound in the aliphatic chain, and you can see the bis indole having dialkylation on the other side. Again you can have a different macrocyclic system, and the ring fusion location will change. Okay, the different location on the macrocyclic system. So one can have the different diindole fused macrocyclic system. One can synthesize from your diazoimidamide as the starting material. And you can see another reaction which you have done. So you take this diazoimidamide, you link it with the indole, and you can just see that the intramolecular alkylation with the copper triplet. So what is the indole 3rd position undergoes a C alkylation with the carbene-carbon, and you get another macrocyclic system, and again the fused with the 2 indole systems. Okay, you have a 2-3 types of macrocyclic system on that. Okay, so with this let me conclude, and what we have done is you can see the preparation of your the diazoimidamide, okay, and also the 3 sulfonimido indole and 2 sulfonimido indole, and you can see the SH insertion from your whatever the thioamides, thioureas, semicarbozones or cyclic thioamides and so on. You have the plenty of possibility. That means you no need to take a thiol. Okay, whatever the enolization that happens, and you can do the SH insertion. That's what I want to demonstrate here, and you can see from the extension of that thioether, you can end up with the thiazolo indoles, and then from 2 sulfonimido indole you can get the bis indoles, and you can have a macrocyclic compounds through simple N-alkylation, the 2 indole nucleus on the macrocyclic core. You can have generation. This macrocyclic system you can modify a little, and you can the same concept you can get a different route from the macrocyclic having on the 2 indole fused system on the system. Okay, so we acknowledge again the SERB and the DST Women Scientist program. So one girl student got the Women Scientist project on that system. So that's how It is her work, her PhD, part of her PhD work, which I have presented. And with this, thank you very much. Thank you for your assessment.
So a couple of questions from the student side. So no? So if, yeah.
No
One more question from the faculty side, this side.
Okay.
Okay, if there is no other questions, so we may congratulate Professor Muthusamy for his wonderful talk.
Thank you very much, sir.
A small moment of photo. Photo liya?
Yes, okay. Thank you.
Thank you.
Yes. Thank you. Okay.
The next speaker is Professor K. Sathiyanarayanan from VIT Vellore. So he has completed his PhD in organic chemistry in Navala University, and he has done a postdoctoral course in Korea, South Korea. Also, he has been awarded the Fellow of Royal Society, and he has many credits in his credential. He has published many papers, research articles. So I welcome Dr. Sathiyanarayanan to deliver his lecture.
Good morning to all. Let me join Professor Muthusamy in thanking the organizers to give this wonderful opportunity to deliver a lecture. I also acknowledge him for the pains taken to organize this conference. So, that is previous professor talked about the organic synthesis. Actually, we also wanted to start organic synthesis. So, the manic type reaction, that is the substance containing two methylene groups flanking the keto group, if it is subjected to reaction with ammonium acetate and aldehyde, you will get a heterocyclic ring. That is well known manic type reaction. So, we tried the same thing with beta tetralone. Beta tetralone is, so if you see this beta tetralone, it is having two methylene groups and we have benzaldehyde ammonium acetate. So we suppose that is we are going to get a product which is having condensation using these two hydrogen, active methylene hydrogen. But fortunately, we ended up with this product. So, when we got the product and we got very good yield of 80% and it was very good crystal. So, first we went for NMR and other basic things. We could not identify the compound because this compound structure, we don't know that. So, fortunately, since we got the structure crystal, then we diffracted the crystal and we got the crystal structure. So, finally, we confirmed this structure. So, it is a highly convergent synthesis, and in the one step, we can get a big molecule like this. So, once we get this, then we wanted to focus on that compound. So, what we did is we tried various applications of this compound, and here you can have n number of substitutions in the benzaldehyde, and you can get any number of substituted phenanthridines. So, this is called the phenanthridine system. So, as sir said, you should be very thorough with the nomenclature. So, then we just published this paper in Journal of Heterocyclic Chemistry and Bulletin of Korean Chemical Society way back in 2009. That is, at that time we started this research. Then we slowly moved to the next step. So we wanted to find out the applications of this molecule. First we tried with biological application. It didn't work. Then we did the applications in photophysical studies. So you know very well that is, it is having a lone pair of electrons. So when this lone pair is used, then this molecule is giving a very good fluorescence. So we thought we can concentrate on the fluorescent properties. So first we extended this to the photophysical properties. So we prepared a series of compounds. So it is having different substitution in the benzaldehyde, and if you use 6-bromotetralone, you can get this, and this can be converted into the corresponding cyanide. So now we have these compounds. Then we just studied the photophysical studies. So we prepared these many substitutions, that is with O-methyl, that is first one is with formaldehyde, this one, this is with normal benzaldehyde, this is with substituted benzaldehyde with normal skeleton, this is with cyanide substitution. So we have prepared this 8 compounds, 8 plus 2, 10 compounds. Then we studied the photophysical studies. So all the compounds were highly fluorescent. We just took the absorption spectra and the fluorescence spectra, and it is having solvatochromism also. Solvatochromism means your emission will get, that is our absorption will get shifted to the various nanometers if you change the solvent. Similarly, emission will also change. Then we went for half-life studies. Then we found out always this nitro compound, that is this one. So nitro compound is having higher Stokes shift and also the higher quantum yield. Then we extended this for a simple application of DNA intercalation. So for DNA intercalation studies, they are using yttrium bromide. So it is having the efficiency equivalent to the yttrium bromide. In conclusion, so first we synthesize the molecule, then now we have slowly moved into the photophysical studies, and fortunately it is giving a good photophysical studies. We published this in the Dyes and Pigments journal. Then we went for some more substitutions to completely study how this photophysical study is depending on the substitution. So previous case, we got a clue that nitro compound is having some higher values of that is quantum yield and Stokes shift. So we wanted to confirm that. So now again we synthesize these many compounds. So again this is having the substitution in the benzaldehyde and also the 6-bromotetralone. So 6-bromotetralone, we have only bromine now. We didn't go for cyanide. Then we prepared these many compounds and subjected to absorption and emission studies. So we got two things, that is, it is having a large molar coefficients of 3200 to around a lakh. Then high Stokes shift value also observed. So we finally concluded from these photophysical studies we can go for sensing, because since we are getting a very high value of fluorescence, quantum yield and Stokes shift, everything, we can go for the photophysical studies. So this is the consolidated value, Stokes shift and quantum yield. So first we tested with hydrogen concentration, we got a variation. So we used trifluoroacetic acid whether it is able to sense trifluoroacetic acid or not. And in fact, it is sensing the trifluoroacetic acid. Both absorption and emission are changing. So, in the absorption, it is changing to the red side, and emission also changing. So, next. So, again, see, we have taken all the values. So, without TFA, with the TFA, we tested this and we got a very good color. So, this is the color change. So, we tested 3 compounds with trifluoroacetic acid and we got the color change. So, again, in the conclusion, we were able to synthesize the compound which are having very good sensing property for trifluoroacetic acid. Then we extended to other molecules also. So, again, now we are preparing compound which is having nitrogen here as well as oxygen, that is, it is salicylaldehyde. So, using salicylaldehyde we synthesized and we treated with BF3 to know whether it is sensing BF3 or not, and it is sensing BF3 very nicely. So, we got values, we recorded the photo of that is absorption and the emission for both compound as well as compound with BF3. So, this is the absorption, and as usual we are getting the solvatochromism. So, depending on the solvent we are getting different colors, and this indicates that the solvents are having interaction with the fluorophore. Then we took the CV also. So, from this we calculated the band gap, HOMO, LUMO, etc. So, next is, this is an interesting one. So, we prepared that salicylaldehyde, substituted phenanthridine, and the salicylaldehyde we made some substitution, that is this R. So, when we are making this substitution, the salicylaldehyde, that is normal salicylaldehyde, is not sensing anything, but at the same time when you introduce NN diethyl, this group, so it is sensing. It is very interesting, that is we have this compound. So, this compound is R is H or R is NN diethyl, this side and this side. So, when you have only H and you are adding aniline derivatives, similarly aliphatic derivatives, so you are getting only blue color, but when you are having NN dimethyl substitution, when you add aliphatic amines you are not getting anything, when you are adding aniline you are getting a green color. So, it is a very clear indication that you can distinguish the primary amine, primary aromatic amine and primary aliphatic amine. So, aromatic amine is giving green color and aliphatic amine is not giving green color. So, next is, so this is the so now the same thing, that is we used ethylenamine and we used the aniline. So, when we are having, that is the addition order is not important, whether you are adding boron trifluoride first or whether you are adding amine first, it does not matter. In both the cases aliphatic amines are not sensed, whereas aromatic amines are sensed. So, the mechanism if you see, that is first you are taking the substance and then you are adding BF3. So when you are adding BF3, you are getting this blue color in case of both primary amine. But when you are adding aniline, you are getting the green color. So, but when you are adding BF3 to this, you are not getting anything. So, it means that it is a sensor for aromatic primary amine. So, this is the coordinate, that is we have done all the studies, coordination studies, then selectivity of selectivity studies. So, in the selectivity it is very clear, that is we are having, in addition to BF3, various boron containing compounds. So, those compounds are also not sensing, that is only BF3 and aniline is sensing. So, when we have, that is we can have the compound, then boron trifluoride, then aniline. Similarly, we can have pre-mixed compound also, that is boron trifluoride and the substance, and similarly we can have boron trifluoride and aniline. In all the cases, it is sensing the aniline. So, we have got a very good sensor for differentiating aromatic amine and aliphatic amine, and the ICT process is there, and we have done extensive study and we calculated LUMO-HOMO energy levels and everything we have done. So, it is so far aniline sensor is very rare. Now, we have got an aniline sensor specifically for aniline, which can distinguish aniline from other aliphatic amines. So, this paper we got published in Dyes and Pigments, that is Photophysical Studies, then Journal of Organic Chemistry we published the aniline sensing. Then this is the next one, that is instead of benzaldehyde, we use cinnamaldehyde. So, cinnamaldehyde we used, that is 4 substitutions are there in the cinnamaldehyde, that is normal cinnamaldehyde, methoxy, NN-dimethyl, nitro and fluoro. So, we studied absorption and emission spectra, and it is having fluorescence in the solid also. So, again we calculated Stokes shift and quantum yield. So, this is the again aggregation we studied. So, the aggregation, when you add water to normally this is done in the acetonitrile medium. So, when you are increasing the water percentage, aggregation is happening at 50%, we are getting maximum. So, again it is used for sensing the pH, that is you can, depending on the pH value, the color of the substance, that is color of the fluorophore will change. So, we added sulfonic acid, then we reversed it by adding triethylamine. So, it is very clear when you are adding the sulfonic acid, the color changes to the red. When you are adding triethylamine, it is reversed. So, this is the mechanism, that is the good old mechanism, ICT mechanism, and because of the change in, that is first if you see here, that is H plus is added. So, this nitrogen is getting protonated, and here this nitrogen is getting protonated. Once you go to this level, you cannot come back. So, the same thing, that is here also we have explained the same mechanism. So, so far, so this was published in RSC Advances. So far, we have studied the photophysical studies, synthesis and fuse sensing. Now, we extended to many metals. So, this is the first one we used for the ruthenium ruthenium sensing. So here we are using propargyl aldehyde, and then we are using this as the sensor for ruthenium, the same thing. Now we have applied this to OLED also. That is, we synthesized this compound and we tested the performance of the OLED. Next is, it is used for cyanide sensing, the same thing. So we never changed our core. This is our core. This is our core, and we never changed our core. So this is for chromium. This is for dopamine, and this is for thorium, and we have studied for many metals. So this is again for and one more thing is the limit of detection. In all the cases, it is almost nanomolar. So you can go to very low level. And this is for aluminum, thorium, picric acid, and this is for again thorium, and this is thorium. So this is copper, cadmium, and this is also for chromium and cadmium. So that's all. So still we are doing many synthesis and sensing properties. Thank you.
Thank you very much, sir.
Finished within the time.
So, one or two questions from the student side. It's allowed. Yes.
Yes.
Good morning, sir.
Yes, Luna.
Sir, are there any potential application beyond the chemical sensing for these derivatives, sir?
We have sensing, and we can apply it for OLED applications also.
Oh, okay, sir. Thank you.
Excuse me, sir. Sir, I have a question, sir, here. Sir, you are detecting aniline, right? So, in case if you are functionalized or any substituted aniline, how about the selectivity, sir?
No, substitution, it depends upon the again substitution.
Okay.
Which substitution you are.
And also you are detecting picric acid, 2,4,6 dinitrophenol. If it is nitrophenol or any
or
two
it is
substituted phenol.
dinitrophenol, it will not sense. It will sense only the picric acid.
Okay, thank you.
So, thank you very much, sir, for your speech. Small moment of. Thank you very much. Thank you very much. The next speaker is Professor Sivakumar Vaidyanathan. He's from IIT Hyderabad. So he has obtained his bachelor and master degree in Muthusamy Arts College, Vellore, affiliated with the University of Madras. And then after that, he has received his PhD from IIT Madras. After a few years of postdoctoral stint in South Korea and France, so he has moved to NIT Rourkela for a few years, and then he has finally moved to IIT Hyderabad. So he has been awarded BRNS Young Scientist Award, DST Young Scientist Award, INSPHERE Faculty Award, and the list is extending. So I invite Dr. Sivakumar to deliver his lecture.
Next. Very good morning, one and all. First, let me thank Professor Sivakumar and Professor Suresh and the Department of Chemistry, MKU University, for giving an opportunity to stand here to present our work here.
So today I'm going to talk about molecular design and synthesis of new TADF material for highly efficient solution process white walnut. Um, of course, I just this is a it's not too old. It's 15 years old institute ours. This is our main building. This is the first building that has been built for the academic dedication. And recently, last year, this building has been dedicated by Professor Govardhan Mehta to the Department of Chemistry. We have 5 floors, and you may appreciate after I tell you that what is the secret behind this, this building. This looks like a periodic table where you have a S block, D block, which is like a color one, and then you have a P block, and then lanthanides and actinides are located in the down. So where we have classrooms are there in this sessions. Of course, we have, I'm sorry, we have a very 3 years back, we started BTech in industrial chemistry, which is a 4 years program, where one need to qualify the JE main and advanced to get into this. And we have regular JAM pass students can come for the MSc Chemistry 2 years program. Of course, what we do is optoelectronics laboratory at IIT Hyderabad, that whatever the material that emit light in the visible photon, we are interested. We are mixed of we have a ceramic, we have a pure organic material, we have a nanomaterial, we have organometallic lanthanide complexes. Whatever compound that emits light, we are interested. So recently we also started up some work on room temperature phosphorescence material in organic material, because in inorganic material it's known to emit overnight, which is called long persistent phosphors. But we have started this work in recently, and then we are mainly working on organic fluorophores which emits in the blue region for white OLED. So today I'm going to talk about this blue component which is present over here. In the Jablonski diagram, what we have known that any light when you shine the system that go to the excited state comes to the ground. I mean the first excited state with a vibrational relaxation, and go to the intersystem crossing, and then it get phosphorescence, and it comes from S1 to S0 by emitting photon, which is a fluorescence one. Based on the lifetime, one can able to distinguish fluorescence and phosphorescence. But in case of photoluminescence, when you shine light, it goes to the excited state with you get 100% of singlet state. Whereas in case of organic light emitting diodes, that is we call it as electroluminescence phenomena, where the organic molecule are sandwiched between 2 electrodes, anode and cathode, where you get here 25% of singlet and then 75% of triplet state. As we know, simple organic system that cannot harvest this triplet state to the ground state, and hence this become a dark excited state. So that means only 25% one can harvest from here to ground state. So when you charge it, the electron, I mean the exciton, that means hole and electron moves in the emissive layer, it recombine and produce photon. That visible photons in the starting from violet to NIR, one can able to get it. Of course, this is the working phenomena where it hole and electron moves to the emissive layer, and then it recombine and produce light. Of course, this has a lot of applications. And there are 3 generation OLEDs been known now. The first generation OLED is been recognized in 1991 in Kodak company, where they use the pure fluorescent moiety. And then you can say, as I mentioned in the previous slide, that it can produce 25% of singlet and 75% of triplet state. So that means in electrically generated exciton, one can only harvest singlet state to the ground state. That means this belongs to the fluorescent OLED. So in the second generation OLED, where one can able to harvest the triplet dark exciton to the ground state by means of spin orbit coupling by using heavy metal ion effect, then one can able to generate 100% of internal quantum efficiency. The third generation OLED says the TADF material, thermally activated delayed fluorescence. Even though this phenomena is known in 1961 in Eoson material. So this triplet state is going back to this S1 state, and delayed fluorescence is obtained. That means one can able to have these all the exciton comes to the ground state by emitting photon that gives internal quantum efficiency 100%. Of course, as I mentioned, the first generation OLED discovered by Tang and Van Vleck in the anthracite AlQ3 material, and then the internal quantum efficiency, as I mentioned, this can be a 25%, and the external quantum efficiency after putting into the device, one can able to limit only the, it can come to the 5% only. Of course, these are the donor acceptor molecule that has been present in the literature. All of them is showing maximum of 5% external quantum efficiency. Of course, obtaining deep blue fluorescent material stands better because whatever the visible photon that we are seeing, it's all related to your eye sensitivity curve. That means the retina, what it says, that only reflected. So based on this, the commission, International Commission for Illumination has given XYZ coordinates that's called the CIE coordinates. The second generation OLED given by the Mark Thompson and Forrest, they use the platinum complexes to harvest this energy to the ground state, and gives, even though it gives a maximum efficiency goes beyond the 5%, but because of the usage of heavy metal ion effect, one reason. The other reason is that obtaining deep blue materials also is very difficult in case of phosphorescence based OLED. Of course, this third generation OLED TADF material, thermally activated direct fluorescence, one can able to have the internal quantum efficiency 100%. So that means the external quantum efficiency can beyond go 20%. So this is Professor Adachi has came up with a concept with the tin porphyrin complexes in 2009. Of course, the challenges that we have to have the blue LED is that there are two standards that has been given in the standard, that is National Television Standard Committee given the value 0.14 and 0.08, the Y value. The European Broadcast Union also given some value with the Y value supposed to be 0.06. Because if you have, that E is equal to Hc by lambda, if you wanted to have the blue color around 400, that means you need to look for the semiconductor which is supposed to have more than 3 electron volt. So wide band gap materials are necessary to get a blue. Also, this blue emitter not only important in case of producing blue color, it is also important to mix with that other complementary color green and red to produce white color. Okay. So that is also this, the blue components are less stable compared to the green and red color, and the severe excitation of electrical excitation, the blue light degrades. That means whatever the white LED that you are producing, the prolonged time, if you keep it, the blue color degraded. That means the white LED which you are getting, it is a mixing of red and green. It's the blue is getting deteriorated. So the other one is the CRI, color rendering index. So you have the 0 to 100, where you take the color rendering index, the sunlight as 100%, and then your artificial lighting that we are seeing in the inside indoor, that you can compare the object in presence of sunlight and the absence of sunlight. So how much the percentage, so you assume that in the object shows 100% in the outside. So based on that, one can able to get this. That means the LED that emits around 55 to 100, one can have good, poor and excellent. That means the excellent one people used in the in the stadium. So more than 90% is required to get a white color which can mimic the sunlight. So we recently categorized them unipolar and dipolar material which are having the linker and without linker. So this basically you take its OLED structure. If I have all only unipolar material, so you have the charge recombination site belongs here. That means it's very, very small zone it belongs to. Charge can come and recombine here. That means the light comes here very poor here. If you have the other one that only whole transporting material will be there, that means only donating ability is there. That means it goes, this also the zone is becoming not wider. But if you have combined both donor and acceptor, that means one can able to widen this recombination zone where one can have the exciton recombination gets more, then you can get a light more output one can able to have. So this is again we have categorized recently, but this paper need to be published. These are the variety of phenanthridine molecules which we have synthesized in our laboratory. And the one which is here located, we can see this is the unipolar material. So we used the external quantum efficiency, we got only 2.8%. And when you have used this one as a host material to hold the iridium complexes, it shows only 5%. That means this component unipolar is not been recognized. This article been published as a part of virtual special issue for the emerging researcher in the physical chemistry domain. So the next one is that, here we have taken the phenanthridine and then connected the triphenylamine in meta position, and here it is in the para position where electronic communication is in the not been arrested, whereas here have a meta position and then you also have changed in the N1 position the substitution. So here what we get is that when you replace the CI color coordinates as we need to move to the whatever the value that has been given by the standard European broadcast unit. So we have when we do this, we got this the CI value is 0.02. In the previous slide you might have seen. Of course, we have synthesized with this component, optimized the geometry and have homolumo calculations, and we are done. So you can see here in the solid, the CI value we got is 0.07, 0.06 and 0.06, which is very much interesting. And PL quantum is also very much pretty good, 60 to 80%. And when we make the device in a blue device, what we found is that one of the device that gives 0.02 Y value. That means it is giving very pure blue color. So by using this, combining this blue with the yellow iridium phosphor, we made the white LED, which is also giving the ideal white light having 0.33 and 0.33 white color, pure white color in the CI color coordinates, and having the external quantum efficiency 12% we got, which is quite good. Of course, we also have this connected, we putting O linkage, we stop this communication between the carbazole and the phenanthridine band, and then we got this external quantum efficiency around 3.8%. So the other molecule that we have synthesized by using the pi bridge fluorine molecule, where one can see that the in a TADF material, the T1 supposed to be very close to S1, but here we can see the T3 is very close to S1. That means when we harvest the energy from the T1 to S1, we call it as cool exciton, and when we harvest from the T3 to S1 or higher energy triplet level, we call it as hot exciton. So that means the hot exciton recombination can be possible in this case, so that one can able to improve the external quantum efficiency. And by using the Salvator chromosome, we could able to sense that it has HLCT phenomena. That means hybridized, localized charge transfer state is existing in this material. Of course, we have the external quantum efficiency is 3%, but the CI value we got is 0.02%. So how to improve this external quantum efficiency more than 5%? As I already mentioned, we need to go for the TADF material. Of course, as I already shown you. So the TADF material, when you wanted to design the blue material, there are two concepts that we need to recognize. One is the gap between S1 and T1 supposed to be less. Then in order to get this S1 T1 gap, the donor acceptor is supposed to be very twisted geometry. That means you should not have a longer conjugation, we should have twisted molecules, so that we can, the steric entrance can able to separate this, and then multi-resonance effect can also have separate this homo-lumo. That means you should not have a complete separation between homo-lumo, but because in order to have the F value, that means oscillator strength, because if you have the oscillator strength, then only you will have good absorption. So once you have good absorption, then only you will get a good emission. So in this sense that we need to compromise, compute between the delta EST value, that means the gap between S1 and T1, as well as you should have the separation between HOMO-LUMO should be there. That means partial overlap HOMO-LUMO also should be considered in order to have the higher quantum efficiency. So what we have taken is that in the simple backbone of keto molecule, so you have a benzophenone. We introduced forcefully 2 methyl group and 1 cyanide group, to assuming that cyanide can induce the HLCT phenomena, and then you can have this 2 methyl group and keto can make a TADF concept. So we have interlocked acceptor core. So we have changed the donor molecule from the carbazole, substituted carbazole with a phenyl ring and triphenylamine, phenothiazine and phenoxazine. So we get this emission varied. So synthesis, we followed this method. I'll change. So this is the material that shows blue color in this. When you put the carbazole and the substituted triacylbutyl group, you get a blue color here. Before doing that, we also done some calculation. We found that this one is the ideal one to get a TADF property. So you can see here the delta S1 T2 value is 0.1 electron volt, whereas here S1 T2 value is 0.03. That means you can also have hot exciton can also come to the T2 to S1 state. So this in toluene, thin film, solid, all of them showing in the bluish slight green color, and salvatochromosome study shows that there is a charge transfer characteristics exist. So lifetime also shows the TADF characteristics. And by using this device structure, we made the OLED structure. So what we found is that in the CBP, presence of CBP, this component shows the external quantum efficiency around 9%, and then the Y value is 0.13. By mixing this with another fluorescent molecule, we get a deep blue hyperfluorescence, where one can see that the external quantum efficiency drastically increased from the 9% is 14%. So the hyperfluorescence, by using our molecule, one can induce more external quantum efficiency in this molecule. Of course, by using this CCDBA and then our molecule, we can fabricate the white LED, which shows the external quantum efficiency we found to be very good, and then it creates a warm white light. So the next one which I am going to talk about, the carbazole. If I have the carbazole with the insertion of one phenyl ring here, diphenylamine and carbazole here, the locking and unlocking system. If you lock this carbon-carbon bond, you get a blue light. If you unlock this carbon-carbon bond, you get a green light. So in this sense that we made this component, what we found is that one of them showing blue color, the other one is showing green color. So the green one is having a 14%, the blue one is having 7% external quantum efficiency. So next one we are going to talk about the butterfly structure, uneven wing, where one have phenothiazine and phenoxazine. So what we found is that both of them is showing phenoxazine and phenothiazine, both of them showing yellow color. Where we end up with that the delta ST value is very, very narrow here, the 0.06 and 0.05 here. So that means 0.015. That means here one can enormously expect that there will be a TADF property. So what will it's supposed to be give that the external quantum efficiency is supposed to be increased drastically. So in this case, when you make this device, what we found this compound shows the almost 18% is the candelas per meter square. The quantum efficiency goes as good as 27, 31% we got with the 5% of dopant. So this is a record breaking efficiency in the case of yellow color. So when you use this as a sensitizer, so we get this rubidin molecule TBB. So you have X percentage of this without any our TADF material. So only rubidium dye which having 1%. You can see that the actional quantum efficiency is 17%. Sorry, 5%. When you have used our phenoxazine and phenothiazine, the actional quantum efficiency increased 20%. So here 18%. That means it acts as a sensitizer for this rubidin dye molecule. So to summarize, we have done phenanthroimidazole based molecule shows blue color having the CI value of 0.05 to 0.02, having the actional quantum efficiency of 5%. And by looking at this structure, by varying the donor ability from carbazole to phenothiazine and phenoxazine, one can able to tune the emission color, and also the actional quantum efficiency drastically increased from 9% to 31%. So I thank most of the work has been done by Dr. Intaka Malam. Currently is the Institute postdoc at IIT Guwahati. I thank SCRB and Inspire DST for the funding. Thank you so much.
Thank you, Dr. Sivakumar. So on time. Two more questions. Two questions from the audience side.
Yeah, please. B3 alloy pi. So that's DP. Yeah. No. We use simple because you wanted to just go whether to go or not. Just simple calculation, optimize the geometry and get the Omaluma gap, because if you get the Omaluma gap, then only we'll know that whether it is going to be a 3 electron volt or 2 electron, which color we are going to predict. So more or less it will have a plus or minus some variation. But in general, before proceed for the synthesis, we always wanted to do whether it's having twisted geometry or regular geometry, so that you can have some idea whether to proceed or not to proceed. Yes. Yes. I have shown in the latter part of my presentation where the carbazole to phenothiazine and phenoxazine, one can able to go from all the way from blue to yellowish orange color. It is possible. Yes. So you need to characterize them structurally. You find that its compound is characterized. Yes, you have to deposit in the, you have the electrodes, right? So you have the structure shows some of the slides I showed you, ITO slash, Yole transporting material slash our emissive material, then electron transporting material, then you have slash another electrode. So these are the combination. You need to put this way to deposit. Certain things we deposit by the vacuum deposition, and our emissive material has been processed in the solution process, spin coating. Yeah, of course. We have some value here. I can show you this one. The lifetime of phenothiazine and phenoxazine, we said, because it goes 31%. So it started degrading 19,844 hours, and this is 10,550 hours. So that's the thing. Degradation is one of the critical thing. One need to monitor if you want to go for the commercial, because you assume that it is going to stay longer time. But the ultimately when you make the device, TV or whatever, then it will start degrading. Then you will not have a yellow color. Only you will end up with a blue color, other colors. Yeah, thank you. I think organizer is seeing me, so I should get on.
We appreciate Dr. Sivakumar for his wonderful presentation. Thank you.
Before calling, I'm coming. Thank you. Thank you so much. Thank you. Sorry, no problem.
So the next speaker is Professor Annadhasan. Is from IICB, Kolkata. So he has completed his BS from Pombugar College and a PhD from IIT Kanpur. Also, he has pursued postdoctoral career in South Korea, Germany, and UK. So currently is working in IACB, Calcutta. So his research interests are crystal engineering towards the functional materials and synthetic molecular and supramolecular receptors for molecular recognition. So I invite Dr. Natarajan to present his work.
Yep. First of all, good morning to everyone. And I sincerely thank the organizer, especially Professor Sivakumar, for invitation and taking all the care. And I also appreciate all the student volunteers who took all the efforts towards this conference. Okay. So one of our major research objectives is to make macro bicyclic organic cage molecules. We have listened and learned from many other speakers earlier, macrocycles, like yesterday, Professor Jayaraman spoke about cyclodextrin, and day before yesterday, Professor Arunachalam spoke about pillararine molecules. So they are like a bangle kind of molecules. Our objective is to make macro bi or tricyclic molecule so that you have a very efficient cavity and it's highly rigid structure, and we can selectively target some specific guest molecules inside. So this is what we had in our design strategy, have some aromatic molecules above and below and put them 3 or 4 linkers so that we can choose the space in between the 2 planes so that we can bind the guest molecules over there. So we had some different guest molecules in our mind. One of them is polycyclic aromatic hydrocarbons. They are kind of highly carcinogenic aromatic molecules. They are simply flat, and even our petroleum combustion emits these kind of aromatic molecules. They are in the atmosphere as well as in the water, where it's very difficult to degrade them. So if we can come up with some simple organic molecule which can bind them inside the cavity, it's easier to trap them and isolate them and sequester them. That is one of the possible approach. Then another option what we had in our hand is, like, can we solubilize them in water, so that if we have a water-soluble organic macrocycle, then we can use it to bind carbohydrates or nucleotides, these kind of biologically relevant guest molecules. And another one is picric acid. Previous speakers also spoke about the picric acid sensing as one of the important objective. Okay. So the inspiration came from Professor Stoddard. He's a Nobel laureate in 2016, and he demonstrated synthesizing these kind of organic cage molecules. And the challenge is that synthesizing is not very easy, and because macro bicyclization is very thermodynamically defying. Okay. So, and what he has done, you have to take a step-by-step approach. First, you take this pyridine molecule, tripyridine molecule, and do the nucleophilic substitution to get a first half, then to put the other half, and you have to use some template. Okay, then the yield is very poor. Then you have to remove the template. The removal of template itself, normally they used to take 7-8 days for continuous extraction to remove the template. Okay, so this is one of the very challenging synthesis. What they have done, they got in very limited yield, and removal of the template is kind of continuous extraction over 7 days kind of thing. So we thought, can we make this kind of molecule in some simple, reliable approach? So what we wondered, so we thought, can we use the click reaction, which is very popular, everybody is aware of click reaction. Can we use this click reaction to make this kind of organic macrocycle? So we took the similar aromatic pen and functionalized with the triazine, functionalized with the triazide, azide, and acetylene moiety. And we performed the click reaction. To our surprise, what we got, very beautiful reaction and very high yield. It's very high yield for this kind of macrocyclization reaction, and no template, and we can readily purify the molecule by simple column chromatographic purification. Just one, there is some polymeric byproduct, and we can simply put it in the silica gel column and run it through, and we can readily get this molecule. Okay. Then we thought, we examined what can we do with this molecule. We choose the polycyclic aromatic hydrocarbons, and we did the NMR titration as well as fluorescence titration, and we also performed the single crystal X-ray diffraction to conclude that this organic cage molecule can readily bind the polycyclic aromatic hydrocarbons inside the cavity. And we measured the affinity by fluorescence titration. When the dye molecules are fluorescent, okay, so once we add this organic cage molecule, and it quenches the emission, from which we can continuously plot and measure the affinity. Then this is triazine based molecule. Then we also made a cage molecule with the benzene in the middle moiety. Then we did the similar reaction, we got this molecule. Then we thought, can we do the N-methylation over here so that it can become cationic, okay? So we did the N-methylation with the trimethyloxonium tetrafluoroborate, and it's a very powerful electrophile. We can also do the reaction with a simple methyl iodide also, okay? Then once we had this molecule, this is organic soluble, then we did the anion exchange with the iodide or BF4 salt into chloride salt. Then it becomes water soluble molecule. Okay, now we have a water-soluble organic cage molecule in our hand. Initially, we wanted to examine whether it can bind carbohydrates inside the cavity. The carbohydrate recognition is very important, challenging task. But when we tried and we couldn't get anything out of our hand, so the molecule doesn't bind the carbohydrate. Then we kept quiet. What we can do with this molecule? Then what we found, this molecule readily binds the pyrene derivative, the hydroxypyrene trisulfonate salt. Okay, that's very important dye molecule in the sensing purpose. So this has the acid base. In a deprotonated medium, it shows the different emission, whereas in the protonated state, it's showing a different emission. So it's a very powerful dye molecule, and people use it for different sensing application. So what we did when we take, and this molecule, although it's fluorescent in water, it has the no emission because the molecule stacks one over other, and the emission is getting completely quenched in the water. So the molecule is not emissive in water. And when we mix this molecule with our host molecule, what we found, the solution becomes emissive, because it's not aggregating in the water. Only one guest molecule goes and binds inside the macrocyclic cage. So the molecule is showing, the system is showing emission in the water. Okay, so then what we did, so this is for the both of them with the benzene clickage and the triazine clickage. Then what we did, once we have the supramolecular complex, then when we add the adenosine triphosphate, ATP, what happens, the ATP has a stronger affinity with the macrocycle, and it goes and replaces the dye molecule. The emission becomes quenched, so that we can sense how much ATP present in the medium using these two molecules. So this kind of what we call indicator displacement assay. Okay. Then this is selective also. It's only selective for the ATP, whereas the other adenosine monophosphate and guanosine phosphate and those kind of other phosphate molecules, they are not going bound inside the cavity. So this is one interesting system what we came up. And then once we did the analysis, then we were asked whether it does the binding only in aqueous medium or buffer medium. Can we do it in a physiologically relevant human serum matrix? Then we examined whether in the bovine serum albumin and human serum albumin, as well as the human blood, and they take the serum out of the thing. We did the analysis, and the molecule shows reasonable sensing of the adenosine triphosphate even in the physiologically relevant biological medium also. Okay. Then next we moved one step further. So this tetraphenylethylene, so I think many of you are aware of it. That is a very beautiful molecule showing the aggregation-induced emission. The molecule is not emissive, but if you take this molecule in THF or respirators kind of solution, you add water and it increases the aggregation and it shows the emission. Okay. Then people were wondering, can we take this tetraphenylethylene and cyclize it so that we can increase the emission even in the dilute state. Okay, so people use different approaches to make a macrocyclization to make this tetraphenylethylene based macrocycles. We thought, can we make this molecule by our hand? So then we took the starting materials, and when we did the synthesis, what we end up seeing, we have two isomers. One is face to face, the other one is opposite to opposite. Then next we did one step further. Can we increase the length? This is the X-ray structures of the two molecules in different conformations. Okay. Then we did one more extra step. Then we put another phenyl ring in the building block. Then we extended the linker size. Then we got the extended clickage over here. Okay, this is the X-ray structure of the molecule. Then we did the emission studies. So to begin with, the molecule is emissive even in the dilute solution. Okay. Then once we in the THF solvent, then once we add the more and more water molecule, the AA phenomenon becomes aggressive, and we could see the very enhanced aggregation-induced emission. Okay, this is also emissive in the solid state as well. Then we thought what we can do. I think picric acid sensing is one of the very popular thing we all come across. Then we also examined the same thing. So then what we found, it has a very good limit of detection. Our previous speaker also told about it. So it has a very good limit of detection for the picric acid with our system. Then we did the DFT studies to find out this is the photo-induced electron transfer between here to there, and so that it shows the beautiful emission sensing. And it's also selective for the trinitrophenol compared to the other nitrophenols. Okay. Then we did the detailed lifetime measurements. We found that it is not static, it is only dynamic quenching. That means the trinitrophenol is not going inside, but it's in the external complex only. Okay. Then I slowly talk about another interesting class of materials. So once we have this, what we call halogen bonded organic primer. So once we have this tetrabromo molecule as the intermediate in our hand, we wondered, can we do something interesting with the thing? Then we did some one step further, and we made a spleen spacer in between the halogen derivative. Okay, it has some specific reason. So then when we mix it with LabCo, what we thought, whether it can form a complex between these two things. This is what we got. So in the X-ray structure, what we see, the halogen and the dapco nitrogen, they are in a very short distance. So this phenomenon, what we call halogen bonding, it's something similar to hydrogen bonding, but with the halogen atom. Okay, the iodine atom, and you have a strong electron density around the iodine, and whereas on the tip you have some small sigma hole. Okay, when there is any non-polar, any molecule with lone pair electrons are coming, and it can stay closer with that thing. Even they stay closer than the sum of the van der Waals steady. This phenomenon, what we call halogen bonding, and it's very powerful non-covalent interaction. And it is complementary to hydrogen bonding. Hydrogen bonding in water medium, water competes with your hydrogen bonding partners. Whereas in the case of halogen bonding, and it works very stronger in the polar medium also. Okay. And since it is DAPCO, what we have, it is kind of extended network what we are going to get. And the idea is that you take both of them and simply grind it and you get a powder material, and you can do the, when you see the powder pattern, it's already crystalline. So, okay. And as well as you just do the recrystallization to collect the X-ray structure, and they are kind of matching with each other. So by simple grinding, you can get a beautiful halogen bonded organic framework in our hand. And this is the X-ray structure of the extended thing. So what we have is kind of a diamondoid kind of network. So if you just put a straight line between the centroid to the other molecule, what we have is like a simple diamond kind of extended diamond kind of structure. And what we have is a huge space, and the space is filled by the similar network. So what we have is kind of tenfold interpenetrated network. And this is the different view of the same crystal structure. And what we have here is a simple narrow pore with a 5 angstrom dimension, and it's not a straight tubular pore, but it's like a corrugated structure. Okay, it's a very narrow, but that also very useful for some reason. Okay, when we did the X-ray structure, what we have is a THF molecule sitting along the channels. Then we can apply heat, and we can remove the THF molecule away from the X-ray structure. Okay, then we could do the single crystal XRD, and we find that no electron density to support that any guest molecule. Then we did different guest molecules, the same THF, and we soak it further, and we could see this THF is getting intruded over the thing. And we did the experiment with a different guest molecule like dioxane or ethyl acetate. We could solve the structure. We could see that the guest molecules are reversibly going inside. We can exchange them. Okay. Then we did the gas adsorption studies. It shows that it's not strongly absorbing any gas molecule because the pore is very narrow and not linear. Whereas the system is very stable in different solvent as well as in different pH. Starting from pH 3 to pH 13, the system is very stable. Okay. So this thing we made us to examine a lot of sensing applications. So what we first did, acid sensing. So we can have the halogen bonded framework, then we put it in the, when we expose it into TFA or hydrochloric acid, the emission is getting completely quenched. But we can reverse the sensing application and by exposing the crystalline materials into base molecules. Okay, so when we expose into base vapor and it is coming back, and we can reversibly do the acid-base sensing. The idea is that once we expose into acid vapor, it gets protonated, and when we go back and it is kind of deprotonated, and we can do the acid sensing reversibly. Then we also did the picric acid sensing, and we disperse the solid material in the bulk solvent, and we can do the sensing of the picric acid. What we have is we still very good limit of reduction compared to the previous KG molecule. So more than making the very laborious synthesis, we can take a simple 1:1 halogen bonded complex, and we can get the picric acid sensing as well. Okay. Then what we did, can we have this molecule to capture the iodine? And previous day, Professor Arangu also spoke about pillar arene molecules. So the iodine is a very important nuclear waste. Okay, and so we have to find a material to capture the nuclear waste iodine. And when there is some nuclear accident and that is getting exposed into sea water and atmosphere, so people are looking for some interesting, important halogen bond iodine capturing material. Normally, currently used material is a zeolite loaded with a silver ion. Okay, and that is not reversible. So you have to spend a lot of money to make the zeolite material and loaded with silver, and which is irreversible capture. Okay, people are wondering, can we have some simple material, readily accessible material, and capture the radioactive iodine? So when we did the experiment with our halogen bonded complex by gravimetric method, we could find that it is grabbing up to 3.2 grams per gram of the material as a reversible to load the iodine. And we also found that it is very stable even after several days. And we did the TGA studies to confirm that how much iodine it is staying over there. Then we also did the halogen iodine capture in organic solvent. You dissolve the iodine in the hexane or cyclohexane kind of solvent. Then we soak them into the material contain. You soak them with the halogen bonded framework powder, and we could find that it is readily absorbing the iodine molecule from the solution. Okay. Then we also did the iodine capture from the aqueous solution also. Okay, so we dissolve the iodine, we cannot dissolve it, so we take the mixture of potassium iodide plus iodine and it slowly release the iodine into the system. And we can follow the UV titre, you can follow the UV to find out whether it is iodine is getting captured from the aqueous solution into the solid material. Okay. So then we can readily release the iodine also. When we soak the material in methanol or ethanol solution, the iodine is coming back into the thing so that we can reversibly capture the iodine from one after other. Okay. Then what we found here is there are plenty of covalent organic framework materials. They can capture more iodine, like a 10 grams per gram, but they are not doing the job in aqueous medium, but only in the gas phase capture. And what we found is that our material, what we have is, it has a very decent iodine capture efficiency in both in gas phase as well as in the aqueous solution. This is one of the rare phenomenon what we found over here. So the take home message is, I spoke about two things. One is we can use the click reaction to make a simple organic macrocycle cage kind of molecule. We can use it for host case recognition. And along the way, we have some synthetic intermediates and we use them as a halogen bond. We did the crystal engineering to make a halogen bonded organic framework materials. Okay. Apart from these two things, we also do some other research work. One is like a coordination driven self-assembly to make a metal organic cage molecule. So we take some simple banana shaped organic molecule with the pyridine on the top and bottom, and we mix it with the palladium ion to get the metal organic cage molecules. We do a lot of host-based chemistry with the thing. Then we also make some simple acyclic molecule to form halogen ion binding and halogen ion transport as well. So we did one for the chloride anion transport and the other one for the other molecule, a beautiful molecule which is binding with arsenate anion inside the thing. So by this, I finished my talk, and these are the few students who did all the work. Mostly I spoke about Suman Maji's work over here, and I thank the funding agency and also thank all the people for patience.
So thank you very much, Dr. Natarajan. So a couple of questions from the audience side are allowed.
Can you say again, please?
What type of molecules or substrate that are typically used as cofacial cages in click reaction?
Yeah, I would say almost you can use anything. So you have to just sit back and design and what exactly you want, what kind of guest molecule you want to bind in our case. So we choose the substrate accordingly with the shape matching. So when we had the planar molecule that has a cavity inside, but when we have a tetraphenyl ethylene that is not planar and you don't have the space inside. So what exactly you want and design accordingly.
Okay, thanks.
Have you noticed any triazoles ring rotation based on the guest?
Yeah, that is interesting thing. So when we had the crystal structure when I was showing, and in some cases they are kind of twofold disorder over there. And without any guest, we could see a simple symmetrical propeller orientation, whereas in the presence of guest, they adopt different orientation, and we could find the motion. Yes, definitely, yes.
For the iodine capture.
Yes.
Selecting for only the iodine, or whether it's a competition between any halogen?
We didn't do the competition experiment like a bromine also very important thing. So, but we didn't do the bromine, but we focused on iodine and we could find that. But when we try as a competition, we don't know what will happen.
Because you are focusing on the radioactive.
Yes.
In the atmosphere,
Halogens also there.
How we compete? Whether any size
In-
effect
in-
or cage effect? Or...
In principle, what we have is the DAPCO, the nitrogen. So that nitrogen, when we did the XPS analysis and all, we could see the iodine is existing as a I3 minus and I5 minus kind of thing. So and there is some short electropositive interaction, electrostatic interaction between the DAPCO nitrogen. So as long as the DAPCO getting reasonably protonated, and it can definitely take the bromide or chloride, I would say it's more the electrostatic interaction favoring the inclusion over there.
So another question is, so what is the interaction? Whether you said like absorption studies, because iodine is a larger in size than chlorine.
Yes.
So based on the cage effect or any other effect, they calculate for it.
Yes, it's the same thing. The iodine is bigger, so ideally it should take the chloride also.
Okay.
So when we did the HCl sensing, and we could see that is sensing the HCl mainly because not only the acid vapors, so definitely the anion vapors also. Anion also should go together inside, and that should taken care of it. That's it.
Fundamental question related to same.
Yes.
So when you doing the iodine absorption, does the iodine react with your cages, or its cages are highly chemically stable with respect to iodine?
But it is reversible. So when you soak it in methanol, it comes out.
Okay.
So it's not forming a very strong covalent bond. But when we did the Raman analysis and XPS analysis, what we found, it's not a neutral iodine, but it's like a I3 minus or I5 minus. So definitely there is some kind of anion formation even in the gas phase, and so that it forms the electrostatic interaction between the I3 minus or I5 minus with the N-dapco nitrogen over there. So it's not simply staying in the space, but there is some chemisoption. It's not physisorption, it's more of a chemisoption over there. But it is reversible. It's not completely strong bond, but it's a reversible. Even in put it in methanol, it comes out.
Reversible with respect to any stimuli or just
Solvent, simple solvent, competitive solvent. So in water, THF or DMF, iodine is going inside. Whereas fortunately for alcoholic solvent, and it is reversibly bringing it back. That's what we found.
So thank you very much, doctor. So we can appreciate this one. So the next speaker is Dr. Kishore Natte. So he has completed his BS and MS from Kakatiya University, Warangal, and then he's completed his PhD in Technical University of Berlin, Germany. So after completion of his postdoctoral stint, he has joined in as a senior scientist at CSIR Indian Institute of Petroleum, Dehradun. And then currently he is working as an assistant professor, Department of Chemistry, IIT Hyderabad. So I invite Dr. Kishore to present his work.
After the tea break.
Thank you, Professor, for the nice introduction. And firstly, I want to thank Professor Sivakumar for giving this fantastic opportunity. I also congratulate the organizers for this very nice conference. Really, I'm first time in Madurai, and I really enjoyed my time here. And really blessed to be in Madurai because very powerful temple is here. So, okay. So today I will talk about catalytic transfer hydrogenation in organic synthesis. So I would say that, particularly that how the hydrogen is transferred and it will reduce the unsaturated compounds. Okay, so we will see some nice examples. This is our research lab interest where we work on organofluorine chemistry, CO2 and plastic upcycling, green chemistry and transfer hydrogenation, because I have different kind of backgrounds. I did my MSc in organic chemistry. PhD is the blend of organic and some physical chemistry, and my first postdoc is from catalysis and organic synthesis, and my last postdoc is having some industrial touch. So all this interdisciplinary experience called me to shape these research topics, and today I will talk more about this transfer hydrogenation and in line of some principles with the green chemistry. So we have recently published some nice articles in this transfer hydrogenation. So I want to focus more on this transfer hydrogenation. So before going to the transfer hydrogenation, we should know what is hydrogenation. Hydrogenation is one of the most powerful reaction, and it's a main pillar in chemical synthesis because it is widely used for the preparation of fine chemicals, pharmaceuticals, agrochemicals, polymers. So it is used in various reactions, and it also assessed that 25% of chemical reactions involve at least one transfer hydrogenation step. So by this, we understand that this transfer hydrogenation plays a crucial role in chemical synthesis. And what is transfer hydrogenations? It is also a hydrogenation, but in hydrogenation reaction, in hydrogenation reactions, we use mainly molecular hydrogen and in the presence of a catalyst, whereas in transfer hydrogenation, we use hydrogen donor. And then you may ask yourself, already there is hydrogenation, and why we have to use transfer hydrogenation? In transfer hydrogenation, the in situ hydrogen will be liberated and it is more active. And I would not say drawbacks in hydrogenation, but in hydrogenation, we have to use flammable hydrogen gas. That's why you see the gas cylinder will be in red color. So it is very, difficult to perform. And also sometimes this molecular hydrogen is not that much active, so it will not reduce the unsaturated compounds like it do with transfer hydrogenation. And transfer hydrogenation does not, require some specialized equipments. You don't require very, autoclaves to perform this reaction. You can do it in a very simple glassware, but there are also some safety tips which I want to, let you know. When the research comes, I will, when my research comes, then I will explain you some tips to be aware of it. So there are now, in transfer hydrogenation, there are two types of pathways, okay? So one is the direct transfer pathway and the other one is indirect transfer pathway. So what happens in this direct transfer pathway? In direct transfer pathway, the hydrogen transfers from donor to acceptor in the presence of a AL3 complex, AL3 or lanthanum 3 complexes. This is a very classical reaction. We all studied in, it's a textbook reaction, Meerwein-Pondorf-Verley reduction. So where the isopropanol is used as a hydrogen source. And in indirect transfer pathway, a metal dihydride ion is formed, which will, in the presence of a suitable catalyst, one hydride or two hydrides will transfer from donor to the acceptor molecule. So this is a very, hypothetical mechanism of this transfer hydrogenation. But still, sometimes the mechanisms are very unclear. So a lot of experiments and some studies, DFT studies have to be done to exactly know what is happening in the reaction. So now, the first reaction we have tried is the hydrogenation of aromatic and heteroarenes. So by doing this reaction, we will get direct access to the saturated carbo and heterocycle. So for example, if you take benzene or if you take a pyridine, you get a piperidine, something like that. So these are all readily available. A lot of aromatic compounds, if you go to Sigma Reach or any, you find a lot of compounds are available, We can convert this into the counter aliphatic compounds by using this hydrogenation chemistry. This looks very, very simple, right? But it's not so when you do these reactions in the lab. It's very difficult. Also, these feedstocks are very abundant. This can be accessed from fossil-based and also nowadays, lignocellulosic biomass, plastic waste. So a lot of, methodologies are there to access aromatic compounds. So, but aliphatic compounds, there are very few methodologies. The methodologies are very less. So there are hardly like one or two methodologies available to make this kind of chemistry. For example, Diels-Alder reaction or hydrogenation reaction. We'll see what are these. And by doing this chemistry, we get a very nice access to this, aliphatic compounds, and it increased complexity, and also this high fractional sp3 correlates to clinical success. And the challenge is that difficult to control the stereochemistry here. And then you can see here, for example, just now I'm saying if you take pyridine, you get this kind of compound, and all these derivatives you get, and these are all 3D pharmacophores. And if you see some drug molecules, you always find this. So where we get these molecules? So after preparing these molecules, we have to stitch them very nicely, or we have to, couple them to get a very nice, a very big compound. So you can see here this kind of fragment is very nicely appeared here. So this is present in one of the pharmaceutical compound, nattiglinide, and also the thiagabine. And moreover, this chemistry is also very much useful to store hydrogen. It is useful in liquid organic hydrogen carriers. So one of the best technology to store the hydrogen. I'm not talking about this one, just it's only an application today. So you see, for example, I mentioned here how difficult it is to get access to this pyridine molecule. You can see. For example, if you take three methodologies, one is hydrogenation, one is intramolecular cyclization, and intermolecular cyclization. Among these three approaches, this approach is little bit straightforward and easy, or very practical to do it. Because here it looks very complicated. You get a lot of byproducts, and you need a lot of energy-intensive process. So that's why we prefer to do hydrogenation. And then these are some benchmarking reports. This chemistry was developed by, not developed, but, it's like a lot of excellent results were produced by the group of Frank Glorious and Paul Chiric and Professor Vellore and Kobayashi. So there are a lot of groups from Europe, China, and US. They are working on this topic to generate some nice results from 3D molecules from 2D starting materials. So we have also, did some efforts, and, we also published few papers on this field. in some various journals. But here we used a biomass-derived catalyst. So this carbon is derived from pine needles, so which is consists of some nitrogen. So I will not talk about this methodology, but I will talk about some transfer hydrogenation by using aminoborane. So why we have to use aminoborane? Aminoborane is a promising material for chemical hydrogen storage with 19.6 weight% gravimetric hydrogen capacity. You can see here there is a diagram, so where it has a lot of aminoborane has very good hydrogen release gravimetric capacity. So for example, if you take 1 kg of aminoborane, so almost 190 gram of hydrogen is can be released from that. So it really made me attractive. And also in the last 3 to 5 years, a lot of interesting methodologies were appeared in literature by using this aminoborane as a hydrogen source. First we tried by using like these molecules. Already there are some reports. You see here, they took pyridine and they took this this kind of heterocyclic compounds, acridine, and like very large compounds, and they use aminoborane in the presence of palladium. All these metals are homogeneous and few are heterogeneous, but all these catalysts have to be prepared. You need either glow box or you need ligands, organic ligands, or sophisticated organic ligands, which are sometimes expensive to access. So we thought of developing a methodology where this catalyst is readily available and also the hydrogen source is readily available. So we have tried different types of 3-member ring, 5-member ring, and also like cyclic benzocyclic compounds and many things. So we got this products in very good to nice yields. We can see here. So we have, this is the optimization. So we have done a lot of hit and trials, almost like 150 reactions we have done, which I am not showing, but only these are some important optimization experiments where the reaction works very nicely with 5 equivalent of aminoborane and 5 mole% of ruthenium chloride. Here, any organic ligand, we don't need to use any organic ligand, just only use this ruthenium chloride. Hexahydrate, or it's a hydrate version of this ruthenium chloride in the presence of IPA and 120 degrees and 24 hours. So you get this tetrahydroquinoline in 91% yield. And then we started substrate scope. So a lot of functional groups have been tolerated. For example, if methyl group is present on various positions and it got hydrogenated, particularly the ring which is present on aromatic compound, it is hydrogenated and give very nice yields. And some interesting functional groups like bromine, fluorine, and ester also hydrogenated well. Even on 1 gram scale also it is working very nicely. And even from quinaxylene also we can access this kind of compounds in very good yields. Most importantly, pyridines. Actually these pyridines are very, very difficult. It's a very challenging. By using this kind of reaction conditions and getting these products is very, very challenging. Fortunately, these reaction conditions helped very well and we got access to these compounds in very nice yields. And then these derivatives and followed by some indoles also worked well, and oxygen containing heterocycles, you can see these can be accessed from lignocellulosic biomass like C5 based biomass, and also benzofurans, and complete hydrogenation may also be it can be done by adopting or by tuning some reaction conditions, for example increasing ruthenium catalyst or by increasing some amount of aminoborane, so we can access this complete hydrogenation molecules. And also this very nice pyrrolidine also worked well. Of course, some products we were not able to generate. For example, this is a quinine, it's an anti-malarial drug. So here we have an opportunity to reduce this ring, and there is also a double bond here. But however, unfortunately, this double bond is reducing, but we did not obtain any, this ring hydrogenated product. And also this defluorination happened in many cases. This is really, till today, one of the challenging reaction where up to now only rhodium is used as a catalyst. We tried with ruthenium, but somehow, we got defluorination, and it is very difficult to deal this kind of compounds. However, we are still trying with some other methodologies. In future, definitely we will, get some good results. And then we applied this methodology for making some, pharmaceutical compounds. You can see here, this is the commercially available, and we adapted our reaction conditions, our optimized reaction conditions here, 5 equivalent of aminoborane and 5 mole% of ruthenium chloride. We got this compound where the ring is selectively hydrogenated. Only one ring is hydrogenated, and this keto group is as it is, and also this benzene ring is also, not reacted well. However, the yield is pretty low, or it's a moderate yield, but still we able to get only this much, because this is a very challenging molecule. And once you do benzylation, it will give donepezil, which is used to treat Alzheimer's disease. And the other one is the flumethrin, where fluorine is present on aromatic ring. Don't get confused here. The fluorine is present on aromatic group, so that's why it is undergoing defluorination. But here it is present on aromatic group, but not on hetero ring. It is present on non-hetero ring, so that's why it is it is not undergoing defluorination. So still it is hypothetically we are also examining what is exactly happening, and then we able to synthesize this tubulin polymerization inhibitor, which is having a lot of applications in medicinal chemistry. And then this is a very a simple mechanism where aminoboron undergo complexation and reacts with this quinoline and gives this kind of complex, and again it reacts with aminoboron and finally generates this hydrogenated tetrahydroquinoline, which is our desired product. We have done a lot of control experiments. Due to time limitation, I'm not showing here. So if anyone interested, they can access to our paper and get more information. And then we focused on hydrogenation of nitro compounds. This is a very simple reaction. If you look into the textbook, or many people say that nitro reduction is a very simple reaction, but it is not exactly what is appeared in the textbook. When you go to the lab, when you do the reaction, you will understand. You submit for GC mass or GC analysis, you will see at least 4 to 5 byproducts. Controlling this reaction, like getting a desired product in good yield is not easy. Because anilines and their derivatives are having a plethora of applications in various fields, because without these anilines, we cannot, complete our day. A lot of applications are there, starting from, this, spandex fibers to pharmaceutical drugs, rubber products. So a lot of applications are there for using this kind of anilines. So here we have used 4-chloronitrobenzene. So we use this model reaction particularly to check the chemoselectivity, to know whether this chlorine is undergoing dechlorination or not. So we use this substrate and treated with 3 equivalents of aminoboron and nickel chloride hexahydrate in 2,5 mole% and DPPE as a ligand. So we tried a lot of ligands: monodentate, bidentate, tridentate, nitrogen ligands. And we also tried some sulfur ligands. A lot of ligands we have tried, but only interestingly it worked very nicely with DPPE and got a very good yield with in 93%. And there is no dehalogenation. You see, it's 0%. It's completely tolerating this chloro group, which is very, very important. And if you look into the substrate scope, lot of halogens are tolerated. This is really one of the interesting aspects with the nickel catalyst. Normally, like when you do this kind of chemistry and use molecular hydrogen, it will undergo dehalogenation. Done? 2 minutes, okay. So some pharmaceuticals are also, synthesized, and if you, these are some pharmaceutical intermediates, and then some end-using pharmaceuticals like procaine, butamben, and benzocaine also very nicely synthesized in very good yields. And then we have done some mechanism. You see, this is a direct route and condensation route. After doing some control experiments, we came to know that this reaction is a direct pathway based on control experiments. We find it out. And then methanol can also be used as a transfer hydrogenation. So these are some nice fine chemicals and pharmaceuticals which are synthesized. And then, we also done some gram scale reaction, assessed their green chemistry matrix, which is very important to know where the reaction stands, whether it is sustainable or not. We can apply some nice green chemistry principles for any type of reaction and do this kind of calculations. And then we have done some platinum catalyst by using methanol. This also worked well with different types of unsaturated compounds, and we got these yields in very good amounts. And this is another green chemistry calculations which are very nicely appeared. And then I would like to thank my students and SRG, which I got it from SERB. Most of the work has been done from SRG and my institute grant. So thanks to the funders and my students and audience for giving me this opportunity. And also I would like to thank Professor Shiva once again for giving me this fantastic opportunity. And also my colleagues are here. I would also like to thank them. And thanks everyone. Thank you very much.
So due to shortage of time, only one question from the student side. Only one.
One of your projects, not a question about this project, one of your projects, upscaling of the plastics. So I want 4 important questions. Will be a savior from my project.
Yeah, sure.
What are the plastics that you used? how do you characterize the lower hydrocarbons if there is no GC in my university? How do you find out the solubility of check of plastics post reaction in the pressure reactor? On upscaling of polyethylene, what are the gases that you used in the pressure reactor? These are the questions.
These are all very big questions. I cannot answer in 1 minute.
Okay, at
Because
least-
it's a very, let me finish, because it's a very plastic, it looks very simple, but it's not easy. You will get a lot of byproducts and you need a very nice characterization techniques. So I'm just 1 year or 2 years old for this topic because previously I worked in IIP Dehradun where, you know, they used to synthesize, they used to produce fuel from polyethylene, you know, lots of municipal waste polyethylene is there.
Catalysis.
Yeah. So a lot of catalysts are there, and for example, you know, it depends. For example, if you want benzoic acid, you have to use you know, ester containing polyether, and if you want some amine containing compounds, you have to use polyurethane. So it's, you know, varies from plastic to plastic, but one of the main challenge in this chemistry is the characterization. You know, as you said, gases and, you know, byproducts. It's not easy, and you need a very nice catalytic system where you have to synthesize a heterogeneous catalyst, or you have to design a very nice homogeneous catalyst. It can be done under photo also. So it's a, you know, like it's a mystery, you know, like how the bonds are breaking. Yeah, it's not easy to, you know, tell you in one word because I am not an expert in plastic. Just I started this chemistry, and I'm just only 1 or 1.5 year old to this chemistry.
At least I need the solubility check, sir.
Solubility check
very
is also
difficult.
because it depends on the molecular weight. Because if you are taking low molecular weight, it is easily soluble in some, you know, for example, if you take polyterephthalate, if you take low molecular weight, PET, you know, it will be soluble, but, you know, in acetonitrile or something, if you take high molecular weight, like for example, like 5,000 or 10,000 molecular weight, it's very difficult. Even I also face a similar kind of problems like you. Still, we are, you know, working on it. You have to sonicate, you have to, you know, apply little bit heat, you know, you have to do this some kind of, you know, intelligence techniques you have to apply. But I think in this plastic chemistry, two are the challenges. One is solubility and the other one is the characterization. If you solve this problem, then, you know, the rest is very easy. You know, you will get a nice publication or nice technology out of it.
Thank you so much.
So thank you very much. If you can ask me.
Thank you,
after
Dr.
the question.
Kishore.
Thank you, sir.
So, if there is any clarification doubts, you can discuss with Dr. Kishore in the tea time. So, it's a small moment. Thanks.
Sorry, I thought it is 20 minutes, so I went.
So, the last lecture before tea is by Dr. Annadhasan. So, he has completed his PhD from University of Hyderabad. So, later he moved to ISER, after his postdoctoral career, he has moved to ISER Kolkata as a DST inspired faculty in the year 2022. So later, in the year 2023, he has joined as an assistant professor in the Department of Chemistry, IIT Hyderabad. So currently, he is working in the field of Mechano-Photonics, smart materials, sensors, and optoelectronic materials. I invite Dr. Annadhasan to deliver his lecture.
So, thank you for the nice introduction. I thank the organizing committee, Professor Sivakumar and Suresh, for giving me the opportunity. So, actually, I started this field actually in 2018, I started this Mechano-Photonics. I'll tell you what is like Mechano-Photonics. So, I just deal with the single crystals and polymer resonators, okay? So, single crystals, we cannot bend just like that, okay? Most of the crystals are prone to break. So, I work on single crystals where we can bend it and then we can make it shapes, whatever shapes we want, okay? Yep. So, our laboratory is like Smart Materials and Nanophotonics Laboratory. So, before I go to my topic, just I'll show you IIT Hyderabad how it looks. And then these are the main three buildings, and then our building is like recently it came 1 year back. And then resonators, I'll talk about mostly the basics of resonator. What is a resonator, how it acts. So, if you see this kind of play, we might have done like during like young age, right? So, what is happening? See, this fellow may be like just giving a small word, but it will resonate and then it will come to here, and this guy hears the loud sound. It resonates. It is acoustic wave, it resonates. And then the same thing, like when you do the music frequency, when you change the patterns, everything changes. So, similarly, when you change the wavelength, everything changes in optical waveguides and other things, okay? So here you see this is like decorating material, and then we give some light, and then the output is coming. If you see the end, there is a bright light. This is what the waveguide is happening. The resonating property, it happens and then it comes out. It can happen also like in the laser. Okay, if you characterize it properly, we can see the lasing property. So where it is useful? So now whatever all the gadgets we are using based on the photonic circuits, and then it has the signal encryption. Okay, so we can use these kind of waveguides and everything in the signal encryption. So the optical components is mainly based on optical waveguides and resonators. There are two types of resonators. One is like Fabry-Perot and whispering gallery modes. And if you see the characteristic feature, it should have a high refractive index compared to the surrounding medium. Then only it can, a total inter-reflection can happen. Okay, it can act as a reflective mirrors also. Smooth surface should be there. If there is any crack or something, then the signals will leak out. Okay, then you will not get the signals properly. And then in the Fabry-Perot modes, we have the two mirrors. Like one is like completely 100% mirror like blocked, and then one is like 90%. Some 10% light will be leaked out. Okay, and then we have allowed and disallowed. And then in the case of most of the lasers uses this Fabry-Perot modes types. And then the whispering gallery modes, it's like a resonating, just it will resonate. And then if you see normal fluorescence, the band is like broad, but when it's acting as a resonator, we'll have optical modes. You will not see that easily when you do normal fluorescence spectroscopy, but you have to go for the high resolution microscope, and then you will see the optical modes. This can be like, this is like a preliminary result where you can generate lasers if you tune it properly. So this image shows that how the total reflection is happening in the microcrystal. Okay. Then in the case of micro-resonator whispering gallery mode, this is resonating. Once you give somewhere the light, it resonates. This is a silicon bead where it's showing the resonating property. And then photonic molecular, I started the field like using microspheres. Okay, the photonic molecular reaction, I'll tell you why the title is photonic molecular reaction. So I have moved this microsphere to here by using micromanipulation technique using AFM tip, like under microscope, AFM tip. You know that the tip size is like very small. And then the manipulation is very tricky. You have to be very careful when you handle the micro tip also. So I have just brought it together and then just having a connection. So when I connect it, the pattern of microscopy and the spectroscopy signatures changes everything. Okay, so you can see here when I excite here, I can see the signal here also. And this is like photonic molecular reaction. This is two particles are almost like same size, but I have removed one of them and then I changed the spectral pattern. I'll just show you the animation, like how I had done it. Okay, this is simple, like each particles will be characterized by microscopic technique, and then I have to see also like how it like the patterns looks. Okay, now you will see the two like pairs of peaks will be there. One is like transverse electric and transverse magnetic, and then once I combine it, once I do the manipulation technique, and then it's like very difficult actually to do it because there is a possibility that microsphere also can get attached to the AFM tape. So you have to be very careful when you do it. And then you see the like once it is like combined and when we collect the signals, one is like suppressed. There are two pairs of peaks, but one is suppressed. That is like polarization is happening. It also depends on the angle it attached to the other microsphere. Okay. So the next one is like I'm going to remove one of the particle. Okay, the A particle will be removed by AFM manipulation, and the C particle will be like attached. So this is like a resonator based this one, and then the spectral patterns, everything changes. So I made different, this one's a single particle to then 3 and then crow type resonators, and then ring and other hexagonal things also added. So why it is like so important? If you see, most of the gadgets, whatever you use, mostly it is like of photonic chips, and then it uses optical waveguides and resonators. So resonators are important, and then in electrical, this ones, if you see, most of them are, it has its own function. But when the photonic integrated circuit is there, and then single component will be there, but it will act as multiple functions it will give you. Okay. Most of the photonic integrated circuit uses silicon. It has high refractive index. Because of that, the light will be confined. Okay, it will not go out at all because it has the refractive index of almost like 3.5 to 4.2. Okay. But the problem is like it can act as only passive wave. Passive waveguide means whatever input wavelength you are giving, the same wavelength will come out. So this is a drawback, and then it's highly rigid and non-reconfigurable. Once it is fixed, the circuit was made, we cannot reconfigure it. Okay. So, but is there any alternative? We can use organic resistors. Why it is like? Because it is lightweight, and then we can tune the wavelength. That's a main advantage, okay? And then we can prepare it in the laboratory. We don't need any expensive techniques to reconfigure the crystals. So now whatever all the gadgets are made up of flexible crystal, flexible technology, right? You need a watch or any display you want, everything is based on flexible things. Why can't we use this flexible crystals? So this is the first flexible crystal based photonic circuit made in our laboratory for the first time in 2020. So these are some of the techniques I had used using AFM tip. You see, like there is a bending, cutting, lifting, and transferring. So you should know, like how, you should be expertise. Then only you can do this one actually. Then what is the use of these techniques? We can take and then we can make whatever circuit you want. That's the advantage of this one. Okay. So this is like you can see this is straight crystal and then I just bent it almost like 45-degree angle. Okay. And then if you see the close by, there is no crack or any damage. That's why you should be expertised. Then you can do it, okay? And then if you see the straight waveguide, like it's like generating the fluorescence and then it's like sending it to the other end. So this is called waveguide, electronically excited and then generated fluorescence is transduced, okay? You can see the signals like once the length is different, the signal intensity also goes down. So like same is evaluated by when I bent and then the optical loss were also calculated, both are almost like same, okay? So if you see this video, this crystal is actually elastic crystal. When it is on the substrate, it shows the plastic property, like it just stands, okay? But when I release it fast, it will come back to its original position, okay? You see here, it comes back to its original position. This clearly shows that the crystal is elastic, but behaves like a plastic one, okay? But the other also, it's like it's a self-grown, like self-assembled crystals, and then I cut here and then I try to bend it, okay? It will show you that it also behaves like a plastic. This is also elastic crystal actually, okay? There is an adhesive force between the crystal and the substrate, okay? The adhesive force is like higher than the force which is needed to bring it back to its original position. So we named it as a pseudoplastic crystals, okay? This is the first time we like reported the pseudoplastic crystal, no one else reported. And then what is the conditions whether the crystal should be like flexible? So weak interactions like hydrogen bonding, halogen interactions, pi-pi interactions, and we should have buffer regions to store the energy, whatever external energy you are giving, it should dissipate it, okay? And slip plane also important in the case of plastic crystals. This is elastic crystal and the plastic crystals are also there. So this is the molecule we used for the bending, that which video I have shown, okay? And then if you see, I have done this, I don't want to go for this crystal pattern, okay, I'll just show you. This is this is a buffer region where the whatever external energy you are giving, it will be stored and then just it will be released. This is like a herringbone crystal structure. Once it is like the pressure you are giving, it will come like this, okay? And then the energy will be stored in between the buffer region. And then this is a single crystal, and then just bent it and then measured the optical vibrating property. But here you see, wherever I excite it, the generated fluorescence is completely different. But the output, you see, there is completely different output. That's like here almost like cyan, blue-green, and then the output is like green. So we can modulate it, and then it act as an optical gate, okay, logic gates. So this is the first optical circuit I have made it, and then you can see that it is like straight and then bent it. When I excite it at the middle, we can see 4 output signals. But in the case of the circuit, when I excite at the one end, we can generate like outputs only 2, okay. So the reverse, the light cannot go, okay. But it is possible once you bend the crystal like in 180 degree, okay. So this is the Mechano-Photonics. We coined the name like Mechano-Photonics, and then we have generated different kinds of structures using the technique Mechano manipulation, okay. And you see this is a 2-directional coupler, and then we can make also a ring, because if it is a highly strained one, and then different kinds of circuits. One is active, one is passive. Passive means like whatever input light you are giving, the same it will come out. Active means like generated fluorescence will come out, okay. And can we reshape the crystals using light? This is possible. So I'll just show you some example. This is like 1-dimensional crystal, and then I had made it to 2-dimensional as well as 3-dimensional crystals, okay. It acts as a waveguides, active as well as passive based on your wavelength, okay. I'll show you here, this is the molecule I have prepared, and then you see the crystal structures. And this one is like important, the pi-pi interaction is very important here. Actually, if you see the distance, it's like 4.8. So usually we used to have 3.7, right, 3.7 to 4 maximum, okay. But here it's like 4.8. This weak interaction is like very important for us to make like the flexible crystal. Okay. And then if you see the optical wavegates routine, like a distance dependence optical wavegates I have done, and then the signals are collected at the end. If I excite here, then I can collect the signals, and then I'll follow the same end. So when I was exciting with a laser, 488 laser, and then I saw it's a straight crystal. When I just exciting and then trying to collect, there is a bend. We observed it. So it's like I thought that maybe the laser power may be high, it's like melting it and then something it's doing. So, but when I continued the reaction, like collecting the spectra, I just saw that step by step it's like melting and then just going zigzag like that. Okay. So to do that, what is happening, I have done Raman spectroscopy and then to check whether the Raman and the fluorescence spectroscopy imaging. Okay. Wherever there is a melt, you see that there is not much signal. This tells us that it converts to some other phase. And in a Raman, we identified that that is like something dimer or isomerization is happening. Okay. And then when I went for the TEM analysis, wherever the laser is exposed, it shows amorphous phase. But the crystalline phase, it's like wherever it's not exposed, it shows crystalline. Okay. So we try to identify that whether it is a dimer or not. In order to get dimerized, it should have a 3.7 pi like distance. So okay, but ours is like 4.8. So there is no possibility of getting dimerized. Okay, then there is only one possibility, that easy isomerization. Then we confirmed with Raman spectroscopy experimentally as well as theoretically. Okay, and this is like experimental and theoretical before and after melting. And this is a straight crystal. You can see the step-by-step bending of the crystals, like zigzag. Okay, it's not just a simple. It is almost like 300 microns, like length. Okay, so you can see this is a straight crystal. Its morphology, and then you can see in the FSM how it looks. So this is a kink wherever I exposed to laser. You can see that there is a melt. There is a crystalline and melt. So two heterostructures we can make it in a single crystal. So this is the closest view. You can see that there is a bleaching also, it is happening. There the intensity is going down. In the crystalline area, the intensity is very high. Okay. So this is a naturally bent crystal. You can see the cracks. Okay. But in the case of laser-induced bending, you see that there is a melt, and then it's like in particular angle, just almost like 45 degree. It's going out. Okay. When we increase the laser power, it's just completely wipes out, and then it's like cutting out everything. Okay. And then I made it, that is two-dimensional, one-dimensional to two-dimensional. But here you can see that one-dimensional to three-dimensional. So in order to do this one, I have to lift the crystal in AFM tip, manipulate it, and then just bring it in the air. So when you bring it in the air, there is a more possibility that it can bend in any direction. Okay. So here, if you see, the first cut it just made it, and then after that it just bends in different direction. But the output is like we can see in different end. You can see the output here. So I had made it. This is the like different steps, almost like 12, 13 kinks I have done exposure, and then you can see this is a three-dimensional optical waveguide. It was published in Anglicam. Okay, and where it can be used, that's what it matters. Whatever we do, where it can be used. Now, whatever the photonic integrated circuit it is having, like we can use it in Intel. Now it's using silicon-based this one. Okay, but if I told the drawback of silicon, it can act as a only passive waveguide. But if you want to make it multi-wavelength active, then you should use organic crystal also. Integrate organic crystal as well as the silicon-based. Okay. Then whatever laser surgery, whatever you are doing is like the size will be like, spot size will be in millimeter. But in order to use it, I am creating a micro laser where it can be used. Okay. Then operations can be done with micro lasers. You don't have to see the spot actually. Just in micron science, you will not have any damage at all. Okay. Yes, I thank my postdoctoral mentor, Professor R. Chandrasekhar from University of Hyderabad, who gave me the platform to perform all the experiments. Okay, and then all collaborators, and then the fundings from DSC Inspire faculty, and then IIT Hyderabad for seed grant, and then SIR for the funding. And then if anyone is interested in working in my lab, you can come around and then just check my website, and then you can contact. And then shortly there will be a DST SIR project-based project fellow JRF position is available. You can just contact me. And thank you, one and all.
Only one question is from audience side. Due to time, shortage of time. Yes.
Sir, are there any emerging technologies that combine electronic and photonic functionalities?
Now, most of the technology, now whatever gadget you are using is electronic and photonic only. Okay. Now, everything, whatever gadget you are using is like electronic and photonic. So, we wanted to convert completely to photonic. If the light is there, then we can use the device, anything. Okay. That's what our aim is. We don't need any electricity. We can just use the photonic, this one part.
Okay, sir.
Yes.
Okay. Thank you, Dr.
Yes.
Annadhasan. A small moment of within time.
Thank you, Professor Kannadasan, for wonderful chair. Actually, the first session, today, the excellent talks, outstanding. Thank you for all the speakers. Thank you very much. We'll meet after the tea break. How many? 10 minutes? Thank you. 10 minutes. Yeah.
Let us dive into the session 10. The session chair is Dr. R.T.S. Muthulakshmi, Azim Premji, University, Bangalore. Over to you, ma'am.
Thank you. Hi, everyone. I'm going to introduce, my own teacher, not only for me, including your, teacher for your Professor Shiva. If you have, heard most of the presentation, at least, many of the presenters here were actually being taught by our professor, our HSP Rao Garu. He did his PhD from IISc Bangalore, and I am going to repeat the same quote, mentioned by his own junior, Professor Kaliyappan from IIT Bombay. So he was saying that, oh, you are HSP student. I am sure you are very good at, organic chemistry. He is such a wonderful teacher. So this is how, our HSP sir was to us. Right now, actually, is director, scientific advisor to TADF Pharma Hyderabad. He is also actually, he holds lot many, feathers to his cap of being such a wonderful teacher. He has actually, he's an editorial member of, Journal of, what is this journal actually? He was editorial member for, other journals. It's not at all, audible. Yeah, I mean, visible, sorry.
Journal of Chemical Sciences.
Yeah, journal. He was a member of Journal of Chemical Sciences, but he is in the Journal of Heterocyclic Chemistry, and then Archivoc and International Journal of Organic Chemistry. He was also an executive committee member of NOAC and then CRSA as well. He has guided so many students, and he holds. He published more than 150. Valuable or most, important papers, and I would, invite sir. Thank you, sir.
Thank you, Ma. Thank you, thank you.
Nothing. Mike is here.
Mike is here. Next previous laser. Okay. City. Good afternoon. Good afternoon to all of you. Hello. Wake up, because you had tea, therefore you should be energetic. Listen to a 20-year-old guy 50 years back. So, I know that you really heard lots of good lectures. I could see my very good friend Ramana here. He gives a superlative talks. And Subbu is here. He gives a talk which could go above your head, to some extent. And then Nityanandan is here. So they're all good students of mine. And, well, I'm very, very happy to be here in Madurai Kamaraj University. Cutting things short, presently I'm in the industry. Although I can give an academic talk thanks to my recent publications that appeared in journals, but I chose to talk to you something a little bit different. That is the alternate solvents that one can use while conducting reactions. This talk is directed towards backbenchers, not the front benchers. They can go to sleep, absolutely. There is no problem. So, and then, and if there is a take-home message here, the take-home message is that you might look for solvents other than what you normally use in your organic reactions. So that's the take-home message. I presently work for a company called TADF Pharma as a scientific advisor. I tell myself, till very recently as an academic, my profession demanded that I generate knowledge. And now my profession demands that convert that knowledge to money. So obviously both are important. And how to convert your knowledge to money is a challenge, absolutely. About which I'll talk to you at the very end of this talk if I have time. Okay. So I took this particular slide to many of the front benchers, essentially to tell you that there is an overlap between academia and industry. That overlap should be explored as much as possible. I took this figure from Accounts of Chemical Research written by what is popularly called as Sultan of Synthesis, Phil Barron, from Scripps. So Phil Barron comes out with this figure which tells about that industry is profit-driven, intellectual property-driven, and projects for bettering the mankind. So if that is not there, they will not work on them. On the other hand, academia, all of you know that it is driven by knowledge generation and mentoring students. And the pursuit of basic knowledge is what is an academic world knows. But there is an overlap area, and that overlap area is science. And TADF in Estonian language means science. So it's a company is science driven. And that's what I thought I will tell you about. There's an opportunity for a symbiosis between academia and industry, which is explored very much less in our country because of various reasons about which we'll maybe some other time. But then one should explore the possibility of bridging this gap of between the academia and industry as much as possible by our individual efforts, and then things may be different. Okay, and I'm sure this madam who comes from Atul Premji University will tell you that this kind of symbiosis is absolutely important and in promoting science in general. So in that context, we can think of introducing some of these new methods of doing chemistry, and then in the possibility of exploring profitable ventures using new methods. So that's my idea of taking today's talk. Of course, you possibly know this. The solvents as such, as a way of doing things generated nearly 300 years back, wherein among the first people I took from literature that a Dutch medical doctor, chemist has described that solvent is a very, very important, obviously we all know that, for conducting transformations, organic transformations. So hardly there are any reactions which we can say there are solvents. But then it's both a boon and a bane. Because without solvents we can't conduct reactions, many of them at least. And bane, because what do we do with those after doing those reactions? Many of you know that they go to sink in the laboratories, and a sink to earth, and earth to pollution. So this is something which we all know. If not, incinerate them, that means burn them, and then again goes to air and pollution, and pollution, and pollution. And if this happens to be at least 50 times more than the compound that you want, then this is a serious problem. Therefore, generally public, if you go outside, I used to tell this, if you go to outside and tell to a, say, bus conductor, or to a auto driver, or to a rickshaw puller, that what do? I do chemistry. And if that person has a knowledge, a little bit knowledge, they'll say, you're going to pollute us or what? Then you say that, no, we discover medicines. Okay, you're discovering medicines on one hand, and on the other hand, you're polluting. That means you cause the problem, and you might find a solution to the problem. This is not correct, right? So we should find a solution to the problem without causing the problem. So that's the idea. And many of youngsters today know about this so much thanks to media. So there are rough estimates is that more than 600 solvents are there in the vogue today. So in academia, we go with the principle, make, use, and dispose. Most of the solvents are made for us, like tetrahydrofuran, for example, it is made for us. And then we use them and you dispose it off without ever bothering about whether it is going to be useful or not. Come on, where do I point out? Yeah. So we also know that there are many types of solvents, polar, apolar, protic, aprotic. Any organic teacher will tell you about these things, that we have different kinds of solvent, but almost all of them I think I went too far. Some of the solvents that I listed here are extremely common. I just listed them. You know, without even thinking, we use dichloromethane in our lab. Without even thinking, we use chloroform in our lab, knowing or without knowing that they cause enormous of problems if you take them inside your body. Because they are chlorinated solvents. They don't get destroyed at all, including your body cannot destroy them. And so is the solvents which we think are innocuous. THF, ask a serious organic chemistry researcher, they cannot live without dry THF. They cannot perform one reaction without dry THF. But then what happens to THF? Is it a problem? Acetone is a problem. Almost every solvent that we use is a problem as far as the common man is concerned. It's like, gun. I have to shoot it correctly. Where is the sensor is there? Okay, now I see that. I thought sensor is here. Okay. Now, we think that acetone is safe, but it is not all that safe. You go to industry, they will say that, we're not talking about 1 liter, 2 liter, which in academic institutions use. We are talking about tons. We are talking about thousands of kgs of acetone is used in industry. And what happens to it? If somehow it spills, it can catch fire because it's heavier than air. It goes down. Without knowing, people tend to, use them. And then they could cause lots and lots. Dioxin, for example, it's a hepatotoxic, and methyl tertiary ether, although it has got a good smell, but it could cause you problems. THF is absolutely good smell in the beginning. Yeah, tell me. Oh, sure, you can decide also. Okay. Both sides pointed to that. Okay, so all right. So THF is a good smelling, but a chronic exposure. See, all of them is something which, maybe present-day teachers are teaching you. Present-day teachers are teaching you that THF, don't use THF. Instead, you switch over to CPME, cyclopentyl methyl ether. Don't use THF, switch over to 2-methyl tetrahydrofuran. Why CPME? Why not THF? Because THF also generates, tetrahydrofuran generates peroxides. Diethyl ether, at least when we were young, we were using diethyl ether. But today, diethyl ether, we don't see them at all. You know why? Because its boiling point is only 32 degrees. It evaporates extremely fast. It catches fire, and it also puts you to sleep. So all these things are there, So, because we see that diethyl ether was used as an anesthetic. Chloroform was used as anesthetic at the time of Arthur Conan Doyle, who wrote this, Sherlock Holmes books. So that way. So CPME is one solvent which industry would like to promote because it's hardly mixes with water, and also it doesn't form peroxides. But then the cost of CPME is coming down to a level that it may be affordable at industry level today, because we can regenerate it or reclaim that back by distillation. So in fact, reuse, reclaim and reuse is a mantra in industry. Believe it or not, the profit and loss difference is only a solvent. So if you can recover your solvent and put back to its your use, that's the difference between the profit and the loss, not making a profit. So many industries are looking at the possibilities of recycling the solvent, which we used to practice in our lab many years back. So CPME, I just listed this reaction of how to make CPME in the industry, but we don't make them, but we buy them. The cost is about 1,000 rupees, whereas the MTBE, methyl tertiary ether, which is a better solvent compared to diethyl ether, is about 300. 2-methyl THF, which comes from natural sources, is 500 rupees. So another solvent which I just listed here, which is very high boiling, sulfolane. Many people may not know this, but sulfolane is a good solvent for many organic reactions, which can be done because it's a very high boiling point, 285 degrees. It doesn't evaporate, but you can conduct reactions more easily than, for example, DMSO, dimethyl sulfoxide. So wherever you are using dimethyl sulfoxide, one can switch over to. But still, that compound is coming from not from natural sources. One that comes from natural sources is 2-methyl THF. So if front benchers can tell who practice organic chemistry, do they use 2-methyl THF? They don't right now, because in my opinion, they don't. I think Ramana can tell whether his lab uses them or not. But because there is a mind block. Because every possible reaction that was described in literature, they use THF. Therefore, we tend to follow them blindly. But wherever THF is there, you can switch over to 2-methyl THF today, because 2-methyl THF is a replacement for many of these ether solvents, namely diethyl ether, of course, THF, of course, diisopropyl ether, methyl tertiary ether, or CPME, cyclopentyl methyl ether. The boiling point is 78 degrees, so it can be recovered very easily. Its miscibility with water is negligible. It doesn't form peroxides as much as THF does. Therefore, one can do all sorts of dry reactions in 2-methyl THF. So if possible, and I want to tell that you can switch over because these come from natural sources. 2-methyl CHF is a sustainable solvent. That's what I want to tell you. And in industry, we are switching over to 2-methyl THF whenever we want to do reactions, because industry cannot pollute, because we have to get a certificate every year from Pollution Control Board. And Pollution Control Board, in India, their things are different, but then it also doesn't give that easily the pollution control, this one. So I listed the good points about it. Siva told me that you have 30 minutes and I want to put it 25 minutes. For 5 minutes, I can still ask some questions. That's the idea. So I will rush through the slides because I want to tell you about deep eutectic solvents. That's the idea. So another, very attractive to me is styrene. Styrene comes from natural sources, is a sustainable solvent of a very high boiling point, 227 degrees. And what I listed in the just next to it is an equivalent solvent that we normally use. For example, we use NMP. You ask any serious organic chemistry researcher, they will tell you we use NMP as a solvent, N-methylpyrrolidone. And N-butylpyrrolidone is a better solvent than NMP because of its low, characteristics of toxicity. So whereas NMP is more toxic. But even better than NMP is styrene. Styrene is a solvent which is coming into vogue only very recently as a replacement for NMP and DMF. But it does have a keto group. But it is coming from, there is certain parameters called Hansen solubility parameters. I might like this Hansen solubility because it's called HSPA parameters. And then these parameters, Camlin-Taft parameter, these tell you about equivalence. So tomorrow, if you are looking for an equivalence of a solvent that you are using but causing problem, you might look at the parameters of HSP and then look for a replacement, more sustainable, more usually available, better solvent system. That's how styrene is a solvent that can replace NMP and DMF in its polarity, in its viscosity, in its dielectric constant, and the ignition, the flash point, like that. So many parameters are there. So like styrene is made from cellulose or biomass. You can see that. And then in 2 steps, it is made So the other derivative of styrene is a cygnate solvent, where they convert it into an acetal so that it becomes innocuous. Once it converts to acetal, it becomes equivalent to a dichloromethane in its solvent characteristics. So one should possibly look for a replacement for the traditional solvent that we use, and look for those solvents which you may not want to take down your notes, because I shared this PPT with Siva. He can share to you anybody, no problem. There is no intellectual property right here, so they can take it down and take it. But non-chlorinated, therefore that's very important. Another solvent that comes from eucalyptus oil, particularly from the leaves which has fallen down from the eucalyptus tree, is eucalyptol, which is having a boiling point 172 degrees. That is a solvent which is a sustainable solvent. And there is another solvent called valorolactone, which is prepared from levulinic acid, which is an alternative solvent for DMF. So these solvents are emerging in recent years. This is about eucalyptol. Okay. And this another solvent system which making a lot of buzz in recent years is ionic liquids. I'm sure many teachers would have taught you something about ionic liquid. Ionic liquid is a liquid, although it has ions. Almost all the ionic compounds that you can remember are, are all solids. But there are some ionic compounds which are liquids, and that, of course, if you have an organic anion and an organic cation, they tend to become liquids. Okay, and one of the, I wanted to show this to tell you that Professor P.C. Ray, who is one of those doyen organic chemists of our country during pre-independence times, and he is credited with discovering the first ionic liquid in the world. So that he, of course, did not really understand its significance, but he made the triethyl ammonium nitrite and showed that it is a liquid at room temperature. It's an ionic compound liquid. So he described that much, but he did not tell about its utility and all those things. And more importantly, Walden, who is very well known to us through Walden inversion, in SN2 type of reactions and Walden inversion, he is the one who described more details about triethyl ammonium nitrate, and he described it in 1914, 1911, so it's just about 3 years later, although I don't think they knew. But the whole thing went into oblivion till 1992, that is about 80 years. And where the N-butyl, 1-butyl, 3-methyl, imidazolium, tetrahydrofluorate is a gold standard ionic liquid which is in use in WIG today. If you take out a number of papers on ionic liquid, there are hundreds of them. Therefore, why there are hundreds of them? Because you can perform a reaction in an ionic liquid. But why ionic liquid? The good things about ionic liquids is that they don't evaporate. You just keep it outside, they stay forever. That's first thing. And they have a reasonably high boiling point. Therefore, they are liquids in the first place. So they dissolve organic compounds, both reagents and reactants. And then you can take out your products with a non-polar organic solvent very easily because they don't mix with ionic liquid. So this way, the reactions can be performed, taken out and reuse them without ever hurting the solvent itself. So all that one needs to do is to conduct the reaction, take out your product, and conduct the reaction, take out your product. Repeatedly, one can do that. Somewhere they have shown it about a dozen times they can use the same ionic liquid for conducting the same reaction again. Okay, so that's they're non-volatile, dense, flame resistance, all sorts of good things are there. But not only the ionic liquid about imidazole, there are many compounds which have been shown to be ionic liquids, and then many are emerging out, particularly in the technology field. Okay, of course, I did put one slide to show that why ionic liquids are liquids in the first place. The reason is that they are made up of organic cation and inorganic anion or an organic anion, but they wobble. Unlike sodium chloride, for example, sodium and chloride, they don't wobble. Because they wobble, they tend to become liquids. Okay, wobbling is more, steric hindrance, wobbling is more, and then they become liquids. So that way, there is hardly any hydrogen bonding networks like in water, but then they become liquids because of the steric hindrance between the cation and the anion, and then they tend to exchange between themselves. That's how they are liquids. Okay, and just I did this Google patent search and found that to be hundreds and hundreds, 10,000 patents have been filed with ionic liquid as a keyword. So one can imagine that there are many possibilities. They are looking into enormous diversity of field for ionic liquids. Although they are good, they are still non-sustainable, that they do not come from natural sources. They are of course expensive. Many of the people who do research know that they are expensive, and then they are labor intensive is a synthesis. First you have to make them in the first place, and so that one can use them once it is made, that means we can purchase them, then things are okay. To purchase them we need to have money, and industry doesn't have money, believe it or not. A lot of people think that industry is flush with money. What they have is an intense ideas, So recently I did write a review article. So I put that about the deep eutectic solvents, okay, which appeared in Resonance. Resonance is a basic journal which talks about the recent advances in science that could be applicable at the BSc level. So I just put only one review about the application of deep eutectic solvent in extraction of media for plant and food samples, about which I'll tell you a little bit more. So there are a number of reviews have appeared in deep eutectic solvents, but their discovery is only extremely recent. About ionic liquids, I told you nearly 100 years back, whereas DES, deep eutectic solvents, their discovery is very, very recent. Then let me also tell you about what is the eutectic means. Why do we call them deep eutectic solvents? And in the Greek, it is meant that it's a well melting. That means they melt at a low or liquid at room temperature. That's the idea. Okay, so they are liquid at room temperature, and they have a sharp melting point, and then lower melting point, a freezing point, the individual constituents. See, the whole thing is that there are two compounds coming together and they form a liquid. Two solids, mix them, it becomes a liquid. So there's a magic here. So that magic, when they have become liquid, what happens and how we can use them, I'm going to tell you in next few slides. Okay. Imagine you take choline chloride, which is a natural chemical. Many of you may or may not know this. Choline chloride is a neurotransmitter. It is there in all of us, all human beings, all animals, all higher order animals. There is a neurotransmitter, it is there. And that choline chloride, which comes from animal husbandry industry as a byproduct. Lots of people do not even think when they take a non-vegetarian food, they take only a certain part of an animal. But what happens to the rest of them? Rest of them, they also still have a lot of good chemicals that one can take it out and then use them for some reason or other. Okay. So one of the compound that can come out with an animal husbandry industry is choline chloride. And urea, everybody knows about urea. Urea is a fertilizer. Urea is a natural chemical. Vellore made it. Therefore, it has become a very famous organic chemical. And that's how it's a natural compound. Every human being makes it. Or, I mean, animals also make it. But then when you mix two solids, melting point of 302 degrees and 133 degrees, which I put it here. And when you mix them together, mix them good enough, it becomes a liquid. Liquid with a 12 degrees freezing point. Therefore, at room temperature, it's a liquid. Now, that's the magic. The two solids, mix them together good enough, then it becomes a liquid. Now, this liquid is, initially it was called an ionic liquid by Andrew Abbott. And this is something which I thought I should possibly tell, that this is a guy from the University of Leicester in UK, who, I don't know why, but he mixed them together and then he found it to be liquid. What really came to his brain wave that he had to mix these two, but he did that in a 1:2 ratio. Remember that, that's the important point. You can't mix with any ratio and think that it becomes a liquid. And then it became a liquid and he took a patent first, before publishing in JACS. So his first paper appeared on this deep eutectic solvent in JACS, and before that he took a patent first and showed that this is a liquid and it can do lots of transformations. I'm going to tell some examples out of that. So what I want to tell you here is the take-home message is that these two solids, you all have to discover one solid, mix them together, it becomes a liquid, use that for your purpose and show that and take a patent. So it's not easy, although I tell this. But then remember this, this is only a graphical representation of deep eutectic solvent. What are the possibilities that, I showed this as a choline chloride is a vitamin B complex material, and then nutrition supplement for livestock, and urea is an agricultural chemical, and these two mixing together, DES has become, for DES, it has become a gold standard, right? And it's just not urea. and the choline chloride mixing with the various other compounds. It could be a carboxylic acid like dioxylic acid or phenylacetic acid, malonic acid, which all of which are natural compounds. Phenol, which is also a natural compound, but much less amount, but the phenol is available. Ethylene glycol, glucose, fructose, they all mix in certain proportion. The important point is the proportion here, 1:2. If you mix that 1:2 and mix them good enough, in my lab in Pondicherry, we bought this choline chloride and urea is already available. So we just heat it to 80 degrees and then cooled it. It becomes a liquid, stayed forever. And for about 6 months, there was nothing happened to it. So not even green, yellow, no color. So then, then why they should become liquids in the first place? Unlike ionic liquids, which I told you it's becoming the steric hindrance and wobbling, here the extensive hydrogen bonding network and a little bit of electrostatic attractive forces also. So that's how we need a hydrogen bond donor and a hydrogen bond acceptor. So this oxygen is an acceptor and an hydrogen bonder, electrostatic attractive forces, and then this is how it keeps going, a network goes on, just like in water, for example. So this extensive hydrogen bonding network is the reason, is what has been told, excuse me. And here I listed a number of, one component to the other component when they mix them together. See, one discovery, I tell you, as always happens, one discovery, people latch onto it and then keep on working on it as quickly as possible. Now you get publications, maybe you get patents, you could find something. So that's the whole idea. Now, people have quickly discovered that there are so many of the hydrogen bond acceptors and hydrogen bond donors. Mix them in a certain proportion. Proportion is important. So if mix them proportion, it becomes liquid. 3 minutes. Okay, 3 minutes. All right, fair enough, because I am also coming to the end. There are obviously different types of deaths are there. Once they are there, they are always there. Okay, and then where do we apply them? So we can apply them into diverse fields, like what I wrote here is a coupling reaction, or very importantly, perfumery chemicals from plant sources. I was thinking when I was coming back from here that Madurai Malika is a patented or geo-tagged material. And what does Malika contain? Can we take out the fragrance material and make money out of it? One can do in this way that Malika you put it in desk and take out the soluble components with a an immiscible solvent like maybe 2-methyl THF. 2-methyl THF is not miscible with DES. And of course, I listed the other possibilities of as using as a solvents. There are many alternative solvents are possible in modern day chemistry. So, and less solvent is possible in flow chemistry. I think these things which many of. So I'll skip these slides because I realize that I have only 3 minutes, but then I'll spend a minute to tell about TADF. I told you already that in historian language, TADF means science, and then we have, it's led by 2 scientists, Sivakumar and then Gopu, and there are scientific personnel. So if any one of you are interested to join our company, you are always welcome, but you should be prepared for 8 to 9. Simple. So you start at 8 and leave at 9, and then you learn a lot. You learn because it's a science driven. We do not stop anybody from learning. We'll learn a lot. And I thank you for your kind attention.
Hello, any questions?
Either they understood everything or they did not understand anything. So if they understood everything, no questions. Anything, no, they didn't understand anything, that's also no questions. Perfect.
No questions?
No, they have. This is one topic which anybody can ask any question kind of thing. Sir.
Yeah, please.
So the serine solvent is very interesting. If we don't have that ketone, the ring will easily open in acid.
It doesn't.
Yeah.
Next one is, it is the next carbon atom.
Okay.
Of course, you're correct. It's a 7-membered ring. It is positive to hydrolyze it, but it's a very stable molecule.
The same with the signet, which is also equivalent to DCM. But I don't know how hydrolytically stable with acids.
The truth is that we don't use acids when you are conducting that reaction.
Right, okay.
Of course, every solvent has a limitation, sir. Even in THF, we can't use acids. THF, no, you cannot use that in, for example, HCl. It opens up. So you're correct. It has its own limitations. It's not a mantra for every solution. You're correct. That part is correct. But
So I have one question, maybe not question, just information. If anybody is interested in this company, TDS, what will be the package? I mean, salary package.
I can't. See, one thing we will tell you in industry, you will never know the salary of your neighbor. So, so money part, you leave it, because I also tell you, lots of many years back when I joined for the first faculty position, there used to be, the Dr. Pandey, he's still there. When he went for interview for a private industry, they asked for the salary. Then the guy who is supposed to offer him a job, he told, very simple. We take a balance, make you sit in one of the sides, and we'll put money on the other side. How much you weigh, you take it. Now, I think you understand the meaning of that, actually. So whatever you are worth, you are taken. So in the beginning, whatever may be salary, people get recognition depending upon your performance. In government system, everybody ages. That's it. There is no difference between aging. Everybody. In private industry, your aging is commensurate with your performance. I think that answers your question.
Teaching the green solvents and everything. So what is the role of green solvents in industrial and day-to-day practice? Because we are developing a lot of green solvents. Apart from the ionic liquid, even for the API development, everything they are using, still we are depending on the THF and the dioxin, everything. Because you are from industry.
I know, honestly speaking, what happens is that industry works on profit. We cannot really, and we are also bound by regulations. Believe it or not, we have that environmental regulations of the state government. They come and inspect and give a certificate. Now, to meet their requirement, we should have a complete data. We are an ISO 9000 certified company. That means we should have complete inward and outward. Okay. Now, how much of dichloromethane we purchased and what did we with the inventory should be available. Now, what do we do? Honestly speaking, wherever possible, THF is switched over to 2-methyl THF. Money, can we recover it? Or we do recover. We do recover and then reuse. But in Hyderabad, if you go, it is driven by entrepreneurship. That means they buy the used solvent from us, distill, fractional distillation, and resell it to us only. So through fractional distillation. So as much as possible, we don't waste. So, well, green solvent, like all those listing that I had told, that we are switching over wherever possible. Like 2-methyl THF, we did switch over. Okay, but we do still use chlorinated solvent. Our clients will not allow us if we use that at the end stages. We can, number one, I think you must have heard about GMP practices. Yes. So whenever we supply a material with GMP practices, no chlorinated solvent. Like that, we have to, otherwise the client will not buy from us. We have to share the ROS. I think maybe you know what is ROS, route of synthesis. Route of synthesis will have complete regulation, complete data on what we do. So the client, it's a client supplier privilege. That means we don't disclose anybody. What do we do? But the client wants to know everything. So I think I did answer your question.
Yeah, but related to them, because as Sivakumar, so you are a good academician. Okay, then so still in a laboratory for the organic practicals, still we are using the dichloromethane and diethyl ether. So for the organic practicals, we are widely using. So what is your suggestion for alternate greener solvent from the academic, starting from the academic?
Absolutely, I'll tell you. if possible, see, one thing is a mantra, recover and reuse. That's a mantra.
But for the MSc practicals, is it
MSc
possible to
practicals
recover?
also, sir, you devise, because if you are an autonomous institution, if you can devise something, you can devise of, see, my MSc practical, even Nithyanandan, Sivakumar, everybody knows that they did practicals of a product which I could do in research. You may not know, DMP, desmortin pyridinane, was the starting metal is 2-iodobenzene, was made by MSc students, and 2-iodbenzoic acid, we continue to use to make it to desmortin pyridinane and desmortin pyridinane, which we used in our research. So maybe what I'm trying to tell you is that you will have to devise something. What I'm telling is need not be the correct one, but you might come out with something good and better ones. So definitely switch over to those practicals, particularly in autonomous institutions can do that. And also give the practicals which is not in making amount in bulk, milligrams, which characterized by spectroscopic means. Same material you use, Arunachalam will tell you that if we do practicals in our MSc practicals, you take UV spectra, you take NMR spectra of the material that you made yourself and then interpret.
Thank you, sir.
That's how I tried to tell you, but switch over as much as possible.
Okay.
All right.
Thank you, sir.
I can understand affiliated colleges, they don't have liberties, but wherever there is a liberty, you can do that.
So thank you so much. Before I introduce the next, speaker, I have two things to say. Sir, I hope you all agree with whatever Professor Kaliyappan said. His classes are wonderful. And the second thing is I got a chance to stop him after 25 years. Sir, you have only 3 minutes left, which is not possible otherwise. The third thing is, my sincere apologies. I messed up your introduction. The same way I used to do his organic chemistry exams. Okay. So this is a token of appreciation.
Thank you. Thank you.
Thank you,
Ma.
sir.
God bless you.
Thank you, sir. Let me introduce the next speaker, Professor Raja Angamuthu. He has done his PhD from Leiden University, Netherlands. After completing his, bachelor's and master's from Annadhasan University, Trichy, he was an RA in Annadhasan University from the year 2002 to 2005, and then followed by Leiden University, and then he also did his postdoc from University of Illinois. He has, Young Scientist Research Award from DAE, Department of Atomic Energy, and then Rubicon. He was also a Rubicon Independent Postdoc Fellow in Netherlands from the years 2010 to 2012. Let me, yeah. He's already here. Yeah, thank you.
Not on. Thank you for your kind introduction. Thanks, Siva and Suresh, for kind invitation. Actually, when Siva asked for introduction, I told him, you introduce Raja Angamuthu, he's from IIT Kanpur. Okay, it's already 1 o'clock. I guess there are one or two more talks. I will make you eat lunch on time. Within 15 minutes, I would like to convince you that we are able to sequester few environmentally detrimental molecules and we are able to activate 1 or 2 also. So in our lab, we would like to use simple organic hydrates which are made in one-step synthesis to activate some small molecules. Sulfur dioxide is not really activation because it is already activated molecule. And we would also use metal hydrides. And most of the time we would like to isolate them and analyze because working with metal hydride is kind of not that nice strategy actually. So then we would like to sequester the small molecules using very weak interactions, and I would like to show in few slides that what kind of interactions we would use in our research. And we would not be talking about this part where we would make such moieties in one-spot synthesis. And you would see how we combine all these things in one molecule to do the sequestration and activation. So to sequester the molecule or even to remove the molecule from the gaseous waste, we would like to develop some systems. They should be easy to synthesize. If they are working well, if we want to make it better or stabilize them in certain conditions, they should be open to modifications. Of course, they should be cost effective and eco-friendly. And most importantly, the interaction between the detrimental molecule and the host system should not be too strong, because if they are too strong, we have to use too much energy to break them apart if we want to remove the molecule from the host or if we want to activate the molecule. So our main goal in developing the host system is the small molecule, and the system should not bind too strong. So as a bio-inspired group, we always look at the nature if we can develop some things on the line of natural systems. So you can see here, in any biomolecule, if you see, there will be a lot of water molecules around them. And that's how they are in biosystems. And all the water molecules, if you see around the heterocyclic systems, for example, this is a water molecule. It will have two free lone pairs. And those localized electron density will be always looking at the center of the heterocyclic ring. And I will show you how the heterocyclic ring electronics is in the middle of the ring. We all know in benzene, we have electron density on top of the ring. And if you attach electron withdrawing group on the side, the electron density will be removed from the center. And the electron deficiency created in the middle attracts the small molecules. We don't want to work with water, but we want to use these kind of small, weak interactions to attract the environmentally detrimental molecules. I will show you one practical example where we can visualize actually simply. So you can see here, hexafluorobenzene melting point is 5 degrees, so it is a liquid at room temperature. Mesitylene melting point is minus 45 degrees Celsius. That is also liquid at room temperature. If you mix them, it's a solid. It's a solid at room temperature. The reason is that the hexafluorobenzene, because of the presence of electron withdrawing groups in the periphery, it completely removes the electron density that we know as a pi cloud to the periphery. So in the middle, you have electron deficient valley. And in the mesitylene, because of the electron donating groups, you have the elevated electron density in the middle. And this electron deficiency and electron density occupies like strategically each other, they will sit on top of each other. So you have hexafluorobenzene, mesitylene, hexafluorobenzene, mesitylene. This interaction allows the mixture of this liquid and this liquid to be solid in room temperature. So you can see how strong this interaction can be, but this is very weak interaction. So the melting point is 34 degrees Celsius when you mix these two things. So we have drawn a simple molecule where the triazine will have these electron withdrawing groups, and by virtue triazine is already having electron deficiency in the middle. So by attaching these groups, you can even pull more electron density from the middle. You will have a delta positive nature in the middle of the triazine ring. So if you look at the electronics of sulfur dioxide is already a charge separated molecule where the sulfur is cationic, oxygen is partially anionic. So one can conceive that the electron density elevated oxygen can be attracted to the electron deficient ring of the center of the triazine ring. And also you can expect the electrostatic interactions between the S plus and the nitrogen, because this nitrogen will have some localized electron density, which we can visualize in the molecular electrostatic potential picture also. You can see in the benzene ring, you have some electron density in the middle, we call pi cloud. And the more electron withdrawing group you attach on the periphery, the electron density from the center will be removed from the center, and you can see the electron deficient valley will be created. And that is the electron deficient valley we would like to use to attract the small molecules. But experimentally analyzing or experimentally believing these things is a little bit tricky. So you can see here immediately we have made large number of molecules because they are all one-step reactions. You take cyanuric chloride and mix with thiols, amines, alcohols, you can get this kind of simple molecules easily. And in the middle of this triazine ring, we are expecting the electron deficient valley. The problem is this molecule has the electron deficient value in the middle of the trisine ring. But on the other hand, the same molecule has electron density enhanced centers also, and they intermolecularly interact. So the problem is now the incoming molecule doesn't have any other site to stand on top. Actually, instead of this sulfur, I want the sulfur dioxide to be standing on top, carbon dioxide to be standing on top, especially chlorofluorocarbons where not many systems are available to sequester them. I would like to see those kind of things. For example, you can see a chloride is looking at the center, a sulfur is looking at the center, but I don't want the intermolecular interactions. So we have to avoid the interaction between the same molecules by building a fort around this center so that the small molecule will come in and then strategically sit there with using the weak interaction. So we have changed a lot of things. We have studied a lot of molecules and there were few successes. So simply you can see we know about pi-pi stacking, and also these kind of molecules stacked on top of each other are called as pi-fa dimers. The problem is here the distance between two rings, such stacked rings is like 3.7 to 4.2, 4.5 angstrom. If you are able to push those two rings around 8 to 9 angstrom unit, you can put a small molecule in the middle of them. So our main aim is that with changing the peripheral groups a little bit bigger, hydrophobic, so that the rings will go away from each other. So if we gain 9, 10 angstrom unit, we can have small molecules, triatomic, tetraatomic small molecules in the middle. And you can see here, this is a simple system. Isopropyl amine substituted triazine, this triisopropyl amine substituted triazine. The same molecule has hydrogen bond donor and hydrogen bond acceptor. Because of that, you can see here, this one molecule is in the middle and 3 more molecules are on the periphery. They are making the hydrogen bonding. Now, the good thing is that this molecule and these 3 molecules are perpendicular in direction, so they make a nice basket. And if you put this tetramer and another tetramer on top of each other, you can see the isopropyl groups push each other, and in the middle of these 2 triazine rings, you have some 8 angstrom unit that allows the small molecules to go in the middle and then stand there. And the interaction between the electron deficient valley and the electron density enhanced groups from the small molecule, you can easily visualize. So this is one of the simple examples where you can see that, but our aim is to take molecules like sulfur dioxide, carbon dioxide, chlorofluorocarbons, or even simple halogenated carbons. So in the trial, one such molecule, you can see here, because now we know what to do to save this electron deficient valley. You can see here we have this tetramethyl substituted phenyl and thiol, and these 3 aromatic rings are perpendicular to this triazine. And because of that, 2 such molecules cannot come closer to each other, and 2 molecules are standing apart by 9 angstrom distance, and that 9 angstrom distance is good enough to put many small molecules. I will show you a few examples now. So you can see here, we start with simple systems where the highly electronegative fluoride has the more localized electron density, where that localized electron density can look at the electron deficient valley, and the distance is some 3 angstrom unit. In the TGA, you can clearly see this first drop is the removal of this difluorobenzene, and the second drop is the decomposition of this whole molecule, and that happens around 350 degrees Celsius. This happens around 98 degrees Celsius. The boiling point of difluorobenzene is 88. The temperature at which the difluorobenzene leaves from this system is 98. The 10-degree difference in the boiling point says how much the interaction is between this electron deficient valley and the electron density elevated fluoride ring. Fluoride. And you can see here, a triazine here, in the middle there is a difluorobenzene, on top there is another triazine. So it will be stacked on top of each other like that. So if you take monofluorobenzene instead, only one fluoride is attracted to the triazine ring, and you can see the temperature difference is 5 degrees. It doesn't show exactly the energy is half, but it says that the difluorobenzene is interacting strongly than the monofluorobenzene. And you can see here dibromobenzene, the temperature at which the temperature difference between the boiling point and the temperature at which the dibromobenzene leaves is 30 degrees Celsius. This means the interaction is a little bit stronger. So the interaction is not only by the electron density and electron deficiency, the interaction is also because of the size of this molecule. Because if the size and orientation of this molecule allows to pack exactly in the middle of these two trisine rings, the interaction will be perfect. Then when the interaction is perfect, the interaction energy also will be a little bit higher. And in dichloromethane, you can see the temperature difference is 80 degrees Celsius. The good thing is that this molecule is able to take all the small molecule inside. And the other good thing, it decomposes at 350 degrees Celsius. If you look at the flue gas plants, where the gas waste comes out with carbon dioxide, sulfur dioxide, little bit of moisture, everything, that comes around 200 degrees Celsius. So you can use this system to sequester molecules from the flue gas plant actually, because it works at until 350 degrees Celsius, so the gas mixture can be 200-250 degrees Celsius without any problem. And you can see in the crystal lattice how the small molecules are sitting in between the two trisine rings. There is a trisine here, trisine here, trisine here, and dichloromethane sitting in between. One chloride is interacting with the trisine here, another chloride is interacting with the trisine here. And after removing this dichloromethane, the lattice is still same, so you can remove and then replenish the molecules also. And you can see here, all we need is one electronegative atom in the molecule. So fortunately, all the environmentally detrimental molecules, chlorofluorocarbons, carbon dioxide, sulfur dioxide, any molecule, it has at least one electronegative atom, THF, acetonitrile, carbon disulfide. And we can also use this system to separate small molecules. Maybe I will show you in the next example. You can see here, if you take a mixture of cis and trans 1,2-dichloroethene, cis dichloroethene sits exactly in between two rings, so that stays inside, the trans doesn't stay inside, so you can separate the mixture of cis and trans. Cis will be inside and trans will be eluted outside. And you can see if you crystallize separately with the cis, the molecule will show the cis. In trans, the trans will not be inside, only the molecule will be making the matrix. Finally, the one which we wanted is sulfur dioxide. You can see here, S plus of the sulfur dioxide has the electrostatic interaction with the nitrogen, which has electron density. And the O, delta negative O of the sulfur dioxide is interacting with the center of the ring with the distance of 3 angstrom. That is very good, actually a little bit of stronger interaction compared to these lone pair pi interactions. And the boiling point of sulfur dioxide is -10. The temperature at which sulfur dioxide leaves from this matrix is 110, so the temperature difference is 120 degrees Celsius. And still it can work in the flue gas plants actually, because this one is weaker, this one is a little bit stronger, and this temperature difference is somewhere in between those two things. So when we heat this molecule, first this sulfur dioxide will go away, then second this sulfur dioxide will come out at 120 degrees Celsius. And you can see here, now we know how to bring the gaseous small molecule to the active site. So activating gaseous small molecule has one big bottleneck. You have to increase the temperature or increase the pressure, then only you can activate the small molecule, because a hydrophobic molecule like carbon dioxide, it has to reach the active site, you have to increase the pressure. But if you have a group that lures the small molecule near the active site, it is very easy to activate the molecule. So I showed you in one step we can make these molecules. Ethylene diamine, pyridinaldehyde and alcohol, you can get these molecules out. And the ethylene diamine, the R group can be anything. We have like 10-20 different R groups, the molecule always works. Once you make the molecule, you just add one equivalent of sodium borohydride, you can reduce it, and then the stable molecule will come out from the system, you can use it. And here I will show you how we are using this molecule to activate the sulfur dioxide from sulfur dioxide to sulfate. In this, the synthesis of this molecule is very simple. Making this ethylene diamine using the cyanuric chloride is just a one-day job. Then once we have the ethylene diamine, mixing 2 equivalent of pyridinaldehyde and methanol in any metal salt will work. Then we can build this. The problem with this hemiaminal group is we cannot use this directly, so we reduce this molecule into this stable molecule. Then you can see here, this is the hemiaminal molecule. You can isolate, very stable, but it will not be stable in presence of acid and bases. This is the last. And you can reduce that hemiaminal ether group using sodium borohydrate, that is a stable molecule. Then you can protonate, you can use sulfur dioxide, any molecule, the whole molecule is stable under serious conditions, toxic conditions, acidic conditions, basic conditions also. So the electrochemistry is referenced against ferrocene. According to this molecule cannot extract electron from ferrocene. So somewhere here the molecule sits. If when you protonate the molecule becomes electron hungry, so that accepts electron at this point. When you interact this molecule with sulfur dioxide, the molecule becomes more electron hunger, that goes below the ferrocene, so it can extract the electron from ferrocene. Here we cannot use the electrocatalysis in the electrocatalysis cell because of sulfur dioxide, so we use the chemical electron donor, ferrocene as the electron donor here. So you can see here ferrocene has its characteristic peak here, and the copper complex has its DD band here. When you combine the copper complex and ferrocene, electron transfer doesn't happen, the copper 2 stays as copper 2. The copper complex, when you mix sulfur dioxide binds to these areas, the whole molecule becomes electron deficient, and that is what we see here, the DD band moves here. Then when you mix copper complex, ferrocene, sulfur dioxide in presence of air, in open air, you can see here the ferrocenium forms here, that is the characteristic peak for ferrocenium. You can add ferrocene as much as you want, you purge sulfur dioxide, you will get the ferrocenium sulfate. Then you can remove the ferrocenium sulfate, and then you can keep on adding more ferrocene and more sulfur dioxide purge. It should be done in presence of air. So I think I am able to convince that I will be able to bring the small molecules to the active site, and I am able to activate the small molecules also. And in future, we would like to do the electrocatalysis, maybe not with sulfur dioxide, with some other molecules. So these are the first 3 students who established this whole set of work, conoramine synthesis. He is Abhishek Konar, because of his name only the molecule is conoramine. And Sonam Mehrotra established all the small molecule sequestration. Thank you for your kind attention.
Thank you, Professor Rajan. With the momentum, moment of inertia kicking in on me, I forgot to mention that he is from IIT Kanpur. I'm so sorry. So, any questions?
A very interesting talk, sir. Sir, have you heard of tetral bonds?
Yeah.
So, do you think the molecules that are capable of forming tetral bonds can be used as for sequestration agents?
We observe those things. For example, you are seeing the nitrogen and sulfur. In simply, I call electrostatic bonds, but it's okay. But it is possible. It's possible.
Yes,
they are a little bit stronger than the lone pair pi interaction.
Yes.
I am aiming at lone pair pi interaction because the energy involved is very less. So it is easy to remove the molecule later also.
Yes, sir.
Tetral bonds make a little bit stronger interaction.
Best because while doing literature survey, like we are observing that the papers coming on the tetral bonds, it's increasing recently.
Exactly.
So there is a chance of doing that also. No? Yes, I wanted to know that. Thank you.
So even though I wanted to do lone pair pi, you can see there is a NS bond also.
Yes, sir. Yeah, I could see that.
Sir, have you performed any anion bending studies with your trypsin-based systems?
It will work. It will work. Anion pi interaction, cation pi interaction is a well-established topic. They will all work just by changing the electronics of the peripheral groups. For example, if you attach electrons withdrawing group or electron donating group, you can make the interaction with the anions and cations. But we are making interaction with the neutral molecules, gaseous molecules.
Thank you.
Any more questions? If not, I have a question. Just a clarification, actually. I'm just thinking, loud. Is there a way that these molecules can be used as scrubbers for industrial applications?
Exactly. That's the main goal of this.
No, you talked about certain industries. I'm asking about, overall maybe a lab setup.
Yeah. So, for example, these chlorinated gases, we are trying to attract all the chlorinated gases into this because of if you have chloride, bromide, fluoride in the small molecule, it is very easy to attract those molecules using this scrubbing system.
So how different this is from existing method? That's exactly what actually.
See, in every case, so if you are using compression as the goal, so if you will use low temperature and high pressure to compress, for example, into MOPs and all. This one we want to use at room temperature and also elevated temperatures. Still the interaction should work. for example, the sulfur dioxide interaction, the crystal diffraction was done at room temperature. So we want to use mostly at room temperature and until 100, 200 degrees Celsius. So they might work at high temperatures without any force, without any like low temperature or high pressure. They should work.
Thank you so much. Yeah, as a token of appreciation, I don't know. Today I have, amnesia or something. I forget one or the other step.
Thank you.
Thank you. So let me introduce the next speaker, Dr. Ganesh Venkatraman. Not to forget, I am going to, read out everything. Assistant Professor, Department of Chemistry, India. Just joking. Okay, he is from Indian Institute of Technology, IIT Kharagpur. He did his education from Bishop Heber College, Trichy, and then joined as an integrated PhD student from IASC. He worked with Professor S. Chandrasekhar as a CSIR Shyama Prasad Mukherjee Fellow. He has postdoctoral experience in 2 countries, one from Japan, another one from UK. And he started as an independent researcher to start with in IIT Kharagpur. Now he is an assistant professor there. He is also a recipient of Ramanujam Fellowship.
Yeah, thank you for the generous introduction. And good afternoon, everyone. I'm the one who is stopping you from lunch. So I work on nickel catalyzed oxidative cyclization of pi systems over benchtop. Firstly, I would like to thank the organizers to give me an opportunity to present my work here. So I joined the institute in 2018. So I'm going to present some of my work that we have been doing recently. So the main aim of our work is to bring nickel catalysis to the benchtop. You know, nickel is very sensitive in the presence of air and moisture, but the main idea is to bring it to benchtop and make it easy to access. So, So our work mainly focuses on multifunctionation of unsaturated systems. So we work basically on nickel mediated reactions, and these are the verticals, copper and phosphorus catalyzed reactions. And so today I'll be talking about our nickel chemistry here. So we mainly focus on the oxidative cyclization of nickel 0 with pi systems. So what we are doing here is we select 2 pi systems and then we add nickel in a 2 + 2 + 1 fashion. So this gives us a 5-membered nickel species. Yeah. So in the first example, we have an aldehyde and an alkyne. So when they do cycloaddition, we are going to get the corresponding allyl alcohol. And similarly, when we have aldehyde and an enamide, we are going to get an enamide system here. So today I'll be covering these 3 topics. If possible, I will also show some of the results from here. Right. So when we joined, I joined in 2018, and I applied for funding. It was about 2019. The time we placed an order for a glow box, COVID happened. And for the 3 years, we are not able to get glow box. So now the problem is, I have proposed, my proposal is based on nickel 0, and I don't have a glow box. So what should I do with it? So, so the thing is, I started looking at alternative ways of accessing nickel 0. So these are famous air-stable nickel 0 complexes that has been recently developed. So this is the famous one, nickel COD2, which is highly air sensitive. It decomposes in 1 hour in air. So if we replace one of the COD ligands with electron deficient alkenes, generally what happens is this becomes much more stable. So what we're trying to do is we're trying to remove electron density from nickel 0 so that it becomes more stable. Yeah. So here they have used a styrene. This is Cornella's work, and Engel. This is in 2021. So they have used a fumarate ligand, and this catalyst here, this complex here, is very old, 1962, but nobody has used it in catalysis much. It is very less explored. This is called nickel COD DQ. This is duroquinone. These can be easily prepared. All these catalysts require glow box for preparation. But this catalyst, we don't need a glow box to prepare. So what we can do is we can take nickel COD and add DQ. DQ is this duroquinone part, and then heat it at 45 degrees Celsius. We get this red powdery material. This is almost equivalent to sodium sulfate in our lab. We store how we store sodium sulfate in the lab. So this is a nickel zero system, but we can easily store it in air for almost 200 days. So there is no problem with this catalyst. This can also be prepared through a glow box free method, where we start with nickel lacac, reduce it in situ, form the nickel COD to, in the Schlenk line, and then we add DQ to it. So this will give you the same complex. Yeah. So now we have the complex ready. So Aki is a PMRF fellow. She took up this challenge of using this complex for oxidative cyclization. So here you can see that all the aldehydes and alkynes that we have, they give very good yields and selectivities. So the selectivity depends on the ligand that we use, basically. Since our ligand is NHC, so most of the times the selectivities are constant. It's 97.3 in all the cases. So similarly, we can use alkynes and ionamides. The ionamides also provide very good selectivity here. And this is a chiral substrate which comes from chiral oxazolidone sort of system. And we get very good diacetyl selectivity in this situation. Right. So now the question is, the catalyst is very stable. That we know. So that means the reaction is also going to happen in air and water, is what we asked this question. So what we did was to look at the catalytic activity. So catalyst is giving us 81% when we prepare it freshly. So we store it for more than 200 days. The catalytic activity is still maintained, 79%. There is no issue with the catalyst for more than 200 days. You can store it like sodium sulfate on top of the bench. But when we open the reaction to air, there is no reaction. Similarly, when we do the reaction in trace amount of water, there is no reaction as well. So here, what happens is, we also tried to see what are the byproducts, what are the products that we are getting out of the reaction. One of this is duroquinone here, so which is the ligand that we actually added. So in this case, during the reaction, the duroquinone decomplexes, makes the active catalyst, and you can see here, when we add nickel COD-DQ with NHC, we are getting the corresponding NHC-DQ complex, and when we add the substrate displaces the DQ. And this complex here is highly air sensitive and moisture sensitive. So the reaction is highly air and moisture sensitive still, but the pre-catalyst that we have is quite stable in air and moisture. So this is the mechanism here, where this 2 plus 1 adduct will give us the corresponding 5-membered ring, and this undergoes metathesis, sigma 1 metathesis with silyl hydride to get the corresponding allyl alcohol, silyl allyl alcohol. So this is a simple comparison between nickel COD and nickel COD DQ. This is very few hours, it is stable in air, but here it can stay up to 200 days, not a problem at all. And storage and handling, this requires glow box, and it should be stored at -20. You need a freezer with the glow box, but here it requires, it can be stored on the bench top. The functional group tolerance is good with nickel COD, but it is much superior with this catalyst here. Yields are good and comparable and superior than nickel COD. Reaction time, nickel COD2 is short. Since we add DQ, we are sort of removing electron density from the nickel. So what happens is the activity comes down. So because of that, the reaction time is a bit longer. And the cost of nickel COD is expensive, and this is also expensive as well. So we are not working on the cost side of it, but it becomes more stable over the bench top. Yeah. So what I've shown here is these two examples here. So my student was trying some other work with 1,3 diines. So, and he forgot to add the aldehyde. Okay. So what happens in the situation? He got a very nonpolar spot, and then we tried to characterize it. What we found was it underwent a cyclotrimerization of this type. When it undergoes cyclotrimerization, you get a hexasubstituted benzene. This is all substituted benzene, fully substituted benzene. Yeah. So hexasubstituted benzenes are very important because the Taxol core is hexasubstituted benzene, and here there are several optoelectronic materials which are highly conjugated hexasubstituted benzenes, and you can also have host sort of supramolecular materials which are also a part of, which consists of X-substituted benzene as well. So we looked up the literature. So with 1,3-dienes, only one report was known with copper catalyst. And the problem is that it is very much restricted to aryl alkynes, aryl substituted alkynes. The alkyl ones don't work. So this is restricted to aryl dienes, and they have very poor selectivity. The selectivity that I mean is, this is unsymmetrical substituted, and this is symmetrically substituted X-substituted benzene. Okay, so what we thought was, if we want to accommodate alkyl functional groups, the catalyst has to be more reducing. So if we compare cobalt 1 and nickel 0 is more reducing than cobalt 1. So what we thought was to use nickel bromide as a pre-catalyst and reduce it in situ with manganese to form nickel 0. And this can now trigger our 2+2+1 cycloaddition followed by another Diels-Alder type reaction to give us the corresponding hexa-substituted benzene. So we made a lot of substrates. You can see here the alkyl substitutions work very well. We can scale it up to a gram scale, and we can have several alkyl substitutions, chloro, free hydroxy group, ester, cyano, all works pretty well. And it is also compatible with aryl functionalities. So we took one step further. Can we substitute sugars and make like multivalent sugar compounds on benzene? Okay. So these are lectin binders. So they bind, lectins are specifically going to bind with carbohydrate fragment. So what we did was to prepare the corresponding 1,3-diene with glucose, fructose, galactose, and mannose. And we showed that all these couple to give us the corresponding hexa-substituted benzenes with sugar decorated on the peripheral. And they gave pretty good yields as well. Now the story is, both the ends are symmetrical. What happens if these two are not the same groups? So theoretically, there are 8 possible combinations that you will get as a 8 isomers you should be getting. So let's say if I take the first example, where this is phenyl and butyl in these two ends, I can have 8 possible combinations. And when we do this reaction, we get all the 8 possible regioisomers. So it is very difficult to control this reaction. So what we thought was to bring in some stereoelectronic effects in those reactions. So we started to introduce bulky groups. A terbutyl group. A terbutyl group will never like to be in this position because it is going to have a lot of steric hindrance. So it will always try to be in the peripheral of this alkyne. So we can clearly see that there is a single regioisomer with greater than 95 to 5. Similarly, if we add silyl groups, the silyl group also provides pretty good selectivity. Now, what about the electronics? So if we substitute it with aryl and an ester group, aryl and ester group, generally the ester substituted double bond is electron deficient. So they are going to preferentially, the nickel is going to preferentially add to the electron deficient triple bond basically. So the ester functionality is going to get in, and so this is going to be here, and the aryl group will go to the periphery. So this is how the stereoelectronic effect of this reaction generally works. So we have very good selectivity in these cases as well. Fine. So if we look at the mechanism is very complicated. As you can see that there are several pathways involved. We actually did the calculations, but I'm not going to go through this. But I'll present a very simple sort of mechanism here. So where we form the nickel 0, and then this coordinates with the triple bond. So this does a 2+2+1 oxidative cycloaddition to give this sort of an intermediate. So there are 3 possible intermediates that we can get, and only one of them will go further to react to give us the hexa-substituted benzene of this type. So, but the situation is pretty complex when we consider all the pathways. So, yeah, so this brings me to the end of this section. I'll just briefly tell you what we are trying to do here. So here we had aldehyde and alkyne, and here without alkyne. So here what we are trying to do is we are trying to add aldehyde and alkene. So aldehyde and alkene are very difficult to add because alkene's pi star orbital is pretty high. It is very difficult for the nickel to access this pi star orbital. So because of this reason, we tried to do this reaction intramolecularly. So my student Sito here, who tried to do this reaction to get the corresponding chromanol derivatives. So these chromanol derivatives are very prominent in natural products. So the key intermediate is like where the nickel adds to these pi systems to form this 5-membered 2 plus 2 plus 1 adduct here as well. So, sorry. So what is the challenge in these substrates? What is new here is that generally in the literature, when we see that, here we don't have any heteroatom here. When we introduce a heteroatom, the metal adds to the double bond to form an allyl like a Sujitros type dealylation. So generally this is the side product that we get. So this is the main challenge to use these as substrates. So here what we have done is we tried to add a Lewis acid to increase the electrophilicity of this aldehyde so that this sort of 2 plus 2 cyclization happens in these cases. So with this, we have made several substrates. I'm not going to go into this. So the synthesis of anti-asthmatic drug is what is shown here. So we use this intermediate. We used our methodology to make compounds of this type. So the mechanism is very similar in this case, where the nickel forms nickel 0, and it undergoes 2 plus 2 plus 2 addition to give us this intermediate. And this further opens up to give the corresponding chromanol. That's all. So totally, I've shown you that we can access these building blocks, all these 4, using oxidative cycloaddition reactions. So I'll stop here, and I'd like to thank my students. This is my group. Today I presented the work of Rajesh, Aki, and Sudipto is here. Yeah, so these 3. And I thank the funding body, SCRB and STARS and IIT Kharagpur for the funding. Thank you very much. Thank you all. Thanks.
Thank you. You have finished well within the time, actually. Okay. Any questions?
I think they are awake.
Everyone understood everything.
It's fine.
Any question from front bench? No, everything is clear. Sad.
If somebody has to ask, I can ask this question. Of course, this is a very, very interesting work with using nickel 0. And my point is very simple, that can we make it even more stable than what you were able to achieve 200 days kind of thing? And still there are issues with the air, there are issues with water.
Yes.
Can we make stable nickel complexes like nickel acac, for example? It's an extremely stable molecule. I also handled it. But well, you might comment on that, making it even more stable than what it is.
The problem with making it more stable is that it won't decomplex very fast. So we need the ligand to come out of the complex.
Like so nickel acac, for example, nickel acac is extremely stable, so it doesn't work at all.
The reduction capability of nickel will come down quite a lot. So nickel is superior than palladium because of its reduction capabilities. It can do oxidation very strongly. So so that
industry will love nickel, but they are forced to use palladium. That's the idea. Actually.
But palladium is robust. So
robust, but then palladium is very costly. But did you work on some hydrogenations on this kind of
No,
thing?
I have not ventured into hydrogenation. Mostly we are focusing on cycloaddition reactions.
Good.
Thank you.
Okay, thank you.
Thank you, sir. Thank you, Dr. Ganesh.
Thank you.
It's a token of appreciation.
Thank you. Thanks.
Thank you. Thank you. So with this, I think we are ready for lunch. Enjoy the lunch.
Ganesh Venkatraman.
Thanks. Welcome back, everyone. So in this session, we will have about 6 speakers. The first speaker is a plenary lecture by Professor M.G. Sethuraman. So Sethuraman sir is a very senior professor, and he has a teaching experience of about 33 years and research experience of 37 years. So the notable, so he has published around more than 150 papers, and notable awards are like he's listed as a top 2% of world scientists by Stanford University, and several other awards as well. So I invite Professor Sethuraman to deliver his talk. Thank you.
Okay, sir.
Call on mic. Call on mic.
Yeah. Okay.
So they will control, sir. Just hand over. Yeah. That's okay. It's okay. They will control.
நான் மூவ் பண்ணிட்டே இருப்பேனே பரவாயில்லையா ஓகே ஃபைன் not moving. At the outset, let me thank Dr. Sivakumar and his team for giving me an opportunity to stand before you and present my little work on carbon dots and their supported composites as electrocatalysts towards clean energy production. Now, we have been doing little work on this area of carbon dots for quite some time now, and this is an offshoot of that work. Can you move to the first slide? No, it's not moving. Huh? Somebody came and got it. That's already given. You want it again? No. ஒரு நிமிஷம்
நீங்க ஆன் இது ஆன் பண்ணணும் சார் அக்சஸ் கொடுங்க டிரைவுக்கு
வரலையே யாருக்கு எனக்கா
இல்லை சொல்கிறேன் பயந்து கிளாஸ் அட்டென்ட் பண்ணல இப்போ அங்கே உட்காந்துட்டு சார் ஒன்லி 3 minutes லெஃப்ட் அப்படின்னு சொல்லிட்டு சான்ஸ் வச்சுருக்கோம்
ஓகே டன்
டன் Can we have the slide?
பாத்துக்கிறேன் நீங்க பாருங்க
நாம கஷ்டமாச்சே
ஒண்ணு இல்ல வந்துரும்
இருக்காங்களே உங்களுக்கு இது வேணுமா வாட்ஸ்அப்ல வேணுமா வாட்ஸ்அப்லயும் இருக்கு
இல்ல நான் கனெக்ட் பண்ணலாம் ஒண்ணும் இல்ல நீங்க பாத்துக்கலாம் நீங்க சும்மா பேசிட்டே இருங்க சப்போஸ் பண்ணிட்டு
Friends, we all know that depletion of fossil fuels and raising demand for energy are the major challenges that we are facing today. Of course, next 3 decades, the world is going to see a 50% increase in the world energy consumption, and 95% of this energy is now being met only by the fossil fuel. and the need for energy sources has increased the interest exponentially in the branch of energy protection and conservation. And among the various methods that are available to solve this, resolve this crisis of energy, we have the electrocatalytic water splitting being projected as a good solution for the production of hydrogen and oxygen, which serve as a fuel and feedstock for the chemical industry. So this production of hydrogen and oxygen by electrochemical water splitting assumes greater importance because of the almost negligible environmental pollutions. Now, if you look at this water splitting reaction, it has two half reactions. One is your OER, oxygen evolution reaction. The other one is the HER, hydrogen evolution reaction. So this is actually considered as a clean and green way for the production of hydrogen, your HER. And this electrocatalytic reaction, if you look at, has actually a serious disadvantage of being, having a very sluggish kinetics. So people try to hasten the reaction by using platinum and its composites as an electrocatalyst. But the problem with platinum, you know, is the high cost and all that. So people are looking for other alternatives, including transition metal electrocatalysts and others. And what we have done in this study is we have actually taken the carbon supported materials, and in fact they are being used here as in the formation of composites along with palladium and other metals, and we are actually trying to use this as a electrocatalyst. And again in the OER also, the tremendous need for energy source has increased the interest in the field of energy production and conversion. So OER is actually done, and this oxygen evolution reaction, if you look at, ruthenium and iridium are actually used as the noble metals. So for catalyzing the reaction. And again, people are trying to have cost-effective, earth-abundant OER catalysts to accelerate the reaction in the high-performing level. And if you look at the alternatives that are being, looked into are, carbon dots is actually one of the promising alternatives, actually, looked as a material. So this is actually sp2 consists of sp2 hybridized carbon atoms, which has a size of less than 10 nanometers. And the advantages with carbon dots is it has got greater solubility in water, easy synthesis is there, biocompatibility is there, eco-friendliness is there, functionalization is there, and it has excellent photostability, and fluorescence emission is also there. And if you look at the methods of synthesis, it is very easy, like all your Bajaj advertisement where you say, shut it, forget it. Okay, fill it, shut it, forget it. All that you need to do is let's take an autoclave, put it inside, and then what? By hydrothermal expansion, method, you can easily, prepare it. So solvothermal methods, micro methods, and ultrasonication are the very popular methods for using carbon dots. And if you look at the carbon dots, they have got wide applications. Like one is they are actually used as sensing. And we ourselves have reported sensing of even Fe3+. And the energy production as supercapacitors, actually there. Catalysis, n number of applications, papers have come. In phototherapy, of course, carbon dots actually have characteristic fluorescence with even cancerous cells. They are actually used as theranostic agent, therapeutic agent, and diagnostic agent. They have got cytotoxicity also. So in bioimaging studies people are actually able to identify cancer cells using carbon dots. For dye degradation, that is actually used. For storage applications, it is actually used. So a number of uses are there. So what we have done is actually use these carbon dots for preparing composites with metals, and we have actually tried to use them as electrocatalysts in the HER and OER reaction. Being a natural products chemist, so we thought that why don't we actually use carbon dots from natural sources, and number of natural sources are available for the preparation of carbon dots. What we have done actually is from Morinda citrifolia, we prepared the green extract, and actually we prepared the carbon dots. So what we have done is like we have prepared nitrogen doped carbon dots. So for enhanced fluorescence and other properties. So NDCDs we have actually prepared, and we have actually made a kind of composite with palladium. So palladium, nanopalladium, and NDCDs composites we have prepared, and we have actually analyzed using the TEM analysis. If you look at the size of the particle that we have prepared is around 4.6, and it is mostly amorphous in nature, and we are able to do the XRD analysis. We are actually able to confirm the crystallinity of the palladium particles, and we did the EDAX also. We could confirm the presence of carbon, nitrogen, oxygen and palladium, and then we found out the FTIRs. We actually found out the functional groups which are there. See, because they are actually obtained from the natural sources, so such of those functional groups which are there in the phytoconstituents are also there on the surface of the doped carbon dots, and we actually had that CH, CO, CN and all that is there, and then we actually recorded the Raman spectra also, and we could have the D band and G band, and then we actually went for the UV visible spectra. Again we could have this N to pi star transition, pi to pi star transitions, and then we actually had the fluorescent dependent emission in the case when we recorded the fluorescent spectra. I am just going a little faster, and then when we actually did the electrochemical studies using glassy carbon electrode and using this as the working electrode. There is some problem with the, sorry, battery has to be changed or what? Anyway, fine. So using silver chloride as the reference electrode and platinum electrode as the counter, we actually did the electrochemical studies, and we were able to see, when we actually performed the TAFL plots, we were able to see that these are the TAFL slopes that we have given, and then we actually did the LSP studies also. If you look at the bare glassy carbon and bare platinum along with the NDCDs coated over glassy carbon electrode and then this composite coated, we could see that it has got lesser onset potential, one. Now, apart from that, we also had lower over potential, and the TAFL slope also was the least when compared to all this. So, all these things actually qualified these composite to be a better electrocatalyst than the pure metal as such, palladium as such. And then we actually did the impedance studies also, and when we actually did the impedance studies, we could find out that the total resistance is much less when compared to the bare GC. So that actually again proves the electrocatalytic performance of the composite that we have prepared. And then we actually found out the electrochemical surface area from this, using the CDL values and the specific capacitance value, and we were able to calculate the ECCA as 0.15%. That actually decrease the charge resistance and enhance the HER kinetics. We actually found out the stability of the electrocatalyst by doing chronopotentiometric studies for over 24 hours even, and it was actually found to be very stable. And not satisfied with that, we thought we will just couple palladium along with copper, and actually we tried to make a catalyst, a better electrocatalyst. So this palladium copper alloyed nanoparticle was actually chosen, and again we had a composite with NDCDs, and then this was also studied. And this is the kind of study, the TEM image, and this is the EDS for this, and then we did the XRD also. Some problem with it. I'm sorry. So XPS also we have done, and actually we have done, we have proved the existence of palladium, copper, carbon and nitrogen in this, and then we actually did the Raman spectra also. And when we actually went for the electrochemical studies, we could see that. Can I have something else? Sir, there is some problem here.
It skips slides.
Yeah.
Just press it lightly, it should be okay.
No, even then it happens. Yeah. Yeah. No, I'll try also. Okay, this is the LSP and TAFL plot for this. Again, we could see that this bimetallic composite that we actually prepared has the least onset potential, and the over potential was also much less. And the TAFL load, if you look at it, is only -88 when compared to the palladium this one. The other one, it was much higher. And again, the impedance studies also, we could actually find that. Can you move? Just go to the previous line. This is the one. Next one. We actually varied the next one. See, we did the electrochemical surface, active surface area also, calculation also, and then chronopotentiometric studies. Go to the next one. So what actually we could convert is like the nitrogen doped carbon dots, which we could synthesize from this Morinda citrifolia. We could actually characterize it, and then we could make palladium composite out of that, and we actually studied for electrochemical studies, and we when it was studied, go to the next one, we could see that it actually has the lowest over potential, Tafel value also is much less. When we actually compare the electrocatalytic efficiency of the palladium as such and palladium copper, and we see that when we are able to have the bimetallic one, the Tafel slope is much less, and again the over potential also is much less. The total charge transfer resistance also is actually much less. So we could project that this as a better electrocatalyst even compared to your single metallic nano palladium based composite. Next. Now what this we actually had it published in Hydrogen Energy. Next. Then what we actually did was we studied the OER reaction also. Of course, we took a different next one. We actually adopted a different strategy. We actually had layered dihydroxide, double hydroxides actually produced. This LDH is actually a kind of naturally occurring anionic clay material which actually has two-dimensional lamellar architecture, and this actually consists of a kind of brucite-like positive layers. And what we had actually done is next. We have prepared very easy methods. There are several advantages of using preparing the layered double hydroxide also. The hydrothermal method is there, urea hydrolysis method is there, number of methods are there. Next, what we had done is like the applications are again catalysts. They are actually used as catalysts, adsorbents, medicine, in variety of ways LDHs are actually used. What we have done in our study is next. We have actually taken the cluster beans, and then from that we prepared the NDCDs, and actually we took nickel chloride and cobalt nitrate, and we actually had prepared layered double hydroxides of nickel and cobalt, and we made a composite with the nitrogen doped carbon dots, and then we actually characterized that in the routine way like HR, TEM and all that. You can keep going. Next is XPS data, FTIR also, and then we actually went for, go to the previous one. We did the electrochemical studies. Again, we instead of the glassy carbon, we actually went for the nickel foam here, and then go to the previous one. We could see that in the case of this layered double hydroxide, nickel cobalt, the onset potential is much less. It is 1.552, and again the over potential also was much less. And then again, go to the previous one, the Tafel slope also was actually much less. So all these things actually demonstrate the higher catalytic activity of this nickel cobalt layered double hydroxides. So this is one of the new strategies that we have actually evolved. So this is layered dihydroxide studies are already available. What we have done is actually we have made a composite with the carbon dots, and that is actually done for the first time in our lab. Next. And then we did the impedance studies using that. We could see that charge transfer resistance is much, RCT values are much less in the case of the nickel cobalt layered double hydroxides. And then next, we did the electrochemical surface area studies, the stability studies we actually carried out chronopotentiometrically. Next, and this is the, we wanted to actually still go for a better studies. We actually thought we will replace cobalt with iron, and we studied the effect of that. Actually, we prepared the nickel iron layered double hydroxides with NDCDs composite. Next. And then we actually characterized it by TEM. Then we went for the EDS studies. Next. XRD, FTIR. Next. Then we did the XPS also. Fine, go to the next one. When we actually performed the electrochemical studies, next. See, what actually we could see is again, this has got a very least onset potential, And again, the over potential also was much less, and Tafel slope also value was much less. Then next, the impedance studies also we could perform. There again, the total resistance value and the OCP values are actually least. Next, and then next. See, look at this. See, we actually made a comparison between nickel cobalt layered double hydroxide and nickel iron, and we could actually find out that in the case of when we replace cobalt with iron, we were able to have. See, all these years, there have been studies where transition metal, there are some reports already available. When we make use of transition metal electrocatalysts, they are not that effective, and slowly reports are now emerging that when we make some composites like what we have done in this case, they can be effectively used as the electrocatalyst for HER and OER reactions. Next, this is one paper which we actually had it published in Fuel. Next, and this is again next for the overall water splitting reaction. Again, we did this scheme. We actually prepared nickel sulfide NDCDs composite, and we actually characterized it with SEM image, and then we took the TEM images all. Next, and then we did the XRD. Then we actually found out the FTIR, functional groups which are present. Next, then XPS also was done. Next, UV visible fluorescence and all that. Next, so look at this kind of the electrochemical studies results. Again, here the onset potential is much less, and the over potential is also much less. Again, over potential value, if you look at it, is we actually compared with nickel sulfide as such, NDCDs as such, and then when we actually made the composite, the value is only 173. If you take only NDCDs and coat it over the nickel foam, the values are around 461. And this is the kind of result that we are able to get after composite formation. Next, and then we did the impedance analysis also. There also we have got very interesting results. Next, see, this is that is with the HER. Then we actually did the OER reaction also. There also we are able to have in KOH medium we actually performed this using the 3 electrode system. Again, we had the onset potential about 1.47, and then over potential also was 1.49, which is least, and then Tafel slope also was very least. Next, then we did the routine studies, and we could actually go to the next one. We actually did the turnover frequency and Faraday efficiency also we actually found out. Next, and this is we were able to see that the nickel sulfide nitrogen doped carbon dot serves as a excellent electrocatalyst, and this actually is because of the fast charge transfer pathways that are provided by this. And next, this is the kind of conclusion that we are able to see. And when we just had the nickel sulfide alone, the value is around 66.95, but when we made actually a composite with NDCDs, it actually was brought down to 63.85. Next, and this is actually we had it published in Energy Fuels. Next, and this is another strategy that we had actually worked out. We actually took the 3 metal cobalt, manganese, chromium, LDH nanocubes we prepared, and then we performed the same study on nickel foam. Next, this is again characterization in the usual way. This is actually the synthetic part of it. Next, this is the XPS spectra. Next, the electrochemical studies, if you look at, we have compared the tri-metallic layered double hydroxides with the single one also. We actually used here in this case, instead of the carbon dots, we actually used molybdenum sulfide. That is the only change that actually we made. And in fact, when we actually use molybdenum sulfide, there are also reports that molybdenum sulfide is actually acting as a better energy carrier, electron carrier. So we actually used that, and we were able to get good results. This is another strategy. Apart from the carbon dots, we thought we will replace it by molybdenum sulfide, and there also we could get effective electrocatalytic performance. Next. So these are the results that we could get out of this. Next. This is the chronopotentiometric studies that we have done. Next. So Next. So this again we had it published in Energy Fuels, very recent paper that we have got. Next. See, this is apart from that, we actually thought that why don't we use as such the your transition metals itself. So we thought we will go for a new strategy. So we actually deposited the metals over the stainless steel mesh using a different strategy, using deep eutectic solvent method. Next, where we go to the next one. Next one. See, here we actually made use of next the choline chloride and urea as the proton acceptors and donors. You use the deep eutectic solvent system, and using this as the electrolyte, we could really have the iron nickel deposited over stainless steel, and then this actually system, the iron nickel system deposited over stainless steel mesh, was actually used for HER and OER reactions. Next. Again, this is the bare stainless steel mesh, so no significant morphology was there. This actually, after using the deep eutectic solvent, we could successfully deposit the over the stainless steel mesh, the nickel and iron alloy. Next. And then we studied the XPS. Next. And then we investigated that for HER and OER. We could just find out, that the ore potential value is, in the case of nickel iron deposited over stainless steel, it's much less. And in the OER also, the ore potential is much less when compared to nickel as such or iron as such or bare stainless steel or platinum. And then next, we did the impedance studies also. The charge transfer resistance value is also much less. In fact, it was 2.2 only compared to your iron or nickel. Next. So this was actually a good strategy that we have formulated among the various other strategies that we have actually developed. Next. So what we had done is we have actually done the overall water splitting reaction also. Next. Go to that. Again, next. Oh, I forgot. So this is the report that we had actually in the Materials Today Sustainability, very recent paper again, where we actually synthesized the nickel iron nanoparticles on stainless steel mesh using deep eutectic system or eutectic solvent system, and then we actually studied the HER OER reactions. Next. Now this is not satisfied with this. We thought, why don't we go for the study of HER OER using seawater oxidation. See, again we are actually now trying manganese nickel, manganese cobalt chromium, manganese nickel iron tri-layer double hydroxide systems using seawater oxidation in alkaline medium, and if that actually comes, probably that will be a kind of better study, and that will probably pave way for large scale implementation of this HER and OER reaction. One problem is there is a kind of hindrance from the chloride. Seawater contains number of chloride ions, so the evolution of hydrogen and oxygen may probably be disturbed to a larger extent because of the interference from chloride. So that is there. Next. So studies are there, and seawater oxidation is being projected now worldwide also as a good source for water splitting reactions. One is availability of seawater is plenty. Second is like good conductivity is there, electron transfer is there, higher activity is there, but there are also other problems including your chloride presence. So the presence of these interfering ions is going to face a problem. Once if you are able to devise some strategies wherein you are able to stop the interference from chloride, probably your HER kinetics, HER OER sluggish kinetics can probably enhanced using the appropriate electrocatalysts. So this is the kind of studies that we have made. Since the presentation is only 20 minutes, I thought I'll just rush up. Next, anything? So these are the publications that have come out on this area of water splitting in the hydrogen evolution reaction or oxygen evolution reaction. In fact, this we didn't start it as actually a work. We were actually doing only in the area of bioimaging, and then in sensor area, and then for bioimaging studies only, we were actually making use of it. So when we thought that there are some reports on the use of composites for HER and OER, we thought, why don't we actually make use of the carbon dots? And that has actually yielded the fruits, and we were able to have this many publications. So thanks for your presence and patience. Thank you.
Thank you, sir, for the excellent lecture. The floor is open for discussion. Are there any questions for the students? Please.
Sir, please, sir.
S-doped carbon dot.
Yeah.
S means sulfur, right?
Yeah.
Okay, so the coating will be like the previous technology, just cast coating or bond
Actually,
formation?
We thought we took the seashells, sir.
Okay.
Some of these seashells have sulfur compounds in them. So making use of that, we actually give the coating. The study is going on also.
Because with the sulfur, without sulfur, when you coat it on metal, the interaction will be different.
Yes.
So with the sulfur, there is a possibility of forming some bond-like thing.
Yes.
So whether you already have any
In fact,
speculative idea?
Yeah, we have some studies actually done with the prawn shells, sir, where we were able to have some kind of sulfide coatings themselves, and there is an improved performance also.
The sulfur itself will not oxidize to sulfoxide or sulfur?
No, it doesn't, sir.
Because of doping?
Because of doping. There was, in fact, when we sent one of the papers, this was one of the questions. So will it not get oxidized and won't it give out SO2? If that is the case, like even carbon dots, you have carbon. So there is every possibility of C itself becoming CO2, but doesn't happen at all, sir.
Free sulfur compound get oxidized.
Mm.
Here
It's not happening. Thank you.
If there are no further questions,
Yogesh.
I have been asking this question to many. I think so. The glutamate you use it as a ligand to prepare. So how does it differ from using just a metal salt or and a ligand? So why do we need to?
No, there were actually a report of preparation of similar composites. So we didn't go for actually this one.
Just wondering whether adding a ligand to a metal helps. Whether helps.
It really helps, sir.
Okay. So in terms of temperature and okay. Thank you, sir.
Anything else?
There are no questions. Please join me in thanking Professor Tetrahydrodibenzo. Yes, Paul, thank you, sir. Okay. So our next speaker for the session is Dr. S. Kavitha. So she is working currently in Central Manufacturing Technology Institute. Is Kavitha? Oh, okay. Yeah. Sorry. Yeah. And she finished her bachelor's and master's from PSG College and PhD from Anna University. She has published several publications, and she's a member of several professional bodies. With this introduction, I'll invite Dr. Kavitha for giving her lecture. Do you need the mic? Do you need the mic? Yeah. Okay. Thanks.
Good afternoon, one and all. I apologize for the delay for not giving my lecture during the morning session because my train was late by more than 2 hours. So let me go ahead with my talk. So chemistry people, please apologize. It's more of application related chemistry, I can tell. It's up to you. I leave it to you whether it is chemistry or not. You take the decision. So myself, Kavitha, I'm presently heading Materials and Metallurgy Group in Central Manufacturing Technology Institute, Bangalore. Ours is an autonomous body that comes under Ministry of Heavy Industries. And we always work in TRL level 4 and above. So that's what we are there for in India, especially both for the private sector as well as for the strategic sector as well as for the commercial sector. So let me go ahead. See, basically, this particular topic, pack cementation, I think all of you must be knowing. It's regularly used one in for industrial applications when you use metallic components in industrial applications. So this particular opportunity, I would like to thank BRC and the Department of Atomic Energy, who realized that we at CMTI could develop this technology and indigenize this technology. Basically, this technology was not available in our country, and since 2017, we have been involving and carrying out several experiments to indigenize this technology, and presently, it is CMTI is the only place where we take up this technology, and the components that I am going to present or whatever is included all belong to light water reactor assemblies as well as the nuclear submarine pump assemblies. Okay, so this is where, yeah. So I think can you go back? Oh, yeah. Oh, it's going faster. Yeah. So all of you must be aware what is pack cementation processing. It is basically a surface treatment process, and in order to enhance the surface properties of metallic components. And basically, aluminum is aluminization of the components is aluminum is the only metal which is used, I can say, I mean, vastly in the industry. And this aluminum diffuses into the substrate surface, and then it forms intermetallic compounds as well as aluminum-rich phases that gives the high temperature performance for these materials. So as I have said, these components, whatever has been projected or whatever we are going to talk here is all for strategic sector applications. So what do you get out of this pack cementation processing or aluminization processing is the oxidation and corrosion resistance and effective resistance to sulfidization, carburization, and hydrogen permeation. And basically, it is more reported for ferrous alloys because, as all of you are aware, steels are being more used for these kind of applications, as well as for the nickel, titanium, and cobalt-based alloys. So, yeah. So out of the various aluminization techniques, why pack cementation processing is very important. So what are going to be the advantages? So one is the flexibility, and whatever components which I'm going to show is around 1 meter in length, maybe more also. And then it is relatively easier than other processes listed out there. And then it is economical, because you get a uniform coverage throughout the surface of even complex components, and you have the better adhesion of the aluminized layer to the surface of the component. And then, of course, you have a very good uniformity too. Can I? Yeah. See, why we are going to speak more on alloy steel substrates. So because the aluminum intermetallic is interesting because of its low density, low production cost, good mechanical properties and high temperature oxidation corrosion resistance. So if you see these low alloy steel components are 30% lighter than stainless steels and nickel-based superalloys because of the lower chromium content and the density. And the formation of the dense and adhesive layer has been reported of diffusion aluminized layer has been reported for only alloy steel substrates. We have also done some of the experiments with titanium as well as stainless steel, and then we also observed the same kind of reports. What is reported here? Yeah, can you go to the next slide, please? I'm doing this one. Better only long press. So this is typically the process schematic wherein you have the substrate and the aluminizing mixture is placed uniformly, spread uniformly across the substrate, and the entire container having the substrate as well as the aluminizing mixture is loaded onto a furnace. The aluminizing mixture basically consists of aluminum powder. It can be pure aluminum or it can be a alloy of the substrate major component, which is basically iron here. So it is indicated as iron aluminum powder, followed by ammonium halide and inert oxide filler alumina. So what basically happens is, can you go to the next slide, please? Yeah. So the typical process flow is, as I have said, the preparation of the pack mixture, application of the packs mixture, and heating through a particular cycle in a controlled atmosphere, and cooling and post-treatment. So the diffusion process occurs across the surface, and it allows the penetration of aluminum and to the desired depth and within the substrate material. So depending upon the applications as well as the size of the component, the diffusion layer thickness which you really envisage for also is different. Thank you. Yeah. So this is the typical process precursors we have used. First one is the alumina. The second one, the iron aluminum process precursor, and the third one is the ammonium halide. So what are the different effects of the inert filler morphology? So because it has been increasingly, we could find reports. Basically, we were given only the some of the documents from Russia for optimizing this particular process. So we had to read literature, and then we had to come with a understanding with our collaborators or BRC counterparts, whether we can go ahead with this or we cannot go ahead with this. And so we could find that alumina morphology had a very important effect, because the surface to volume ratio of alumina is least for spherical, and because of this the contact between the aluminum and the substrate is also higher. So in our case also we insisted that this particular morphology would be beneficial for getting the best diffusion aluminization layer thickness. Yeah, next slide. Next slide, please. See, again, when you come to the role of ammonium halide, this basically acts as, all of you know, that it basically acts as the catalyst, and it accelerates the deposition process, not deposition, it is the layer aluminum penetration. And because of the decrease in the halide concentration, of course, the aluminization reaction will also slow down. And even if there is increase in soaking time, it has been observed that there is no increment in the layer thickness. And why even if you increase The increment in layer thickness with certain amount of ammonium halide was due to the increase in the halide vapor pressure, and the ions, as you can see, can escape out of the pack, and the ions can also react with the substrate element directly. So because of these reasons, we could see that there is decrease in halide concentration after a certain range with which there is reduction in the aluminization processing. See the process, no, again. Why don't you go? No? Previous to this? Previous to this? Yeah, next one. See, the primary role of aluminum is to diffuse into the base metal, and the rate of deposition of aluminum depends upon the aluminum activity with the surface, and it is directly proportional to the purity of the aluminum powder. Since all of you know that the cost of aluminum powder is very much high, then we go for iron aluminum compositions, and as reported, pure aluminum gives thick aluminum rich coating forms on the surface. So basically we use here a master alloy for our purpose too. Next slide please. So the effect of temperature and soaking duration. These were some of the observations from the literature we could take on effect of temperature and soaking duration. So up to optimum level, we could find there is increment in the layer thickness, and after which there is carbide precipitation and grain coarsening. So the reasons are at high temperatures, aluminum ion production decreases, aluminum powder viscosity enhances, and the formed aluminide layer can also hinder the diffusion of the new active aluminum atoms. And I don't want to go into carbide precipitate and grain coarsening because it's difficult. And as we go for high durations, the activator ion can escape through clay gaps. And even if you're going to carry out the temperature, process temperature as 900 degrees centigrade, then because of the a molten kind of layer appears on the sample surface, that is, it becomes shiny, the surface, and the surface becomes uneven, and also caking we were able to see. And the rate of active aluminum atoms increased, that is, adhesion phenomenon appeared on the surface. Can you please go to yeah. So this is the precursor weight % for different grades of steels and cast irons. Here, I would say that we have worked on B24V steel and SS316, not much, but B24V to a very great extent. So this is basically the from the reported literature. So they vary the precursor compositions as shown here for the different base metals. So can you go to the next slide, please? So these are the stages of the heat treatment which we are following, and then yeah, there are different stages. I don't want to get into the details because we have our own difficulties in publishing these results. Next slide, please. So again, when it comes to process know-how, what happens is aluminum halide vapor formation happens, and aluminum halide reacts with the substrate, and it penetrates into the, aluminum penetrates into the substrate. So one more thing what we have noticed while very little work has been published in this area, and then the effect of composition on the diffusion aluminization layer thickness. I think one of my colleagues will be doing his PhD upon. So this is very less literature is available in this particular area. Can I have the next slide, please? So this is the alumina particles which we have taken for our work. And as you can see, it is distorted spherical. Go back, please. And the particle size analysis also indicated spherical. This is a SEM image. Next slide, please. So the average particle sizes were analyzed for alumina. Can I go to the next slide, please? And with respect to the master alloy, iron aluminum, we had actually We actually place around 5 tons, 6 tons, and around 10 tons of iron aluminum powder. And there is, as of now, there is only one supplier for iron aluminum powder in India. And we have because when you come to industrial processing, the substrate material is very costly, and then we do not have the freedom to spend the precursors as well as the substrates for more of R&D. So we have to be very, very careful in preparing for the experiments or the batch processing. So with respect to iron aluminum, batch 1 which we have ordered, this was the average particle size reported. Can I have the next slide, please? So these are the SEM micrographs which had a uniform size distribution. This batch 2 I am not showing because that did not give a favorable appearance on the surface of the substrate. So can I have the next slide, please? So this is especially for batch 3, and I think a number of components have been diffusion aluminized using this particular batch 3 iron aluminum. Can I have the next slide? So this is though it has a non-uniform size distribution, we could able to get good surfaces which can be directly the cleaning process of the component after pack cementation, all of you must be knowing, it's very, very difficult, and especially for these kind of critical components, the finishing plays a very important role because these directly go to assembly of the components in the pumps or nuclear reactor assemblies. So can I have the next slide? So these are some of the observations. So only thing what I would like to tell you here is, based on the literature and based on our experiences, the alumina particle size should be lower than that of the iron aluminum powder particles because when aluminum starts to melt and then it tries to penetrate, so these alumina particles are nothing but inorganic fillers. So they are basically there to avoid the segregation of aluminum atoms, and in order to enhance the penetration of the aluminum onto the substrate surface. So we could observe particle stickiness less on the base metal surface, and the particle size really did not have any, because as you have seen batch 1 and batch 2, there is too much of difference in the particle size. So what we could observe it really did not have any significant effect on the surface finishing of the components after diffusion aluminization. So here you can see 2 different components. So you can see the tint, right? And even this tint, there was some problem in acceptance of these components, and finally we had to improvise upon the quality of the coating. And yeah. So this is the upper washer and this is the lower washer, and because the compactness which the aluminization precursor mixture is having with these kind of components is very, very important in deciding the diffusion layer thickness. It's very well shown in the average thickness observed for these 2 components. Can I have the next slide, please? So again, when we go for the hexagonal nut and the lock nut, we use both muffle as well as the pit type furnace, and this was the average thickness which has been reported, and the precursor composition is also shown here. And as you can see, in the case of muffle, always the average thickness is greater than in the case of pit furnace, because in a muffle furnace, you usually put a rectangular container and more amount of aluminizing mixture in comparison to the containers that are used in the pit furnace. So the availability of the packed mixture is more in the case of muffle, and hence we can observe the better layer thickness values. Can I have the next slide, please? So this is some of the case 4 wherein we have varied the compositions of the precursors and layer thickness values are reported. So in some of the cases, dark spots were reported, and we could observe that because of the impurity in the cooling medium, we observe these dark spots. And yeah, the consistency was observed for has been observed for similar compositions, which I have highlighted in blue. Can I have the next slide, please? So these are some of the, again, based on composition variation. Here you can see that increase in alumina gives more thickness than the decrease in ammonium halide, and decrease in ammonium halide significantly decreases the layer thickness because the activation is less. Can I have the next slide, please? So these are some of the observations, but we could not we could not hypothesize what we have observed. I mean, we are not sure about what we have observed. So we could see that in some of the, there was the thickness variation based on the component geometry. In some cases we have observed, but not in all cases. So I just put it there for only as an observation. So can I have the next slide, please? So we also, because all these precursor mixture will go to waste after the diffusion aluminization processing. So presently, we have observed that we can reuse the mixture one more time in order to get the adequate diffusion layer thickness. And this we could prove from the X-ray diffraction of the reused mixture as well as the fresh aluminizing mixture. Can I have the next slide, please? So these are the different experiments which we have done. Next slide, please. So based on the experiments which we have done, we could observe that this composition could give uniform diffusion aluminization layer with an average thickness value. And next slide, please. And the stickiness, as you can see, the regular test coupon as well as the experimental test coupon, none of the particles stuck to the component surface. Can I have the next slide, please? So in the case of experiment 2, the diffusion aluminization layer was not found to be uniform. This is because of the insufficient, because you can see 69.2% of iron aluminum in the pack. Can I have the next slide, please? And in the case of experiment 3, you have adequate thickness, so you have the average thickness, and there is only the difference between the furnace as well as the processing condition of the experiment 1 and experiment 3. Okay, so can I have the next slide, please? So these are some of the typical components that go into the reactor assemblies as well as the nuclear submarine assemblies. These entire things which you see on the left-hand side goes into a light water reactor, and the other one, what you are seeing, all the other things go to the nuclear fuel submarines. Yeah. Yeah. This is again one more picture. Next slide, please. So this is basically how the assemblies and how this is basically a stitched picture from an optical microscope. You can see there is uniform diffusion aluminization layer throughout the surface of the component. Can I have the next slide? So I acknowledge the opportunity given by CRSA local chapter and the organizing members and Director CMTI for all the support. Go back. Yeah, and my advisors and mentors at IGCAR, PSG Tech, NIST, CLRA, as well as CMTI, and DST, New Delhi, and all my students, friends who have been with me throughout. And next slide, please. Yeah, that's it. Thank you. Next slide. Yeah. Any questions?
Are there any questions? Yeah, it's a completely different domain, if you don't mind. Sorry, I don't think there is any questions. So I take this opportunity to thank Dr. Kavitha, and this is a small token of, please. So our next speaker is Professor M. Logesh from NIT. So he's currently an associate professor. Sorry, VIT. Sorry, VIT. He's currently an associate professor there, and he did his masters from Annadhasan University and PhD from University of Puerto Rico, followed by a postdoc in University of Florida. Yeah,
Florida.
Florida. Okay. So, yeah, with this introduction, I'll invite Professor Logesh to give a talk.
Good afternoon. Thank you very much, organizers, and thank you for the nice nice introduction. And thank you, Dr. Siva and Dr. Suresh, for your kind invitation and hospitality. And I especially would like to thank all the student volunteers who have done a terrific job, organizing this event. So today I am going to discuss mostly what I have done so far and a little about what I am planning to do. Okay, so this is like we have just started. Our lab is pretty young, and we are in the early stages of our research exploration. So, so exploring new avenues for transition metal pyrrolizolido complexes. So, so we are looking at polynuclear complexes. So we are basically coordination chemistry group, and we like to look at polynuclear complexes. Why polynuclear complexes? So they are basically everywhere. For example, one of the things that you would see quite often are single molecule magnets, which are manganese 12 complexes. You would see them in photosystem 2, which is manganese 4 and calcium cluster. You will also see in multi-copper oxidases where a copper 3 center is the active site. So you will see them basically everywhere, and that is kind of attractive to us. So we have chosen pyrrozole as our ligand. So what is, a lot of you know what pyrrozole is. It's a polyaza heteroaromatic family. It belongs to that family, and it is a 2 nitrogens adjacent to each other. So as you can, and this is in the family of triazoles, tetrazoles, etc. So when the proton, with the proton present, it is a monodentate ligand. So when you remove the proton, it becomes pyrrozolido or pyrrozolato. So the literature is full of both of these names. So it can bind more metal atoms. It can bind 2 metals at the same time in an exo fashion. Okay, it's pretty sensitive or not. Okay, so it will bind 2 metals at the same time. So this is what makes it very attractive to us, and it can lead to lots of different architectures. So they have probably synthesized these complexes back in the 60s, and even after 60 years, we keep digging out new and new molecular architectures. For example, so we have Professor Jellet Mezei from Western Michigan University, who prepares nano jars. He can basically incarcerate anions inside them. So you can he could trap tetrafluoroberylates or chromates or any other toxic materials with a tetrabutyl ammonium as the lead. So this is one of the architectures, and these are all pyrrozoles. So they are copper 31, copper 29, some magic numbers are there. And you also have a octanuclear iron cluster, which has it is chiral by design. It is chiral. It can be either delta or lambda, and it is redox active, and it has paramagnetic properties, and it can be applied as an MRI contrast agent. You also have a hexanuclear copper pyrazolate complex. So here you can see there are two types of pyrazole. So there is a simple pyrazole, and there is a 3,5-diphenyl pyrazole, which acts as a clip, and it binds 2 triangles together. And this one is also redox active, and you can convert them to you can oxidize it twice over. So it is a copper 6 12 plus, and you can go to 13 plus and 14 plus. The extra charge is delocalized across the 6 copper centers. These are the two views. If you look at them on sideways, and this is a trigonal prismatic structure. So copper pyrazolates is what I have done. Most of my research in. So they are very easy to prepare. So they are self-assembly reactions, and you have three handles, major handles. One, you have an E, which is a capping ligand, and you have terminal ligands. So you have and you also have 4 positions. You can also modify this in these positions, and it can lead to various other geometries. So with oxo core, when it is oxo core, it can be oxidized. So you will reach a copper 3 7+ oxidation state. So I would like to show two examples of how we have used the versatility of this triangular unit into one building a catalyst for nitrate reduction. So in this one I am going to show how the electronics can be controlled. Okay. So this is a nitrate compound. So you have terminal nitrates. It is also easily prepared. You have terminal nitrates, and so this is the crystal structure, how it looks. So you have two binding modes. One in this mode, a bidentate mode, and you also have a monodentate mode. So this can be oxidized. Like I told you, it is like purple in color, and when you oxidize it by 1 electron, it becomes a deep brown color, and it also shows a interesting intervalence charge transfer band in the near IR region. Okay. So this, because we have a nitrate ligand, so you can see. So the by changing the R groups on the pyrazole and also the terminal ligands, you can vary the this redox potential, the copper 3 to copper 3 6+ to 7+, all the way from plus 476, where the terminal ligand is an acetate, to almost instantaneous oxidation at minus 0.133. So this is the easiest oxidation that we have found so far. You have nitro groups, aldehyde groups, you have isocyanate. So there is a rich chemistry in all these complexes. So this is another variant where you have the 4-phenylpyrazole. This can also form. So this is a slightly different one, but what we are going to show is that this nitrate, because we have seen nitrate is a part of an important biogeochemical cycle, where it is part of a nitrogen fixing cycle. So it goes all the way from nitrogen to nitrate. So this nitrate can be reduced to nitrous oxide or nitric oxide. This is since nitric oxide is also a biologically and medicinally significant reagent. We wanted to see whether we can oxidize, we can reduce nitrate to nitric oxide in our complex. So it can be done as it can be simply reduced using thiol, okay, thiophenol or even acetic acid. Both of them will reduce, and the reduction or the NO release can be seen as in this picture. So the nitroso groups goes and binds the tetraphenylphorphyrine cobalt complex, and you can see the shift. So I think I have missed. So what I basically wanted to show was this complex has two roles. It has played, so we could actually control the geometry. We could control the electronic structure by we are getting oxidation from easy to hard, and we could also have a catalytic property. So the next one, I am going to switch gears and then show a high pressure studies. So in this study, what happens? Okay. So we have taken this triangular building unit and then attached it to this flexible linker. So this is a trimethylene pyridine, bipyridine linker. So you can get 1D chains and also 2D chains, 2D sheets. So this is more geometry. So these are all, you can, in 2D sheets they actually stack one over the other. But the interesting point that we wanted to show is that because of these flexible groups, we wanted to see whether this flexibility can be observed by crystallography. So you can place this in a diamond anvil and apply pressure, and you will see, as we could show here, it goes from all the way to 0 GPa, gigapascal, and here we went it all the way up to 8.5 GPa. So this actually compresses, which we can show by the shift in these peaks. So up to about 4, I think about 4 GPa, this is reversible. So beyond that, it becomes completely amorphous, and you cannot retrieve it. So this work was done with Dr. Vadim Drad, and he works in a center named as Matter for Extreme Conditions. So this is a very they study at extremely high pressures and temperatures. So that was with powder XRD, and can we see this by single crystal XRD? So with the collaboration of Dr. Christine Beavers at UC Berkeley, so she could actually take single crystals and keep it inside a diamond anvil, and she could not reach it all the way up to 3 GPa, but we could show up to 1 GPa. She could compress it up to 1 GPa, and it is the principle is the same, but instead of powder XRD, we are shining a synchrotron, which is a high strength radiation at this crystal. Yes, either that or this. I will stop it here. Okay. So the blue one is the ambient pressure. The blue structure is the ambient pressure that was recorded at the our facility, at our lab facility, and red one is at 1 GPa. So 1 GPa, and you cannot see much huge difference, but you could see some of the, so these all these units are closer, slightly closer by angstrom, so very small amount of differences. And this is not groundbreaking, but you are actually showing that the aliphatic units are flexible in experimental means, through experimental means. So what are we planning to do, and what we have done so far is that so these are from so far my postdoc and postdoc work, and what we are trying to do right now is to start with other transition metals. For example, zinc. So zinc MOFs are well known in the literature. Perhaps they are the most common metal organic frameworks, because it is neutral, it is cheap, all those things. But pyrozolites are not that common. So why is that so? These are known to be polymerized. They will polymerize quite easily, and then because of the polymerization, their solubility is also quite low. So what happens in this polymer? So this was published back in 1999. So, and we do not have much many more examples of this. So you just get a single chain, and this structure was obtained from powder X-ray diffraction. So can we isolate either a dinuclear or trinuclear complex of this zinc is our goal. So we started using self-assembly reactions of pyrrole base and a large counterion, for example tetrabutyl ammonium hydroxide, and we were able to isolate a dimer, a dinuclear complex containing chloride. So we can in fact isolate dimeric unit. And we are going to, these are unpublished research, and we are going to see whether this can be used for catalytic or fluorescence purposes. So we also want to move on to other transition metals, for example cobalt, which so this is a cobalt trimers of course are also known, but these unsymmetrical cobalt complexes with 1 chloride and 2 pyridines are not well understood, and they can have interesting magnetic properties, because magnetic properties are catalytic properties. So this is how it looks in both views. So like I told you before, so we are exploring other transition metal pyrrolate complexes, both homonuclear and heterobinuclear complexes. Alkali and alkaline metal pyrrolates, they are of interest in terms of energetics. Pyrroles we can also prepare energetic materials using pyrroles, and what can we do with alkali and alkaline earth metals. And we are also looking into catalytic and electrocatalytic properties of these pyrrolate complexes. And we also want to explore new ligands to prepare polynuclear complexes. With that, I would like to acknowledge Vellore Institute of Technology and the seed grant from them, and Florida International University, who are my hosts of postdoctoral studies, and this is our current group. one more new student is missing, but thank you all for your kind attention. Thanks. I'll be ready.
Thank you. Are there any questions? Questions from the students? Yeah.
Zinc what? Yes. Yes. It is not stable in water, but the good because this is we all of what we have done, they are in organic solvents, and they may not even dissolve in water. But we can. The one good thing about this pyrazoles is that you can prepare water soluble pyrazoles with an ethanol arm. So when you prepare the same complex with the alcohol substituted pyrazole, it can be water soluble. So the chain that I showed is an 1D chain. The complex is isolated, of course. That's a 1D chain. No, I am not planning to, because there are zinc 3D materials are very well known. So you would see like bipyrazoles, tripyrazoles, and even one of the most popular MOFs. Okay, so they are made from pyrazolate ligands, but they are bipyrazoles. So you will see a lot of them. There are lots of examples, and I do not want to get into what's already well known. Thank you. Which one? Which one? Yes, yes, they are very well. They are published. They are published. Yes.
Right. If there are no further questions, let's thank Professor Lokesh.
Yes.
And there is a small gift from the organizer side.
Thank you.
Yes. Right. So our next speaker is Professor Anandan from University of Madras. So he completed his PhD from University of Madras and went on to do a postdoc in NTHU, Taiwan. Currently he is working as an assistant professor there in University of Madras. I request him to start his talk. Thank you.
Thank you, Dr. Ganesan, for your nice introduction. Yeah. Thank you, Dr. Ganesan, for your nice introduction. So very slow. Slide movers. First of all, I would like to thank Dr. Sivakumar, who gave me opportunity to stand in front of you, and I will extend my thanks to CRSI for this opportunity. So what I'm going to talk today is that visible light or electrochemical catalyzed radical cascade cyclization of ortho-alkylated benzamides. So before going this talk, just before going to talk, just I would like to give outline of my presentation. My first presentation is going to talk about the role of cyclization. So then the reactivity of ortho-alkylated benzamides. So then followed by I will talk about our work, which is the chemistry of cascade radical cyclization, which is going to be talked today. So if time permits, so I will discuss that chemistry of copper phenylacetanilide, or then chemistry of oxidation using molecular oxygen, and chemistry of oxidative cyclization. So finally I'm going to end up with acknowledgement. Yeah. So what is the rule of cyclization? We know that it is the well-known textbook chemistry. So I'm going to start with textbook chemistry that Edwin Baldwin, he is the British scientist. He proposed a cyclization of acyclic molecule. So what he proposed based on this, he has proposed three prefixes. So one is that size of the ring. So when it is making of this cyclization, the nucleophile has to attack to the electrophilic nature of this one. How much of this ring is going to be making? Either we are going to make starts with 3-membered, or if it is 4-membered, and then we can make it 5-membered. So that first prefix we are going to fix with how many number of the sides of the carbon we are going to make it. The second one, so a ring closer. So how we are going to close the ring? Whether we are going to close the ring is the substituent which is going to be getting out of the ring, so that you can call it as exo. Or if the substituents are inside the ring, so you will call it as endo. So these two parameters you can use it either exo or endo. So third parameter, the third prefix is nature of electrophilic carbon. So you can see that this nucleophile is going to attack this electrophilic carbon has sp3 carbon. So that means we can call it as tetrahedral structure. So that means we can call it as a tet. Or if this nucleophile attack to the sp2 carbon, that is called trigonal. So that means we can call it as trig. If nucleophile is going to attack with sp carbon, that is diagonal, we can call it as a dig. So if you have any kind of cyclization, we can finish it with 3 prefix. So that we can identify how the cyclization is going to be happen. So this is the rules for the cyclization. So based on that, all the possible cyclization with exo and all the possibilities of endocyclization which are presented here. Among these, so you can see that for the 3-membered cyclization, it's very difficult to make it endo. So we can start with exo, so that's we have possible, but generally 3-membered cyclization little difficult because of this ring strain. So it is the what are the more probability of making of the cyclization? You can start with 5-membered and 6-membered. Even 4-membered also little difficult, but it has many cyclization. But its easiest way is making is 5-membered or 6-membered cyclization. So either exo or endo, you can do it. So that is our idea to how to cyclization. So based on this idea, we have started of thinking the cyclization. For that we have chosen ortho-alkylated benzamide. So why we have chosen of this ortho-alkylated benzamide? Because we have 3 parameter, 3 points, which are generally, if you know that the nitrogens are more nucleophilic than amide unit. So that was our idea. So why not we can make it the amide as a nucleophile? So the second thought is that once if it is making of this amide nucleophile with the help of base, it generates amidyl N nucleophile. So this N nucleophile have one more resonance. It makes O minus. So it has undergoes a resonance, the immunol O minus. So that we can have 2 nucleophilicity, one is nitrogen nucleophilicity, another one is oxygen nucleophilicity. Can we make it both nucleophilicity? It can attack to the triple bond, which are electrophilic in nature. So we can cyclize it. So that when if you are considering this, the nitrogen is the nucleophile, we can attack to this ring, so that double bond is getting out of the ring, so that we can call it as a exo. So where is the sp3 carbon? So this is sp carbon. So that means we can call it as a dig. So that means we are going to make it 5-membered exo dig cyclization. You will end up with isoquinoline structure. The same way, if whereas the nitrogen nucleophile is attacked to this sp carbon, so you will end up with 6-membered heterocyclic. So that means isoquinoline structure. So the another way, if undergoes resonance, it makes O nucleophile. So O nucleophile can undergo 5-exodic cyclization as well as 5-endo-6 cyclization. As a result, you can see that you will end up with 5-membered and 6-membered. In a single molecule, you can make it 4 different heterocycles. So that we can able to make it. So why this is the important? You can see that all the 4 heterocycles has many biological activities. So whatever the presented here, I picked only 3 examples for each and every heterocycles. So you can see that it has antifungal, antimicrobial, anti-cancer activities. So we have natural products. So like that, all the 4 heterocycles has all the 4 heterocycle has biological important molecule. So that is the reason. So we have started our research that they have some computation how to control this nitrogen nucleophilicity and oxygen nucleophilicity. Is there any controlling factor to control the competitive reaction of this N and oxygen? So that's we started off doing literature. So based on this literature, we found that if you want to make it N nucleophilicity, amide nucleophiles, just you can react with base. So this amide nucleophile, so the nitrogen NH is abstracted by the base, will generate carbanion, N minus, which are going to be attacked. If it is attacks, this sp carbon will end up with 5 exodic cyclization of 5-membered ring. If attacks to terminal sp carbon, you will end up with 6-membered ring. So that's easy way. So how to make it O nucleophilicity? So when started off doing literature, so we found that along with base, just we can introduce some electrophile. So what will happen this electrophile? How it is going to be makes O nucleophile than N nucleophile. So what will happen when it is this electrophile? So first it's going to attack to the triple bond. It makes a coordination. So when it is making of this coordination, its triple bonds makes electron deficient in nature. So once if it is electron deficient, so this electron when it is coordinated here, so this makes electron deficient. This nitrogen, that whole system becomes electron deficient. It pulls down the electron density. When it is pulled down the electron density, this N minus nucleophilicity is going to be diminished. So then the reason why you will get O nucleophilicity. So after this O nucleophilicity, it's going to attack either exo or endo cyclization. You may end up with 5-membered or 6-membered cyclization. So this is the basic literature. So this, but have any lot of reports are available. So what we thought, so why not we can make it N radicals, so amidal radicals. So that was our idea. So this having N nucleophilicity, O nucleophilicity has number of publications. So that's why we started off thinking to make it of N radical. So that's we have started this one. If you want to make amidal N radicals, so you need a radical initiator. So the radical initiator can undergoes homolytic of this NH bond to make N radical. So that we can do it. So as well as the same time, what will happen, this N, the radical initiator, which also going to be interact or reacted with this triple bond, you will end up with non-cyclized product majorly than cyclized product. The possibility of cyclization become very less. So we thought that, so what is the condition to make it N radical followed by the cyclization? So that's, we thought we need to do some ambient condition so that we are going to make N radical. So followed by the cyclization, that's our idea. So that's, we started off photochemical condition. So this photochemical condition easily will make the N radical. So then followed by, we'll do cyclization. That was our idea. We started, but when you are doing the started of the literature, so if you want to make it of amidal N radical, so you have to, that literature report says that you have to make functionalization. So you have to make functionalization of NX bond, halogens or bromination or iodination. Under photochemical condition, we can make it amidal radical. Or otherwise, you can make it NS bond. Then you can do homolysis, you will get amidal radical. Or otherwise, NO bond as well as NN bond. So these all the conditions when you are radiation of light, we can able to generate amidal radical. But what will happen when it is NH bond? It's very difficult because if you want to make it of NH bond in homolysis, the homolytic cleavage to make it amidal radical is very difficult because this bond dissociation energy is almost 100 kilocalories per mole. So that means how to making of this one? So this is, they have some process which are proton coupled electron transfer. What is the proton coupled electron transfer? So this, initially this proton is going to be coupled, removed, then followed by the electron is going to be removed. So that is the step-by-step process. First proton is getting removed from this NH bond, then followed by removing of one electron. Or otherwise, first you have to remove your electron first from this NH bond, then deprotonation. So removal of the hydrogen. So you have to do 2 steps, either start from protonation or electron transfer. So this proton coupled electron transfer, the photochemical condition we can do in single step simultaneously. So that is the literature says. So based on this literature studies, we started why not we can do this kind of reaction. So that simply what, so our strategy is that just simply taking off orthoalkylated benzamides, just reduce the presence of acridine mesetyl dye, which is our photosensitizer, which are going to be absorb the blue light, visible light, which is going to be transferred to the substrate. So then we have used phenyl disulfide, which is going to act as a base. So that is going to abstract the proton, and that this photosensitizer going to be abstract the electron from this NH. So these all we have started off thinking, then we performed the reaction, then we nicely we get cyclized product. We thought that we are going to end up with cyclized, but after the cyclization we will get oxygen addition also. So hydroxy ketone also we are end up with this product. So this is the happen at 6 hours. So then, so we, the student, what happened, so he allowed more time. He forgot to stop it at 6 hours. So while started to optimizing the reaction, so he allowed to more time. What will happen? So he will end up with CC bond cleavage. Thalamide is the product, he's end up with this one. So here what we did, we tuned the time tunable synthesis of these 5-membered or thalamide synthesis. So that happened. So what's here, the R2 become RL. If you are taking R2 become RL, we will end up with isoindolamine structure, then thalamide is the structure. So the second one, so if it is alkyl unit, so you will end up with 6-membered cyclization. So this is the one we have important of this reaction. When it is the substituent, when it is controlling the cyclization of the 5-membered and 6-membered is going to be happen. So based on this one, we have started, sorry. Yeah, so we have that optimized tables. Then we have nicely tolerated all the functional group, electron withdrawing group, electron donating group, both are going to be tolerated very well. We have good number of derivatives we have succeeded. So then based on this control experiment and literatures, what is the, why it is the 5-membered cyclization, why it is 6-membered cyclization? Because of this stability of this benzyl radical stability. You can see that if the R2 become phenyl, so you can see the phenyl radical, the toluene phenyl C radical is getting stabilized. 2 minutes, okay. So in the case of alkyl, you can see the phenyl group which are directly attached to the CH, this radical is getting, benzyl radical is getting stabilized. So that is the why reason of this 5-membered, 6-membered is going to be happen. So, this was published OL. Then after that, what we thought? So we can, why not we can do cyclization in between to make it quinolinone. Then followed by this either do exo or endo dick cyclization. So that's we have started of taking off this orthoaminobenzamide or orthosulfonobenzamide. Then started with orthoalkylated benzaldehyde. So what will happen? So this 2-amide and undergoes condensation with aldehyde, which makes isoquinolinone or isosulfonoamide is going to be getting the product. So this one. So under our photochemical condition, so this NH bond is going to be ruptured, it makes N radical, which are going to be cyclized, we will get cyclization of this 5-membered 6 dick cyclization is going to be happen as this the product. So that is the one. So what is the beauty of this one? There has some competitive reaction of this NH and amidyl NH, which are going to be cyclization. In the case of amide, so it is going to be amide nucleophile is going to be attacked, it will undergo 5-dick cyclization. In the case of sulfonamide case, you will get N nucleophile is going to be, N radical is going to be attacked to the triple bond, will get cyclization. So this was published in OL. So this sort of time, so I'm going to skip. So then what we'll thought that, so we have got 2 publications from the photochemistry. Yes, sir. Sorry. Then we started to working on electrochemistry. So this electrophile, which are going to be coordinated on the triple bond, when it is this electrophile coordinated with the triple bond, O nucleophile is going to be attacked. So our idea, why not we can make it nucleophile, so the NX nucleophile, so we can make it in situ to generate electrophile under electrochemical condition. So that electrochemical condition, the electron is removed from this X minus, it generates X plus, which are going to be coordinated on the triple bond. When it is coordinated to the triple bond, so the O nucleophilic attack is going to be takes place. So that's we have succeeded, and then which was published in OBC. So this is the reaction mechanism. You can see that, so this sodium chloride, so when it is removed electron from the anode, it generates X radical. One more electron is removed from X plus, which are going to be coordinated with the triple bond, will get cyclization. The same way, so alkylated benzamide, where then we have performed reaction. Here, so under photochemical condition, first it is going to be cyclization, then followed by oxidation, addition of oxygen happened. What about electrochemical condition? The cyclization followed by reduction, we are end up this product. So that was published in ChemCom. So I think I finished my time. So okay, I will wind up this one. Okay. So this is the one which was published. So then we have other slides. So anyway, I'm skipping. So this is the common equipment which are used in our laboratory for photochemical and electrochemical condition. So finally, I would like to acknowledge our University of Madras gave the opportunity to perform research work. Then I would like to thank DST, SERB, UGC and RUSA for giving the funding opportunity. So these are my research group members. He is the first student, Bhargava Reddy, and then Prabhu. So these two are involving radical cyclization. So the remainings are working some other area. Yeah, thank you for your attendance. Yeah,
Thank you.
Yeah.
Probably we have time for one question.
Yes.
What is the role of phenyl disulfide? Phenyl disulfide used. What is its role? Disulfide.
Yes, sir.
Diphenyl disulfide used as one of the reagents,
yes, sir.
but it's not a part of the product. So what is its role in the?
Yeah, its role is that I will show the mechanism, because lack of time I could not able to explain it properly, because it's going to be it acts as a base.
Disulfide.
Yeah, it acts as a base. Just I will explain it.
Because disulfides are more prone for oxidation.
You can see that what will happen, this disulfide under photochemical condition, it undergoes homolytic cleavage, will get radicals.
Yes.
So this radical, you can see, undergoes that one electron transfer on this photochemical cycles, it makes phenyl sulfur anion. So this phenyl sulfur anion is going to act as a base to abstract this NH bond to make N minus. Then under photochemical condition, electron transfer is going to be takes place, which makes N radical.
So, but it's not part of the product.
No, we are not going to get any product.
Sulfide.
Yeah, no. We are
okay, so on the end of the reactions, disulfide gets cleaved, or it's again existing as a phenyl disulfide?
We are end up with the product is that thiol we get observed.
Thiol.
Oh,
okay.
That we got it.
Okay. So you did the same starting material with both for the photochemical condition as well as the electroorganic synthesis. Okay.
Yes.
So how would you the product
changed, how the products change in the photochemical condition and electrochemical condition.
Yeah, what will happen in a photochemical condition, some oxidation can possible. So that's where end up, you can see when it is cyclization, followed by this oxygen is the under oxygen atmosphere we have performed. So this is the oxygen source is going to be, oxidation is going to be takes place over here and after the cyclization. In electrochemical condition, there is no oxidation. Generally, electrochemical reduction is going to be takes place. After this cyclization, you can see this, after this cyclization, this double bond is getting reduced, will get reduced CH2 product. So that's the reason.
So finally, one question. So what is the atmosphere of this reaction? Where you carried out the reaction in the inner atmosphere, or is it just open air?
Which
For
one, sir?
photochemical?
Photochemical, we are performing under oxygen atmosphere.
Oxygen atmosphere?
Yes, yes.
So it won't any problem?
No, nothing will happen.
Nothing happen. Okay, thank you.
Even if you can perform under nitrogen atmosphere, there is no reaction. So that's the, actually
If you perform in the nitrogen atmosphere because the oxygen radical and redox disulfide is formed. Did you carried out any control experiment?
Yes, sir. I have.
Because most of the photochemical reactions are carried out in the absence of the
Actually,
oxygen.
so we have performed the reaction and instead of nitrogen we have used, there is no reaction.
No reaction. Okay, thank you.
That's we have.
It was an excellent talk. I'd like to thank Dr. Anandan for his excellent talk, and thank you very much. So our next speaker and the last speaker of the session is Professor Muthusamy from Azim Premji University. Professor Muthusamy started her career as a polymer chemist, as a PhD student in IIT Delhi, and then she sort of took an alternative career into teaching methodology. So now she'll be talking to us regarding teaching methodology as well. Over to you, ma'am.
லேசரு இது கரெக்ட் தானே எங்க ஒர்க் ஆகலையா பஸ்ல இருக்கு போயிட்டே இருக்கு ஓகே தேங்க்யூ Hi, good evening everyone. Can you hear me? Are you able to hear me? Last bench. Okay. Last bench, last year. Yeah. So the typical, start. Thanks Shiva and thanks to Dr. Suresh and all the other organizers, for inviting me to give, and first and foremost to accept such kind of, talk. And I'm going to thank all of you for not going to sleep for next 20 minutes. Is that a deal? Do we agree to each other? If I see anyone sleeping, what should be the consequence? I'll ask 10 questions. Okay? Fine. So, as you know, Dr. Ganesh introduced me. I am from Azim Premji University, which, many of you may not be aware. So, to start with, this is our campus in Bangalore. We have 80 acres campus in Bangalore, and we also have a campus in Bhopal, and we have one more campus coming up in Ranchi. The fourth campus is going to come up somewhere near Meghalaya. Okay, so and we are famous for this building. hostel building which is 40 floors. So students always have the complaint that their air pressure actually increases. So and in another 2 years, if you end up in visiting Bangalore, you may end up in seeing 2 more 40 floors building. So they want to ensure that even faculty don't hear anything. So it's a faculty residence. Fine. So this is part of the initiative by our well-known person Azim Premji, who is a Wipro person. I am sure you are all aware of. He took out 10% of his own earnings, which is amounting to somewhere close to 15,000 to 20,000 crores. So he has donated it for a philanthropic activity, and he was more interested in improving education system in India. So that's how this Azim Premji Foundation was started. As part of Azim Premji Foundation, we have this Azim Premji University, and our motto is basically, you can see here, education for social change. We just want to work towards just equitable, human and sustainable society. We have 16 undergraduate programs. We have 275 faculty members. So our university maintains 1:11, one teacher is to 11 students ratio. Okay. So you might have seen that I am going to talk about chemistry education. Does that mean that I am not a chemist? I am a hardcore chemist. In fact, when my son was born, we kept the name Pratik. Pratik means in Sanskrit symbol. So direct periodic table symbol. Okay. And then we also given our pet's name is atom. So I am a hardcore chemist. So I am not going to stop working on chemistry. So what research we do is and as in addition to that, I am also a polymer chemist. I have done my MTech and PhD in polymers. So we started with this project. You might have heard this PCB. Have you heard of the term PCB? Yeah, someone presented in the morning, printed circuit boards. If you see printed circuit boards, there's enormous amount of polymer which is used, which are thermosets. And what we are trying to do is, we are trying to use biological or biochemical methods, and we want to recover useful chemicals from the waste. Now if you go through the literature, all the PCB waste, people are all this recycling, whatever they are trying to do in terms of plastic recycling of PCBs, literally they don't do anything, they just put it as a landfill. They only recover all these useful metals and all those things, and they use chemical methods to even recover all these metals. I put there's top one thing I just wanted to all of us to understand, because we are all going to be research scholars, especially the people from fourth rows. There are this is called pasture quadrant, which I actually call it as, unfortunately this Azim Premji University had hidden it. I call it as a Premji quadrant. So what that means is, you have to basically ask a question when you do research, whether I am going for fundamental understanding or I am going for an applied research. Okay, so if both, when the terms are higher, you call that as pasture quadrant. In our case, it is Azim Premji who believes that that can happen very nicely in educational research. So that's why whenever we aim for any research, we have to aim for the pasture quadrant. Yeah, and to convert that into a proper numbers, how much plastic waste get into. You can see here, there's so much amount which is just getting discarded, and some amount is getting incinerated, where we get energy. Someone was discussing in the morning about PE being converted into fuels, right? And then some, you can see the amount which is getting recycled. Okay, so if you see here, thermoplastics are at least recyclable in an ideal case scenario, but thermosets are simply not recyclable. Okay, so there is no possibility of upscaling. So we have to do something. So, and we discussed about the major issues in polymers, which are characterization and solubility. And the other side of the thing is that if we can use biological or biochemical methods, we don't need to worry about characterization. Okay, because all those enzymes or fungi or even bacteria, they are going to attack certain specific places, and then we can at least we'll try to look for products which are neat and characterizable. Okay, I'll get in touch with you for all the questions you have in your mind. And yeah, that's why we are more interested not even in chemical recycling, we are more interested in biological recycling. Having said that, am I the only one working on it? Definitely no, it is a complete interdisciplinary research where microbiologists are involved, computational biologists are involved, and then polymer chemists is involved. Okay, if needed, we'll add even polymer engineers. I am a half polymer engineer, I have done MTech. So this is how the research is. But I am not going to discuss about this. I am going to discuss about something I feel is very important, maybe more than people who are teaching now. It's more important for those who are planning to teach. Just as a count, how many of you are planning to teach in future? No one else. Only one person, 2, 3, 4. So you are fully dependent on the teachers. Your kid, you will send it to school and then close your eyes. You are not going to teach your kids at all. If your children, your own children, come back from school and ask a doubt, you will say that no, I am not a teacher, I am not going to teach. Is that right? So those who did not raise your hands, let us understand that whether we are going to teach or taking teaching as a profession, we are going to be teachers for someone or the other. May not be in the formal education system, but informally you are going to teach, so you better listen to all these things. Okay, so there are many elements for any educational institution to flourish. The first and foremost, why you are all here at your own universities, for what? For salary, that is for the first row. I am asking the fourth row. You are all here to learn, right, something? So you are all here to learn and they are all here to teach. Am I right? So the first and foremost element of any educational institutions is teaching and learning. Second comes research and discovery. But unfortunately, all the higher institutions, all well-known institutions, all the institutions where all intellectuals go, end up in focusing more here. Somehow this has taken a back seat, right? Do you all agree with me? No, no idea. Say whatever you want to say, right? Okay, and then there are other elements like service, outreach. The job of Siva is to get you some jobs in somewhere, right? And then he was trying to find out what is the salary from HSP sir, right? Nobody is going to say, how much they are getting salary, especially in corporates. Fine. So what is teaching and learning? So teaching and learning is not so easy. It is not simply, someone coming and saying something to you and then you learn something and then you give exams. Whatever the marks you get, done. You got your degree and then you go away. That is not teaching or learning. Teaching and learning puts student at the center. And then when we say school, school means anything. Even universities are, schools in US. So school, and then teacher, and then there's something called learning outcomes, right? So you come to university to learn something. At the end of 2 years, you are expected to learn some things, at least to clear your CSR exam or your GATE exam, something, right? You have some learning outcomes to do. So it is so complicated. In addition to that, you have, physical, mental, intellectual, either knowledge or issues. And then you have your own background. There are so many things. So teaching and learning is not so easy, or it looks like a simple process, but it is highly complicated. You can see here, these are some of the things. If you end up in becoming academicians, if you end up in teaching, please remember, if you just reduce your teaching to only the intellectual part of it, it is going to become a cold abstraction. If you just reduce it to emotions, it becomes narcissist. If you reduce it to only spiritual, it is going to be even more bad. Okay, so teaching is a mixture of everything. Now there are 3 important things I have put: PK, CK and PCK. That's exactly what I am going to discuss. Is this. What is PK? PK is pedagogical knowledge. Pedagogical knowledge is something, there is a concept, say for example the concept of reduction reaction. So how a teacher teaches you, that is pedagogical knowledge. How much teacher knows is content knowledge. How much teacher knows about reduction or oxidation. So that is called content knowledge. So content knowledge is nothing but saying that I know chemistry. Pedagogical knowledge is nothing but saying I teach students. Whereas there is something which you develop over years after becoming, teachers, whether in a school or universities or any institution, is called PCK, pedagogical content knowledge. You know that there is this particular concept I have to teach in certain way, so that in my class, if there are 40 students, there are at least 30 students who can understand the basics of it. So that is called pedagogical content knowledge. So third part is I know how to teach chemistry to students. Now, I don't know whether you have heard this. Bernard Shaw, a very well known person, always used to say that those who can do, those who can't, teach, right? That's the reason that only 4 people raised your hands, because you think that those who can't can only teach, right? That is not the case. This person called Lee Shulman is a very well known American psychologist as well as a scientist. He changed the whole statement. He said that those who can do, okay, so you are all going to be in industries or R&D or wherever you want, but those 4 who have understood chemistry are only going to teach. So rest you can assume that you have not understood chemistry. Okay, now tell me how many of you are planning to teach? Still the 4. Fine. Okay, so what they talk about effective teaching or effective learning. When a teacher is teaching, it is not easy. Teacher has to have certain things. So teacher has to have, what is this happening? Sorry. Teacher has to have something called content knowledge, and then pedagogical knowledge, and then knowledge of students, and then there's something called curriculum. Like when you are doing MSc chemistry, you have something called curriculum, and then teachers also need to know how they have to take assessment, right? So 1 minute, huh? I thought I have taken only 5 minutes. It got over. Okay, fine. So I am going to take 10 minutes. Okay, fine. So teaching is not easy. Okay, complex process. So, so you can see here, you just don't teach. You have to gain knowledge from so many people. People have to come together, sit, discuss about how a concept can be taught in a very effective way, and then that is how the teaching enters into the classroom. I'm not going into this. So what we thought, when we started this educational research, measuring this pedagogical content knowledge is going to be easy. I will get into 10 teachers class. I will see how much they are teaching, and then I will make a module for the rest of the world to follow. Okay, with that thought, we started this research, and then what we realized, that nobody was willing to let us enter into their classes. So what is the best way we can do? We thought we'll get into these, teachers' classrooms. So getting into, school teachers is very much easy in the sense that we can capture how much they learned in university, at the same time how much they are teaching in a school. So this is what, we started with. And then we came up with a lot of, research design. We got the permission from state government departments. We got into 3 states. And then we had a very big team who was working on it. One person was working on physics, another chemistry, another biology. And then we started following all these tools and all those things. And then ultimately what we realized when we started attending their classes is that teachers always have excuses for getting into the lecture mode. So teachers always, get into the lecture mode saying that we don't have time, we have lot of work, other responsibilities, we are, given this duty, that duty and all those things. Whereas the underlying problem was they have actually lack of clarity in content. They actually, have a lot of misconceptions in any, concept. And they think that post-corona, they think that anything which is shown as simulation or, PPT, students understand everything. Okay. And then they think that whatever is given in the textbook is the final and foremost one, even if the textbook has given a wrong information. So, and the next problem is they don't want to write. Anything they understand, they don't want to write it in terms of, documentation. When we try to capture their knowledge, you can clearly see that, I may not be able to explain the color code now, but we clearly saw that nobody wants to write. Nobody wants to talk about their teaching in the first place. If you ask them to write and document what they are teaching, not possible. So how we will, tap the Robin Hood job of somebody having a very good knowledge and then passing on to the others who need the knowledge, which was, not possible for us. So what we realized is this, which is very, very important, and with that I'll, put the full stop, is this. They cannot even connect why they are teaching a concept and how it is related to their daily life. Now, be it in school, be it in PU college, be it in university. Okay, why this concept has to be learned by a student? Now, that, for me, that has to start with a real life example. Okay, why this particular concept has to be learned? Why it is, how it is useful to your day-to-day life. So the teachers are not able to connect what they are teaching with the application in day-to-day basis. And the second one is that they come with certain beliefs, and with that belief, whether it is scientific or non-scientific, they don't want to listen to others. So it is very, very difficult to change their beliefs. So with this, what we realized, we were continuously taking these workshops. We started taking this content enhancement workshop, and after 2 years of completing the workshop, now we have come to a point where teachers started to reflect, personally reflect, and they started to feel that, okay, certain things need to be done. So I've just put one example. They feel that, they need to show experiment, they need to show inquiry, they need to, give some assignments, they need to do projects. So all these reflections have come up. Now you might have seen in the morning, I think Dr. Annadhasan showed a picture about sound. He showed how vibration, makes patterns and how sound is traveling from one byte to the other byte through the wire. Now, until and unless you have not learned all those things, these are all school experiments actually. Until and unless you have not learned all this experimental, experiential learning, okay, how would you even understand that that concept was related to sound? So the experiential learning, or for chemists, it is experimental learning until and unless you do experiment. Like Dr. Natte was making a statement that, in textbook this reaction is given and then you guys think it is very, very simple, but when you start doing it, it is not simple. But until and unless you have not done that experiment, you are not going to understand that that experiment is going to be easy or difficult. So the experiential learning and the experimental learning or inquiry based learning, without that we cannot do anything. So what we are doing now is everywhere we are going and we are trying to increase the content, enhancement of teachers, not students, okay, content enhancement of teachers. And then once, we feel that, okay, there's certain level of personal reflection has come up, then, we are basically, trying to get into the actual research, and this is a reality, okay. So with this, I want to, thank all of you and listen to me, and please read this, and this is very, very important, whether you are going to be a direct teacher or an indirect teacher or you are going to be a researcher, okay. Thank you. And I am so sorry.
Yeah, it was an excellent talk. I don't know if you have any questions on this. If you think, if there are any pressing questions, we can have one. But if there are no questions, we can discuss in the tea time. Yeah, sure.
Yeah. He has a question.
Yeah.
Subsequent academic years was greatly affected, and we are actually one of the victims for that, because of which our semesters are being cut short. So all of the lecturers or the professors are forced to teach us the subject in a very small time, and we are supposed to learn those things in a very short time.
No summer holidays, that was his problem. Yeah, that is exactly how, why and how we started this, research with. We wanted to show teachers that lecture method is not the one and only method to teach a concept to students. There are so many ways. If it is an easy concept, please give it as a project, okay. Combine 2 or 3 chapters, give it as a project, because there are certain things we have seen in our own teachers following. They have never told us that I am teaching you, this is a case-based learning, or this is a, project-based learning. They never told us that this is the method we are following, but they used to follow when we had teachers. They used to give a topic, they used to ask us to go do search, come back and, present to the class. That was more of a case-based learning. Okay, so we have to mix and match so many, learning methods. That's the only way we can actually finish the portions. Just to give an example, our university, we have a very short semester. We are not like others. Azim Premji University follows 15-week semester. Okay, one semester we have only 15 weeks. In 15 weeks, we have 1 week for exams. And we don't, we follow this continuous and comprehensive evaluation. So how we are able to finish a chapter, finish one particular course is basically because we are able to use and mix all the, teaching and learning methods available with us. The way I said, project-based learning or assignment-based learning or case-based learning, inquiry-based learning. So we try to mix and match, and lecture also. Lecture is actually significant amount, but we try to mix and match. That is how COVID loss can be minimized.
Right.
Okay.
Yeah, thank you.
Thanks.
Yeah. Yeah. So, yeah. So from the organizer side, I thank the.
Thank you.
Yeah.
Role reversal.
Thanks a lot. Thank you. Thanks. So with this, I think we close this session. I hand over the mic to the organizers.
Thank you, Ganesh Venkatraman, for wonderful chairing this session. Next, come on. announcement. 20 minutes.
Now it's time for cultural programs.
எவ்வளோ நிமிஷம் 20 minutes இருக்குமா இப்போ கல்ச்சரல்ஸ் கிடைக்குதா நேஷனல் டான்ஸ் அனௌன்ஸ் பண்ணிட்டேன் 2 minutesல வரேன் டான்ஸ்
Dear participants, now almost all the technical sessions are over. So now we are at the end of this CRSA 3 days symposium. The next 20 minutes we have a short cultural program, so followed by the validity sections. After the validity section we have the high tea. Okay, please. Because we planned 6 months before. இங்க வந்து உட்கார சொல்லுங்க.
பிளேடு தான் எடுக்கிறாங்க அதான் கஷ்டம் இல்லையா
A nice feast for eyes. Next, we welcome the Devaratam. It's a dance of goddesses in Tamil. Wow, a glorious gallery. We had a nice feast of ice, an everlasting reminder of this occasion. Next, we have Parayatam, the folk dance of Tamil Nadu. Many thanks to Vivekananda College, Thiruvengadam. Next, we will have the valedictory function. We will have the
Let's now move on the valediction. Tamil Thai Valthu.
ஆக்சுவலாக ஜனகணமன டேரக்டாக போக சொல்கிறாங்க. உங்களுக்கு என்ன இருக்கணுமோ அதையும் சொல்லிடுறீங்க. தமிழ்த்தாய் வாழ்த்துன்னு சொல்லுவாங்க. நான் சொல்லிட்டேன், எங்கே சொல்ல முடியாது.
Now, please stand for தமிழ்த்தாய் வாழ்த்து.
நீராறும் கடலுடுத்த நிலமடந்தை கிளிலொழுகும் சீராறும் வதனமென திகழ்பரத கண்டமிதில் தெக்கணமும் அதிசிறந்த திராவிடனல் திருநாடும் தக்க சிறு பிறை நுதலும் தரித்தனரும் திலகமுமே அத்திலக வாசனை போல் அனைத்துலகும் இன்பமுற எத்திசையும் புகழ் மணக்க இருந்த பெரும் தமிழனங்கே தமிழனங்கே உன் சீரிளமை திறம் வியந்து செயல் மறந்து வாழ்த்துதுமே வாழ்த்துதுமே வாழ்த்துதுமே.
Wholeheartedly we bring forward the dynamic person, Dr. Suresh, Department of Chemistry, Madurai Kamaraj University, to welcome the gatherings.
Very good evening to everybody. So we are at the end of the final session of the 3-day national conference. In Tirukural, one of the very popular Tirukural, உவப்ப தலைக்கூடி உள்ள பிரிதல் அனைத்தும் புலவர் தொழில். So actually the தெய்வ புலவர் திருவள்ளுவர், he just wrote for the poet, but at the time he may not be aware about the scientist. But the same Tirukural, it's exactly matches with the chemist for this function. In Tamil it called as மகிழ்ச்சி பொங்க சேர்ந்து பழகுவதும் பிரிந்திட நேரும்போது மனம் கலங்குவதும் அறிவிலாக சிறந்த ஒரு செயலாகும். பட் இங்கே யாரும் மனம் கலங்கலை. பட் இஃப் யூ translate in English, it is the provenance of scholars that meeting bring delight and departure leave memories. So this scientific meeting makes a lot of memories with a lot of intellectual property. You can gain a lot of information. So I believe that this 3-day national conference conducted under the auspices of the Chemical Trust of India, current resident in chemical science, enlighten your chemistry knowledge, and also it open a lot of gates for new research opportunities. So with this occasion, I am very happy to invite all the delegates and also speakers and the student participants for this conference. Particularly, I would like to welcome our mentor, our CRSA local chapter's past convener, Professor Ramaraj, for this valedictory section. Then I would like to welcome one of the senior professors. It's a very popular academician, Professor H.S.B. Rao, for this valedictory section. Next, I would like to welcome Professor Seduraman sir from Gandhi Gramam Rural Institute to deliver the valedictory for this valedictory. And also, I would like to welcome Professor C.V. Ramana and Professor Shanmugam sir, and Dr. Nithyanandan, Dr. Arunachalam, Dr. Anandan, Dr. Muthusamy, Dr. Manivanan from BHU, Dr. Lokesh from VIT, and one of our colleague, Dr. Sujin Jose, for this valedictory session. So particularly, it's very important, I want to welcome all the participants, because the past 2 days, you keep your passions and you are sitting and still you are filling the auditorium. It's one of the very happiest moment, because validity section, it's difficult to find such type of this number of the heads. But however, from your presence, we thought that it's a great success of this 3 days conference. I'm very happy to welcome all the student participants from the different universities and students from in and around Madurai colleges. And also, finally, I would like to welcome our volunteers, because they are tireless working for the 3 days for the success of this compound. I welcome all the volunteers for this compound. Thank you. Welcome one and all.
Thank you, sir, for a kind welcome note. It will be my pleasure to invite our professor, Dr. S. Sivakumar, to honor the guest, Professor Sethuraman. We invite our professor, Dr. Suresh, to honor the guest, Professor H.S.B. Rao. We invite our professor, Dr. Sivakumar, to honor the guest, Professor Ramraj. Now we invite our professor, Dr. Sivakumar, to honor the guest, C.V. Raman. Feedback from participants.
The participants, you may share your feedbacks regarding the 3 days conference in all the aspects. I welcome the feedback from the participants. Come on. Yes. Any? There is no feedback. Anybody? Yeah. Just come on. Your feedback is whatever. Nobody is present. Come on. Huh? Yeah, come here. You are welcome. Follow with next.
Okay.
Wow, you come here. Come to stage. Huh?
Sir, please validated to stand in the stage. Sir. Just a student, MSc students. Actually, every professor's posted their intellectual properties. They are very important. What did I feel is that because of the lacking of time, they are forced to turn out all the slides. So I expected to explain all of them. I expected Dr. Subramaniam from quantum chemistry. He was explaining about nuts and bolts of every quantum chemistry, but he was forced to move the slides and he was stopped. He too had too much of slides, but he was stopped. I know that. And the question and answer sessions can also be some more increased. The time can be increased. I know I can understand there is very less time, which was good. But this forcing the professors to stop the slide was pretty much paining in my heart, because they, really, there's too much of stuff. We have. I was just writing it. So far, I have written 37 professors in my notepad, and where they all belong to. It will be easy for us. Just their name, their universities. Just you will get an email ID. You can write to them. You will get a PhD. Qualified. So you can also say I participated in MK University. You just offer me a PhD. I hope so. They might offer. That's the thing. Okay. And the contributions of the volunteers was very good. They taken care of very good. Thank you. That's it.
This is a completely different concept, okay? So you, within a time slot, you have to be, it's not that you cannot tell all the stories. Cutting edge only, this conference only for cutting edge, okay? So that is different. That kind of meeting is completely different. So the speakers should present their work within a timeline, okay? So you can interact anytime. There's no restricted. Every time you can interact by email. You can email them 3 times, wherever it is. Fine? Yeah, thanks.
Actually, there is nothing wrong here. There are different ways of arranging lectures. Hope you remember at your department, they arrange 1.5 hour popular lectures. And then 1 hour lecture. Then plenary lecture, 45 minutes. Then the middle-aged speakers, 30 minutes. And youngsters, normally 20 minutes. So that is the way different kind of lectures are arranged. So this kind of seminar is planned to expose what's going on in India, particularly in the current topic. So we have to give it in 20 minutes. So there are different kinds of lecture series. So this is one such a thing that the speaker also should learn to put it in 20 minutes. So we are supposed to do that. So actually what is done with this time is actually it's a planned one. So starting from 1.5 hour to 15 or 20 minutes, there are different kinds. So now that you are able to know 40 different kinds of research and interest, what's going on in India. So this aspect is the last category where we want to expose more. So the speaker also should cooperate to learn to put their points in 20 minutes. So it's not a mistake of anybody.
Yeah, feel free. Feel free to express your views, okay? That's a good for, appreciate you, really. So that's, you should express your feelings, what you feel. Come on.
Good evening to all. I am Balabhavitra from 2nd MSc Chemistry at NKU, School of Chemistry, sir. Sir, for all session, I can really enjoy it. All professors are அவங்களுக்கு கொடுக்க டைமில் வந்து எவ்வளோ ஈஸியாக எக்ஸ்பிளைன் பண்ண முடியுமோ எக்ஸ்பிளைன் பண்ணாங்க சார். பட் எஸ்டர்டே வந்து நேற்று அந்த ராமன் ஸ்பெக்ட்ரா I have really enjoyed it. I have lot of knowledge from these 3-day sessions. Thank you, sir.
Thank you. Yeah, come.
So good evening, everyone. Myself, Mukundram from Pondicherry University. So first of all, I'd like to begin my feedback by thanking all of the volunteers who have worked their heart out to welcome us and to feel us at home here. So please give a big round of applause for them. And yeah, something I would like to add. Before coming here, so I'm doing my MSc project under my professor Balakrishnarajan. So he told me, whenever you go to a conference, since you are only an MSc student or even a student who is pursuing research, no one expects you to understand what is going on completely. Because the work that has been presented by the professors is the work that they have been doing it for years. And we are nothing before their experience. But one thing we are expected to do is try and understand and apply in our lives or apply in our subjects. That's what I found really invigorating and interesting here. And because while I was searching for my project, I have gone through what is going on outside. And I'm really happy to see almost every concept that has been applied here. I have seen it in 1 or 2 research papers. So I can say that because current trends in chemical sciences, because we are not in a single space anymore. The world is a global village and every subject is currently under a microscope of something called interdisciplinary research. Even in chemistry, biology is in chemistry, physics is in biology, everything is there. So it is not a single concept anymore. And I'm really happy to have been exposed to every concept of science after coming here. Because we have a lecture from metallurgy, we have had a lecture from density functional theory, we have had lectures from organic chemistry, physical chemistry, biophysical chemistry, everything. So it's really blessed to be here. And thank you so much for conducting such a conference. Thank you, Sivakumar. Thank you.
Thank you. Thank you. Anyone? Any other?
We will now have Best Poster Awarded distribution. Raman Kavitha Preeti from CLRI.
Sir.
என்ன பேரு? தெரியல எனக்கு பேர் தெரியல. Yeah, see, actually we got several posters they presented. Among them we selected 5 best posters. So among them the best poster award goes to Raman Kavitha Preeti, VIT. The another best poster, Roja Arivalagan, Gandhigram Rural Institute. The next prize, I invite Dr. Ravana to distribute next prize. Mr. Saxena Smile, University of Madras. I invite Professor Surya Prakash Rao to give this presentation next one. It goes to Vivekananda College, Tamil Valavan Kamachi. The another best poster goes to Pondicherry University, Mr. N.S. Mohundram. Congrats, man. Nice. Thank you.
May continue the memories, continue to warm our hearts and inspire us in the day. I please all to join in welcoming Professor M.G. Seduraman, Department of Chemistry, Gandhigram Rural Institute, to offer valediction address.
Respected senior professors on the stage, my dear delegates from various institutions across the country, student friends, a very good evening to all of you. At the outset, let me congratulate the Madurai Kamaraj University for coming forward to host this National Conference on Chemical Research Society of India titled Current Trends in Chemical Sciences. At a very difficult phase of MKU, they have successfully hosted the conference. The credit goes to the organizers. It is not an easy joke to carry forward with the planned activity amidst very difficult circumstances. And with the help and cooperation of all others, they are able to successfully do it. And in what scale? About 67 posters, 43 lectures, unimaginable in 3 days' time. I congratulate the organizers once again. Friends, this is the era where we need to sensitize people on the need to take up research activities at the institutional level. I do not know how many of you know the present trend in the higher education where not many students are lured to the disciplines like chemistry. If you see the number of seats that are getting filled up in sciences, it is a little worrying. At least chemistry is a little better compared to mathematics and physics. The seats are not getting filled up at all. Not just in Tamil Nadu, but across the states. This is the kind of situation that we have. We may not be able to have teachers who will be able to teach science in the schools. We may not be able to have good researchers in universities and colleges and all that. So a difficult situation is there. Rightly, the Department of Chemistry here at Madurai Kamaraj University has come forward to organize this and sensitize the students from across the country. And in fact, it's a kind of feast for them to listen to the luminaries discussing various topics. Of course, there was a murmur saying that they are not given enough time and all that. At least ignite the minds is the kind of slogan. So you would have probably got ignited out of what has been told. Please remember, ladies and gentlemen, publish or perish this is the slogan of yesterday. Publish, cherish and flourish is the slogan of today. So people want to have their publications in quality journals. Gone are the days where people were compromising with the publication in local journals. Now SCI index journals have come and high impact factor journals have come. Such quality metrics like your H index, I-10 index, citation index, all that actually plays a big game. And in fact, I'm sure that in another 5 or 6 years' time, the visiting card will have such details also. A kind of electronic card where you will have dynamic details of the researcher also coming to. Suppose if you take the kind of research statistics, in the year 2018, about 1.35 lakh publications have come from India alone. And if you look at the country-wise statistics, we are 5th. And we are, see, if you look at the kind of investment statistics, we are the amount of money that we are investing in research R&D activities is only 0.65% of the GDP. So very poor investment, but high return is there. But if you look at the kind of articles that are there in Q1 journals, it is much, much less. And if you look at the number of PhDs that are coming out of universities in India, it is roughly about 8,000 from science and about around 1,800 to 2,000 in chemistry alone. So this is the kind of statistic which is really available. So what is needed is we need to have the research activities intensified. We need to have quality research also. Please listen, ladies and gentlemen, it is not enough if we dream of a developed India. India will become Vishwaguru, provided we all participate and contribute towards that. How will we contribute towards that? It is all through development. Development cannot happen without research. So research and development should be there. Of course, UGC also has done its part by asking all colleges to set up an R&D cell in every institution. Of course, the institutions are also trying their level best to boost research, but unfortunately, there is a kind of murmur. Even PhD is, there is a kind of what? PhD expansion is please have degree program. So this is the kind of murmur which is also heard. So I wish that people realize that knowledge is measured not in terms of length and breadth, but it is measured only in terms of depth. So how deep we are in subject. So that depth has to be intensified. So only through research, we can learn the subject in depth and we have to analyze, and any research that we do should contribute for the growth and development of this country. Societal based research should be there. There is a kind of thinking that we should do more on applied science and all that. Of course, there is a mad rush for engineering and your medical colleges also. Let me tell you one thing, your engineering or medicine, they are only applied sciences, nothing but applied chemistry, applied physics, and applied biology. If there is no growth in fundamental science, there will not be any growth in the applied sciences at all. So we need to really strengthen our fundas and then see that the best is contributed towards the development of basic sciences. In that way, every small arena of chemistry has to be equally given importance so that this subject really is strengthened with the kind of interest that you are showing. We are confident that we will see a kind of growth in this country in chemistry domain too, in leaps and bounds. So this university, through this forum, CRSE, has given you a platform to listen to the experts and widen your horizon. I'm sure that you would have been exposed to latest terminologies, some of the terms which probably you have not heard in your life at all. I'm sure that this will motivate you to go into this. So Mada, Pida, Google, Daivam has become the new word. I'm sure that you will Google out and see that the best is actually obtained to you. Please remember one thing. See, this is a kind of yajna that we have to do. Learning the subject, just not for the sake of learning it, but for practicing it. Chemistry is a practicing science. So through research, you can see that there is a development in this domain too. I'm sure that you will put on your heart and soul to learn this. I will always say education should never be out of compulsion. It should be passion. There should be fire in the belly. So we should have enough or more fire in the belly to learn this subject. I'm sure that forums like CRSI gives you enough motivation to see that the best happens to the domain of chemistry, to the people of India, and to the students sitting before us, and the researchers too. So I'm sure that we will really dedicate ourselves to contribute to the cause of chemistry, make this discipline grow, and we will have our own contributions towards that. So thank you all for your presence and patience. I'm sure that you would have enjoyed the proceedings of this 3-day national seminar, and this will really be followed in the coming years too. And I thank all the departmental faculty members for putting their heart and soul, and a core team which has really done amidst difficult circumstances, and the host of volunteers who have really given their support for the successful conduct of this. Last but not the least, without delegates, nothing really can move. The success of the national conference depends only on the delegates. And this is the first time that I'm seeing so many faces in the valedictory session too. So I should thank each one of you for your valuable presence here. So thank you all once again for your presence and patience. Thank you, everybody. Untouchability is a crime. Let us all keep in touch. Thank you.
Thank you, sir. We are honored to have Professor with us today. Join hands in welcoming Professor Surya Prakash Rao to deliver the felicitation address.
Good afternoon. Hello. Good afternoon. I think it is not, I don't have much to say here because Professor Sethuraman covered everything, to tell. But I can only tell this, that I am standing before you in front of my students. And it, of course, is such a great pleasure and happiness for me. And, all of you, what I should say, feasted in chemistry for past 3 days, and let this feast be with you forever. So enjoy yourself. That is very, very important. Be happy and keep smiling, because one smile can win million hearts. And if you keep smiling, the world is with you. Thank you so much. God bless you. Thank you.
We invite our Professor Ramraj to deliver the felicitation address.
Actually, I am one among the organizers, but anyway, still I can say a few words. Particularly, I very much closely interacted with the CRSI, the society at Bangalore. Actually, the society started in the year 1999. You could see in the abstract book. So the first meeting I attended at Bangalore, and then we realized, actually the basic idea was to create an awareness among the chemists, just like American Chemical Society, Royal Society of Chemistry. So that is the idea Professor Sena Rao wanted to inject, and now it works as in the inaugural session, Professor Chandrasekharan told. It started with 100 members, now it exceeded 3,000 members. So that way we are really happy. And being the, I attended the first meeting and the founder member of this society, when they announced the life member, and there were members from big cities and institutes, but Madurai was the first one. We had more number of life members we joined from the smaller places. So that way, in fact, the CRSI appreciated our chemist in Madurai that made us to create the local chapters after 2 years. Apart from the metro cities, Madurai was chosen as one of the city to start with the local chapter. And the very first CRSA local chapter seminar was conducted in Madurai. Then other local chapters followed our thing in the year 2003 or so. So we have done the job last nearly 20 years or so, particularly with the help of Dr. Sivakumar and Dr. Suresh. Whenever I organized this CRSI sponsored seminars. So they were the pillars, and we did a wonderful job. And I'm extremely happy that now they carry forward the torch. And more than that, I'm always a bit worried about inviting more than 12 to 15 speakers. But these young people, they are careless, and they are really done a excellent job. When I saw the list of speakers, I was also a bit worried. As one of the participants pointed out, we are supposed to give more time, but in your research seminar, it's not. In a popular lecture, departmental seminar is okay. But the idea really was, it's not that 40 speakers. You look at the list all over India, the young researchers from all over India, the active researchers, and also senior researchers. So that was extremely happy. And at this juncture also, I tell you the participants that Madurai Kamaraj University became one of the institutional life member in CRSI by paying 1 lakh, I think 1 lakh. We paid, and we are one of the very few institutions who became the life member, institutional life member. That also, it's a privilege for us because our activity showed that way. So we thank our university, the Vice Chancellor, the administration for becoming the life member, the institutional life member. As well, all the years they support us whenever we go for such a seminar. And this time also, our present Vice Chancellor, Professor J. Kumar, was really very cordial, and they supported us. So with these words, I thank particularly Dr. Sivakumar and Suresh and their team and the volunteers for making this meeting so successful. Above all, and as the Professor HSP Rao pointed out, and Professor Sedharam also, so the auditorium is full in the validatory section. So that itself is really great that no one really went out, even though Madurai is a temple city, or Kodaikanal one side, or Rameshwaram other side, but you have not escaped to those places. So that way, really, the seminar attracted so much. So with these words, I congratulate everyone, particularly my colleague, for carrying forward that torch. Thank you. Thank you so much.
We invite our Professor C.V. Ramana to deliver the felicitation address.
Yeah, it's very difficult to talk at the last because already whatever I am supposed to speak, they have spoken. But one thing what I would like to tell you is regarding the presentations and time. See, now actually you have a 3M presentations. It was mainly for the students. So you are supposed to sell yourself, whether it's research or it's a product, in 3 minutes. Okay, so don't expect that actually somebody will give you 1 hour and say whatever you want. So that time, now actually the time is very competitive. So you won't get more than 1 minute, especially when you go for an interview, to say about yourself and to make sure that actually you are valuable for them. Okay. Anyway, thank you. I'm very happy actually because nowhere I have seen actually auditorium full all the 3 days. Okay, so most of the times inaugural session we will see all the people, and after some time you won't see anybody. Only we'll be talking with the front chairs. It's not the case. That was really happy. Thank you.
We invite our Professor Dr. Sivakumar sir to deliver the vote of thanks.
Good evening, everyone. So we have come to the end. Respected professors, Professor Surya Prakash Rao, my guru, my guide and a philosopher, and Professor Ramraj, our mentor from School of Chemistry. He is only guiding, several things, you only guided us for all these proceedings like conducting meetings and everything, chemistry, several things. Respected Professor Seduraman is another mentor for us, and Professor Dr. C.V. Ramana from NCL Pune, and my dear friends, students. Simply you can say it's just thanks. It's not enough. More than that, I don't know which word I have to say other than this thank. But anyway, thank you for everything with students and all. But first of all, I several people are there to. I should thank them. First, I thank to all the speakers. All the speakers are very busy and very popular speaker, scientist actually. To getting their time, is very difficult actually. For us, up to that, this Madurai Kamaraj University, they came, they spent here for 3 days with us. That's tremendous actually. I must thank to them. Second things, the participants. Without participants, nothing can be done. So this conference's success means because of the participants only. We can arrange speakers, fundings, everything, but without students, participants, nothing will be happen. And sponsors also is very, very important because we have to meet out the expenditures. I thank all the sponsors, Horiba India, DSK InnoSciences, Laser Spectra Services, and Anatech. And funding also, I thank SERB, RUSA 2.0, and CRSI, CSCR for funding. And very importantly, I should thank the estate officer, Mr. Anand Kumar, our university. Because of him only this conference is happening actually. He only gave this auditorium immediately for this conference. He arranged all the things. I must thank to him. And the volunteers. Without them, it's very difficult to organize this kind of meetings. All volunteers, my students and Dr. Suresh students and students from School of Chemistry, and my students, and Dr. Kalyani from DD, Madurai Kamaraj University. She helped a lot. She was sitting here for 3 days here. And this conference, after 24 years, I met my friend, my MSc classmate, Dr. Muthusamy from Azim University. Many things, this conference gave me, and my dear friend Nityananda is always with me. And the last, I thank to our Vice Chancellor and Registrar, and finally Madurai Kamaraj University for this opportunity. Even though we have facing difficulties, but this meeting is, they allowed me to conduct. Thank you very much. Thank you for all. Thank you.
I would like to thank the participants for their enthusiastic participation. Without you, all this event would not have been possible. Thank you very much again. I would like to take this moment to thank the very motivated and dedicated organizing committee who made this conference immense successfully. Please stand for national anthem.
जनगण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड उत्कल बंगा विंध्य हिमाचल यमुना गंगा उत्कल तव तरंगा तब शुभ नामे जागे तब सुभाषिष मागे गाहे जब से गाता जनगण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे